morning, everyone. I'm Alina, Program Manager for TensorFlow. Thank you. Welcome to the 2019 TensorFlow Developer Summit. This is our third annual and largest developer summit to date, and I'm so happy to have all of you here, both right here in the room and on the live stream. Welcome. So I'm just curious, by a show of hands, who traveled a little bit further maybe to get here? Europe? Asia? Africa? As far as Australia? Woo! Awesome. Welcome to all of you. We have a lot of great talks ahead, some exciting announcements and cool demos, so let's get going. We are living in a formative moment of history right now, where machine learning is experiencing an unprecedented revolution. The way we fundamentally think about and interact with computer systems has inherently changed due to the breakthroughs in the field of AI. And this is due to three major factors. First, we have lots more compute, specially designed ML accelerators like these TPUs let you train models faster than ever before. Secondly, we have breakthroughs in the field of machine learning. There are novel algorithms created every month, like BERT, an innovative approach to natural language processing, which lets anyone around the world train their own state-of-the-art question answering system. And finally, we have lots and lots of data. We're seeing new waves of data sets come from all kinds of disciplines. For example, the new Open Images Extended dataset. This is a collection of over 478,000 images that volunteers have added with the pursuit of inclusivity and diversity. So all three of these are basically changing how we solve challenging real-world problems. And it's really cool to see that TensorFlow is the platform that's powering this machine learning revolution. It's allowing developers, businesses, and researchers around the world to benefit from intelligent applications. And we've been really amazed by what the community has built with TensorFlow. Developers have been using TensorFlow to solve problems in their local communities. So I don't know if any of you were in the Bay Area during the tragic Paradise Fire, but one of the consequences was that air quality was really bad. It was in the high to mid 200s on the air quality index. And as difficult as this was for us, in Delhi, India, during winter, the air quality can get up to about the 400s on the air quality index. And this is considered very dangerous. So pollution sensors can help gauge air quality, but they're very expensive to deploy at scale. So a group of students in Delhi built image classifiers in TensorFlow and used those to then build an app called AirCognizer. And what it does is basically, just by using the images on a smartphone, it gives an accurate estimation of the air quality. Businesses are also fundamentally improving their products and services built with TensorFlow. For example, Twitter strives to keep its global users informed with relevant and healthy content. But this can be hard when users follow hundreds or even thousands of people. So to solve this, Twitter launched Ranked Timeline, an ML-powered feed which shows the most relevant tweets at the top of the timeline, ensuring users never miss their best and most relevant content. And by using TensorFlow's ecosystem of tools like TensorFlow Hub, TensorBoard, and TensorFlow Model Analysis, Twitter was able to reduce both training and model iteration time, as well as increase the timeline quality and engagement for users. Specific industries are also being very much transformed by ML. GE Healthcare, for example, is using TensorFlow to improve MRI imaging. They use TensorFlow models that run real time on MRI scanners and can actually detect the orientation of the patient inside this scanner. And this is really great because not only does this help the diagnosis, but also lowers the errors and exam time. But also what's really cool is it basically expands this technology to many, many more people around the world. TensorFlow also powers bleeding-edge research. A team of scientists, researchers, and engineers at NERSC, Oak Ridge National Laboratory, and NVIDIA recently won the Gordon Bell Prize for applying deep learning to study the effects of extreme weather patterns using high-performance computing. They built and scaled a neural network using TensorFlow, of course, to run on Summit, the world's fastest supercomputer. They achieved a peak and sustained throughput of 1.13 exaflops in FP16, which is equivalent to more than a quintillion computations per second. I just think I need to pause for a second because that is ridiculously fast, right? In addition to these awesome examples, there are thousands and thousands of people all over the world doing amazing work using TensorFlow. And the power and impact of TensorFlow would not be what it is without all of you. Thank you. It's with your help and interest that TensorFlow has become the most widely adopted ML framework in the world. And right here, I'd like to show the latest map of GitHub stars who self-identified their location. I'm sure many of the dots on this map are right here in the room and on the live stream, so I just want to say thank you one more time. And this growth has been absolutely amazing. TensorFlow has been downloaded over 41 million times and has over 1,800 contributors worldwide. Last November, we celebrated TensorFlow's third birthday by taking a look back at the different components that we've added throughout the years. But today, we'd like to talk about how TensorFlow has matured as a platform to become an entire end-to-end ecosystem. And TensorFlow 2.0 is the start of a new era, and we're committed and focused on making it the best ML platform for all users. To talk more about TensorFlow 2.0, I'd like to introduce Rajat Manga, Engineering Director of TensorFlow, on stage. Thank you.
Thank you, Alina. Hello, everyone. I'm Rajat. I'm an engineer on TensorFlow and have been involved with this since the very beginning. And it's been great to see what we've been up to over the last few years, all the amazing growth and all the amazing things that you've done with it. It's also been great to hear from you. You told us what you like about TensorFlow, and equally importantly, what you would like to see improved in TensorFlow. Your feedback's been loud and clear. You asked for simpler, more intuitive APIs and development experiences. You pointed out areas of redundancy and complexity. And you asked for better documentation and examples. And this is exactly what we've been focusing on with TensorFlow 2.0. To make it easy, we focused on Keras for a single set of APIs and combine it with eager execution for the simplicity of Python. With flexibility to try the craziest ideas and ability to go beyond an exaflop, TensorFlow is more powerful than ever. With the same robustness and performance you expect in production battle-tested at Google. Let's start with the overall architecture for TensorFlow. You may be familiar with this high-level architecture. There have been lots of components and features we've added throughout the years to help support workloads to go from training to deployment. With TensorFlow 2.0, we're really making sure that these components work better together. Here's how these powerful API components fit together for the entire training workflow. With TF Data for data ingestion and transformation, Keras and pre-made estimators for model building, training with eager execution and graphs, and finally packaging for deployment with SaveModel. Let's take a look at some examples. The first thing you need is data. Often you may want to validate results or test your new ideas on a common public data set. TensorFlow datasets includes a large and rapidly growing collection of public datasets that you can get started with very easily. And combined with TF Data, it is simple to wrap your own data to. Here's a small sample of the datasets that are available, and all of these and many more are included there. Then with Keras, you can express the model with layers just as you are used to thinking about it. Standard training and evaluation is packaged as well with model fit and evaluate. Since deep learning models are often computationally expensive, you may want to try scaling this across more than one device. TensorFlow comes pre-built with mirrored strategy that works with small additions to your code. Starting from a pre-trained model or component also works well to reduce some of this computational cost. To make it easy, TensorFlow Hub provides a large collection of pre-trained components that you can include in your model and even fine-tune for your specific dataset. Keras and Estimator offer high-level building blocks for an easy-to-use package. They come with everything you might need for typical training jobs. But sometimes you need a bit more control. For example, when you're exploring new kinds of algorithms. Let's say you wanted to build a custom encoder for machine translation. Here's how you might do this by subclassing a model. Here you can focus on implementing the computational algorithm and let the framework take care of the rest. And you could even customize the training loop to get full control over the gradients and the optimization process. While training models, whether packaged with Keras or more complex ones, it's often valuable to understand the progress and even analyze the model in detail. TensorBoard provides a lot of visualization to help with this. And now it comes full integration into Colab and other Jupyter notebooks, allowing you to see the same visualizations right from within your notebook. All of these features are available in TensorFlow 2.0. And I'm really excited to announce that our alpha release is available for you as of today. Many of you in the room and across the world really helped with lots of work and testing to make this possible. I'd really like to take this moment to thank you all. Please give yourself a round of applause. We really couldn't have done this without you. In addition to all the great improvements we talked about, this release comes with a converter script to help you upgrade from 1.x and a compatibility module to give you access to the 1.x APIs for easy transition. And we are working towards a full release over the next quarter. There's a lot of work going on to make TensorFlow 2.0 really work well for you. You can track the progress and provide feedback on the TensorFlow GitHub projects page. You asked for better documentation, and we've worked to streamline our docs for APIs, guides, and tutorials. All of this material will be available today on the newly redesigned TensorFlow.org website, where you'll find more examples, documentation, and tools to get started. We're really very excited about these changes and what's to come. And to tell you more about improvements in TensorFlow for research and production, I'd like to welcome Megan Caciolo on stage. Thank you.
Thanks, Rajat. TensorFlow has always been a platform for research to production. We just saw how TensorFlow's high-level APIs make it easy to get started and build your models. Now let's talk about how it improves powerful experimentation for researchers and lets you take models from research and prototyping all the way through to production. Researchers have been using TensorFlow for state-of-the-art research. We can see it in paper publications, which are shown over the past few years in this chart. But powerful experimentation begins and really needs flexibility. This begins with eager execution with TensorFlow. In TensorFlow 2.0, by default, every Python command is immediately executed. This means you can write your code in the style you're used to without having to use session run. This also makes a big difference in the realm of debugging. As you iterate through with eager mode, you'll eventually want to distribute your code onto GPUs, TPUs, and other hardware or accelerators. For this, we've provided tf-function, which turns your eager code into a graph, function by function. You get all of the familiar tools like Python control flow, asserts, even print, but can convert to a graph anytime you need to, including when you're ready to move your model into production. And even with this, you'll continue to get great debugging. Debuggability is great not just in eager, but we've made huge improvements in tf-function and graphs as well. In this example shown here, we're splitting a tensor using tf-function, which creates a graph. But because of the mismatched inputs, you get an error. As you can see, we now give users the information about the file and the line number where the error occurred in the model to help you more quickly track things down so you can continue iterating. We've made the error messages concise, easy to understand, and actionable. We hope you enjoy these changes and they make it much easier for you to quickly iterate and progress with your models. Performance is another area we know that researchers, as well as all users for that matter, care about. And we've continued improving core performance in TensorFlow. Since last year, we've sped up training on 8 NVIDIA Tesla V100s by almost double. Using a Google Cloud TPU v2, we've boosted performance by 1.6x. And with Intel MKL acceleration, we've gotten inference speed up by almost 3 times. Performance will continue to be a big focus of TensorFlow 2.0 and a core part of our progress to final release. TensorFlow also provides flexibility to enable researchers, and this is with many add-on libraries that extend and expand TensorFlow in new and useful ways. Some of these add-on libraries are extensions to make certain problems easier, like tf.text with Unicode and the new ragged tensor type. In other cases, it lets us explore how we can make machine learning models fairer and safer via TF privacy. You'll also hear new announcements on TF agents for reinforcement learning, and tomorrow we'll be discussing the new TF federated library for federated learning. Deep learning research is also being applied to real-world applications using TensorFlow. Here are a few examples from researchers at Google where we see them applying it to areas like our data centers, where we're making them more efficient with AI control system that delivers energy savings. Our apps, like Google Maps, the one shown in the middle, which has a new navigation feature called Global Localization. It combines visual positioning service, street view, and machine learning to more accurately identify position and orientation. And devices like the Google Pixel that use machine learning to improve depth estimation to create better portrait mode photos, like the one shown here. In order to make these real-world applications a reality, you must be able to take models from research and prototyping all the way through to launching in production. This has always been a core strength and focus for TensorFlow. Using TensorFlow, you can deploy your models on a number of platforms, like shown here. And models end up in a lot of places, so we want to make sure TensorFlow works well across all of these, on servers and in cloud, on mobile and other edge devices, in browser and JavaScript platforms. We have products for each of these: TensorFlow Extended, TensorFlow Lite, and TensorFlow.js, which I'll briefly talk through. TensorFlow Extended is our end-to-end platform for managing every stage of the machine learning lifecycle. This spans all the way from ingesting and transforming your data to deploying your machine learning models at scale. In orange, shown here, you can see the libraries we've open sourced so far. What this slide alludes to is that we're now taking a step further and providing components built from these libraries that make up an end-to-end platform. And note, these are the same components that are used internally in thousands of production systems powering Google's most important products. But components are only part of the story. 2019 is the year we're putting it all together and providing you with an integrated end-to-end platform. First, you can bring your own orchestrator. Here, we're showing Airflow or Kubeflow or even raw Kubernetes, whatever you want. No matter what orchestrator you choose, the TensorFlow Extended components integrate with a metadata store. This store keeps track of all the component runs, the artifacts that went into them, and the artifacts that were also produced. This enables advanced features like experimentation and experiment tracking, model comparison, and things along those lines that I'm sure you'll be excited about and will help you as you iterate through and work with your production systems. We have an end-to-end talk coming up later today from Clemens and his team, in which they'll take you on a complete tour of using TensorFlow Extended to solve a real problem. Moving on, TensorFlow Lite is our solution for running models on mobile and IoT hardware. It uses a custom streamlined file format and a stripped-down runtime, so you can deploy TensorFlow models everywhere your users are. On-device models can be more responsive to input than cloud backends, and they keep user data on-device for privacy, which is very important, especially in this day and age. Google and our partners like iQIYI in China use TF Lite for all kinds of tools, including predictive text generation, video segmentation, and things like edge detection. But under the hood, TensorFlow Lite is about performance. You can deploy models to CPU, GPU, and even edge TPUs and expect fast performance. And we've been refining since we launched TensorFlow Lite last year. By using the latest quantization techniques on CPU, adding support for OpenGL 3.1 and Metal on GPUs, and tuning our performance on edge TPUs, we're constantly pushing the limits of what is possible on device. And you should expect even greater enhancements in the year ahead. We'll hear details from Raziel and his colleagues coming up in a little bit this morning. JavaScript is the #1 programming language in the world, and until recently hasn't necessarily benefited from all the machine learning development and tools. Last year, we released TensorFlow.js, a library for training and deploying machine learning models in the browser and on Node.js. Since then, we've seen huge adoption in the JavaScript community with more than 300,000 downloads and 100 contributors. But we're just at the beginning, given how big the JavaScript and web ecosystem is. Today, we're excited to announce TensorFlow.js version 1.0. This comes with many improvements and new features. We have a library of off-the-shelf models for common machine learning problems that run both in the browser and on Node. We're also adding support for more platforms where JavaScript runs, such as Electron desktop apps or mobile native platforms. And a huge focus in TensorFlow.js 1.0 is on performance improvements. As an example, compared to last year, mobile net inference in browser is now 9 times faster. You'll learn more about these advances in our talk later in the day. Another language that we're really excited about is Swift. Swift for TensorFlow is re-examining what it means for performance and usability, with a new stack built on top of TensorFlow's core and a new programming model that intends to bring further usability. And today we're announcing that Swift for TensorFlow is now at version 0.2. It's ready for you to experiment with, to try out, and we're really excited to be bringing this to the community. In addition to telling you about version 0.2, we're also excited to announce that Jeremy Howard of Fast.ai is writing a new course in Swift for TensorFlow. Chris and Brennan will tell you a lot more about this later today. So to recap everything we've shown you so far, TensorFlow has grown to a full ecosystem, from research to production, from server to mobile, with many languages. This growth has been fueled by our community and honestly would not have been possible without the community. To talk about what we're planning for you and with you in 2019, I'll hand it over to Kamal. It's all you.
Thank you, Megan. Hi, my name is Kamal, and I'm the product director for TensorFlow. I'm really excited to be here today for this celebration. And what we're celebrating is the most important part of what we're building, and that's the community. Personally, I love building developer platforms. I used to be a developer as an entrepreneur, and now I get to enable other developers by building together a better platform. When we started working on 2.0, we turned to the community. We started with the request for comment process, consulting with all of you on important product decisions. We received valuable feedback, and we couldn't have built 2.0 without you. And some of you wanted to get more involved, so we created special interest groups, or SIGs, like networking or TensorBoard, to name a few. And SIGs are really a great way for the community to build the pieces of TensorFlow that they care the most about. We also wanted to hear more about what you were building, so we launched the Powered by TensorFlow campaign. And I got to say, we were amazed by the creativity of the project, from biological image analysis to custom wearables to chatbots. So after 3 years, our community is really thriving. There are almost 70 machine learning GDEs right now around the world, 1,800 contributors on core alone, and countless more of you who are doing amazing work to help make TensorFlow successful. So on behalf of the whole TensorFlow team, we want to say a huge thank you. So we have big plans for 2019. And I would like to make a few announcements. First, as our community grows, we welcome people who are new to machine learning. And it's really important to provide them with the best educational material. So we're excited to announce 2 new online courses. One is with deeplearning.ai, and it's published on the Coursera platform, and the other is with Udacity. The first batch of these lessons is available right now, and they provide an awesome introduction to TensorFlow for developers. They require no prior knowledge to machine learning, so I highly encourage you to check them out. Next, if you're a student, for the very first time, you can apply to the Google Summer of Code program and get to work with the TensorFlow engineering team to help build a part of TensorFlow. I also talked about the Powered by TensorFlow campaign. We're so excited with the creativity that we decided to launch a 2.0 hackathon on DevPost to let you share your latest and greatest and win cool prizes. So we're really excited to see what you're going to build. Finally, as our ecosystem grows, we're now having a second day at the summit, but we really wanted to do something more. we wanted a place where you can share what you've been building on TensorFlow. So we're excited to announce TensorFlow World, a week-long conference dedicated to open source collaboration. This conference will be co-presented by O'Reilly Media and TensorFlow, and will be held in Santa Clara end of October. Our vision is to bring together the awesome TensorFlow world and give a place for folks to connect with each other. So I'd like to invite on stage Gina Blaber to say a few words about the conference.
Thank you, Kamal. O'Reilly is a learning company with a focus on technology and business. We have strong ties with the open source community, as many of you know, and we have a history of bringing big ideas to life. That's why we're excited about partnering with TensorFlow to create this new event that brings machine learning and AI to the community. The event is TensorFlow, happening October 28 to 31 in Santa Clara. And when I say community, I mean everyone. We want to bring together the entire TensorFlow community of individuals and teams and enterprises. This is the place where you'll meet experts from around the world, the team that actually creates TensorFlow, and the companies and enterprises that will help you deploy it. We have an open CFP right now on the TensorFlow World site. I invite you all to check that out and send in your proposals soon so your voice is heard at that event. We look forward to seeing you at TensorFlow World in October. Thank you.
Thank you, Gina. This is going to be great. Are you guys excited? Woo! So we have a few calls to action for you. Take a course, submit a talk to TF World, start hacking in 2.0. By the way, the grand prizes for a hackathon on DevPost will include free tickets to TensorFlow World. You know, one thing I love is to hear about these amazing stories of people building awesome stuff on top of TensorFlow. And as a team, we really believe that AI advances faster when people have access to our tools and can then apply them to the problems that they care about in ways that we never really dreamed of. And when people can really do that, some special things happen. And I'd like to share with you something really special.
Consultare documenti storici, soprattutto documenti medievali, richiede sempre molto tempo, molta pazienza. In Archivio Vaticano abbiamo 85 km lineari di documenti, più o meno la lunghezza del Canale di Panama. Le scritture scritte nel Medioevo sono diverse da quelle che noi conosciamo. Se qualcuno mi chiedesse un giorno di trascrivere e tradurre tutti i documenti dell'Archivio Vaticano, sicuramente gli direi che è un matto.
Looking at this book, page by page, and trying to decipher, read and transcribe whatever is there takes an enormous amount of time. You would require an army of paleographers.
What I'm excited the most about machine learning is that it enabled us to solve problems that up to 10-15 years ago we thought unsolvable.
In Codice Razzi è nato da quest'idea di costruire un software per poter interpretare, per poter leggere quello che è scritto dentro i manoscritti. Quando abbiamo iniziato ad approcciare il problema ci siamo resi conto che una soluzione basata su reti neurali fosse assolutamente necessaria. La scelta su TensorFlow è stata abbastanza naturale.
Before using any kind of machine learning model, we needed to collect data first. You have thousands of images of dogs and cats in the internet, but there is very little images of ancient manuscripts. We built our own custom web application for crowdsourcing, and we involved high school students to collect the data. I didn't know much about machine learning in general, but I found it very easy to create a TensorFlow environment. When we were trying to figure out which model worked best for us, Keras was the best solution. The production model runs on TensorFlow layers and estimator interface. We experimented with binary classification with fully connected networks, and finally we moved to convolutional neural network and multi-class classification.
In poco tempo siamo riusciti a sviluppare e a testare le prime soluzioni.
When it comes to recognizing single characters, we can get 95% average accuracy.
Poter accedere a uno strumento informatico abbrevia notevolmente. Sciogliere certe abbreviazioni, comprendere un testo in quella scrittura così criptica è un qualcosa di eccezionale.
This will have an enormous impact. In a short period of time, we will have a massive quantity of historical information available.
I just think solving problems is fun. It's a game against myself and how good I can do.
Lo studio della storia è importantissimo per comprendere il nostro presente e per avere anche una prospettiva per il futuro.
This is such a great story. I think about the scholars who wrote these manuscripts. Could you imagine? They could have imagined that centuries later, people would be using computers to bring back to life their work. So we're really lucky to have Elena with us today. Elena, would you stand? Don't miss the talk where she will share her story today. I really hope you have a great day. We have some really awesome things. The team and I will be around. Please come and say hi. We want to hear from you. And with that, I'm going to hand it over to Martin, who will talk about TensorFlow 2.0. Thank you.
Thank you, Kamal. I'm Martin Wicke. I'm the engineer lead for TensorFlow 2, and I'm going to, unsurprisingly, talk about TensorFlow 2. TensorFlow has been extremely successful, and inside of Google, outside of Google, it has grown into a vibrant community that really, when we started it, we were not able to imagine. And our users are building these ingenious, clever, elegant things every day, from art and music, from what you just heard about medieval manuscripts, science, and medicine. And the things people created were unexpected and beautiful, and we learned a lot from that. And we learned a lot from how people did it. And TensorFlow has enabled all this creativity and really jump-started this whole AI democratization, which is great. But it's also, it has been a little bit hard to use sometimes, and we know. It's sometimes a little bit painful. So using sessions wasn't maybe the most natural thing to do when you're coming from regular Python. And the TensorFlow API has grown over time and got a little bit cluttered, a little bit confusing. In the end, you can do everything with TensorFlow, but it wasn't maybe always clear what's the best way to do it with TensorFlow. And so we've learned a lot since we started this. And we realized that you need rapid prototyping, you need easier debugging. There's a lot of clutter. So we're fixing this. We're addressing these issues with a new version of TensorFlow. Today, we're releasing an alpha of TensorFlow 2. Many of you have participated in the design reviews that went into this for all the features that we have implemented. Those of you who are really living on the bleeding edge of development have probably played with it nightly. You have installed it, you have tested it, you have found issues, you have fixed issues. So thank you very much for your help. You can now install the alpha release of TensorFlow 2 using just pip install pre-TensorFlow. And you can go and play with it. So what has changed? When we created TensorFlow 2, really the biggest focus is on usability. We've adopted Keras as the high-level API for TensorFlow. We've integrated it very deeply with TensorFlow. Keras gives you a clear path of how to develop models, how to deploy models. It has a well-established API that makes people productive, and we know that it gets you started quickly. TensorFlow also includes a complete implementation of Keras, of course, but we went further. We have extended Keras so that you can use all of the advanced features in TensorFlow directly from tf.keras. The other big change in TensorFlow 2 is that it is eager execution by default. Traditional 1.x TensorFlow used a declarative style, and that was often a little bit dissonant with the surrounding Python. And in TensorFlow 2, TensorFlow behaves just like the surrounding code. So if you add up two numbers, you get a result back immediately, which is amazing, really. So, but you still get all the benefits of working with a graph. Robust program serialization, easy distribution of programs, distributed computation, optimizations on the graph. All of that stuff is not going away. It's just getting easier. So TensorFlow 2 is a major release. which means that we have the ability to clean it up, and we did, like a lot. So we had a lot of duplicate functionality that we have removed. We've consolidated the API, we've reorganized the API, we've made sure that the API looks and feels consistent. And this is not only about TensorFlow itself. This is about the whole ecosystem of tools that has grown around TensorFlow. We've spent a lot of effort to try and align all of these interfaces, and we've defined exchange formats that allow you to move all throughout this ecosystem without hitting any barriers. We have removed a lot of stuff from TensorFlow, but it doesn't mean that it's not. It means that it has gotten more flexible, not less. It retains and expands on the flexibility it had that enabled all of this development. We've created a more complete low-level API that now exposes all of the internally used ops to the users via the raw ops module. We provide inheritable interfaces for crucial concepts, all of the crucial concepts in TensorFlow, like variables and checkpoints. And this allows framework authors to build on top of TensorFlow while maintaining interoperability with the rest of the ecosystem. You hear a lot of these examples later. There'll be a talk about TF agents later today. There'll be a talk about Sonnet by DeepMind tomorrow. So you'll see examples of how this works in practice. Now, the real question for you is, of course, what do I have to do to be a part of this great new era of TensorFlow? And we know it's always hard to upgrade to anything, and it's especially true for major version upgrades. At Google, we will now start the process of converting one of the largest code bases in the world to TensorFlow 2. And while we're doing that, we'll be writing a lot of migration guides. We have started that already, and some of them are online. And we'll provide a lot of best practices for you. And if you can do it, if we can do it at Google, you can probably do it too. So we're giving you and us a lot of tools to make this transition easier. First of all, as part of TensorFlow 2, we're shipping a compatibility module we call TF-Compat v1, which contains all of the 1.x API. So if you rely on a specific deprecated function, you can still use it. You can still find it there, except for TF-Contrib, which is not going to be included at all. But we've created community-supported alternatives that support your use case if you rely on something in there. We're also publishing a script which will automatically update your code so it runs on TensorFlow 2. So let me show you how that works. So let's say I want to convert this program, which is an example that we have online, a simple language model trained on Shakespeare. So what I do is I simply run tf-upgrade v2, which is a utility that's included with any installation of TensorFlow 2. It tells me what it did, and in this case, there's really just a handful of things that it changed. And you can see, if you look at what it changed, there's some functions that it renamed. A lot of the reorganization of the API leads to renamed functions. So multinomial was actually the wrong name for this function. So renamed it to random categorical. That's something the script will do for you, so you don't have to worry too much about it. A lot of functions had arguments renamed, their order changed, or some arguments added or deleted. As far as possible, the script will make those changes for you. And then, if all else fails, sometimes there isn't really a perfect equivalent in TensorFlow 2 to a symbol that exists in TensorFlow 1, and then we'll use the compatibility module that I talked about earlier. If there's no perfect replacement, we'll use that in order to make sure that your code still works as expected after the conversion. So it's pretty conservative. So for instance, the Atom Optimizer is a very subtle behavior change that mostly probably won't affect you, but just in case it might, we will convert it to Compat v1 Atom Optimizer. Once the conversion is complete and there were no errors, then you can run the new program against TensorFlow 2 and it'll work. So that's the idea. So it should be pretty easy for you. Hopefully you won't get trouble. Note that this automatic conversion, it'll fix it so it works, but it won't fix your style to the new TensorFlow 2 style. That cannot be done automatically, and there's a lot to learn about this process. So if you want to know more, check out the talk by Anna and Tomer tomorrow at 10:30 about 2.0 and porting your models. That'll be worthwhile. Of course, as we do go through this process at Google, we'll also publish a lot more documentation, but this talk is the best start. All right, so let me give you an idea about the timeline of all of this. We have cut 2.0 alpha today, or yesterday, took some time building it. We're now working on implementing some missing features that we already know about. We're converting libraries, we're converting Google. There's lots of testing, lots of optimization that's going to happen over the next couple of months. We're targeting to have a release candidate in spring. Spring is sort of a flexible concept, you know. But in spring, after we have this release candidate, it still has to go through release testing and integration testing. So I expect that to take a little bit longer than for our regular release trains, but you know, that's when you can see an RC and then eventually final. So if you want to follow along with the process, please do so. All of this is tracked online. It's all on the GitHub TensorFlow 2 project tracker. So I would just go and look at that to stay up to date. If you're looking for a particular feature, just want to know what's going on. If you file any bugs, those end up there as well, so everybody knows what's going on. So TensorFlow 2 really wouldn't be possible without you. That has been the case already, but in the future even more so. We'll need you to test this. We'll need you to tell us what works and what doesn't. So please install the alpha today. We're extremely excited to see what you can create with this. So please go, install the alpha, check out the docs. They're at tensorflow.org/r 2.0. And with that, I think you should probably hear about what it's like to be working with TensorFlow 2. We'll have plenty of content over the next couple of days to tell you exactly about all the different aspects of it. But we'll start with Carmel, who will speak about high-level APIs in TensorFlow 2.0. Thank you.
Hi, my name is Carmel Allison, and I'm an engineering manager for TensorFlow. Martin just told you about TensorFlow 2.0 and how to get there, and I'm going to tell you a little bit about what we're bringing in our high-level APIs and what you can expect to find when you arrive. But first, what do I mean when I say high-level APIs? There are many common pieces and routines in building machine learning models, just like building houses. And with our high-level APIs, we bring you tools to help you more easily and reproducibly build your models and scale them. As Martin mentioned a couple years ago, TensorFlow adopted Keras as one of the high-level APIs we offered. Keras is, at its heart, a specification for model building. It works with multiple machine learning frameworks, and it provides a shared language for defining layers, models, losses, optimizers, and so on. We implemented a version of Keras that has been optimized for TensorFlow inside of core TensorFlow, and we called it TF Keras, one of our high-level APIs. Raise your hand if you've used TF Keras already. OK, a lot of you. That's good, because this next slide will seem familiar. In its simplest form, Keras is just that, simple. It was built from the ground up to be Pythonic and easy to learn, and as such, it has been instrumental in inviting people into the machine learning world. The code here represents an entire model definition and training loop, meaning it's really easy for you to design and modify your model architectures without needing to write tons of boilerplate. At the same time, by relying on inheritance and interfaces, Keras is extremely flexible and customizable, which is critical for machine learning applications. Here we have a subclass model. I can define arbitrary model architectures, modify what happens at each training step, and even change the whole training loop if I want to. Which is to say, Keras is simple and effective. Anyone can figure out how to use it. But we had a problem. TF Keras was built for smaller models, and many machine learning problems, including the ones we see internally at Google, need to operate at a much larger scale. And so we have estimators. Estimators were built from the ground up to distribute and scale with fault tolerance across hundreds of machines, no questions asked. This here is the much-loved wide and deep model, a workhorse of the machine learning world that took many years of research to define, but is available as a built-in for training and deployment. Which is to say, estimators are powerful machines. But you've told us that there's a steep learning curve, and it's not always easy to figure out which parts to connect where. And we've learned a lot in the past 2 years building out Estimator and TF Keras. And we've reached the point that we don't think you should have to choose between a simple API and a scalable API. We want a higher level API that takes you all the way from MNIST to planet scale, no questions asked. So, in TensorFlow 2.0, We are standardizing on the Keras API for building layers and models, but we are bringing all the power of estimators into TF Keras so that you can move from prototype to distributed training to production serving in one go. Oops. Okay, so brass tacks. How are we doing this? Well, this is a TF Keras model definition in TensorFlow 113. And this is the same model definition in 2.0. Some of you may notice the code is exactly the same. Okay, so what actually is different? Well, we've done a lot of work to integrate Keras with all of the other features that TensorFlow 2.0 brings to the table. For example, in 113, this built a graph-based model that ran a session under the hood. In 2.0, the same model definition will run in eager mode without any modification. This lets you take advantage of everything eager can do for us. Here, we see that our dataset pipeline behaves just like a NumPy array, easy to debug and flows natively into our Keras model. But at the same time, datasets have been optimized for performance so that you can iterate over and train with a dataset with minimal performance overhead. We're able to achieve this performance with datasets and Keras by taking advantage of graphs even in an eager context. Eager makes debugging and prototyping easy, and all the while, Keras builds an eager-friendly function under the hood that tracks your model, and the TensorFlow runtime then takes care of optimizing for performance and scaling. That said, you can also explicitly run your model step-by-step in eager mode with the flag run eagerly. Even though for this example it might be overkill, you can see that run eagerly allows you to use Python control flow and eager mode for debugging while you're prototyping your model. Another big change coming in 2.0 is that we have consolidated many APIs across TensorFlow under the Keras heading, reducing duplicative classes and making it easier to know what you should use and when. We now have one set of optimizers. These optimizers work across TensorFlow, in and out of eager mode, on one machine or distributed. You can retrieve and set hyperparameters like normal Python attributes, and these optimizers are fully serializable. The weights and configuration can be saved both in the TensorFlow checkpoint format and the backend agnostic Keras format. We have one set of metrics that encompasses all the former TF metrics and Keras metrics and allow for easy subclassing if you want even more. Losses, similarly, have been consolidated into a single set with a number of frequently used built-ins and an easily customizable interface if you so choose. And we have one set of layers, built in the style of Keras layers, which means that they are class-based and fully configurable. There are a great number of built-in layers, including all of the ones that come with the Keras API specification. One set of layers that we took particular care with were the RNN layers in TensorFlow. Raise your hand if you've used RNN layers in TensorFlow. Okay, these slides are for you. In TensorFlow v1, we had several different versions of LSTMs and GRUs, and you had to know ahead of time what device you were optimizing for in order to get peak performance with cuDNN kernels. In 2.0, there is one version of the LSTM layer and one version of the GRU layer, and they select the right operation for the available device at runtime so that you don't have to. This code here runs the cuDNN kernel if you have GPUs available, but also falls back to CPU ops if you don't have GPUs available. In addition to all of those, if you need layers that are not included in the built-in set, TF Keras provides an API that is easy to subclass and customize so that you can innovate on top of the existing layers. This, in fact, is how the community repository TensorFlow add-ons operates. They provide specialized and particularly complex layers, metrics, optimizers, and so on, to the TensorFlow community by building on top of the Keras base classes. All right, so we streamlined APIs. That's a start. The next thing we did was integrate Keras across all of the tools and capabilities that TensorFlow has. One of the tools we found critical to the development of estimators was easily configurable structured data parsing with feature columns. In TensorFlow 2.0, you can use feature columns to parse your data and feed it directly into downstream Keras layers. These feature columns work both with Keras and estimators, so you can mix and match to create reusable data input pipelines. Okay, so you have data in your model, and you're ready to train. One of the most loved tools we have for you running your training jobs is TensorBoard. And I'm pleased to say that in TensorFlow 2.0, TensorBoard integration with Keras is as simple as one line. Here we add the TensorBoard callback to our model when training, and This gets us both our training progress, here we see accuracy and loss, and a conceptual graph representing the model we built layer by layer. As an added bonus, this same callback even includes full profiling of your model, so you can better understand your model's performance and device placement, and you can more readily find ways to minimize bottlenecks. Speaking of performance, one of the exciting pieces we're bringing to TensorFlow 2.0 is the TF Distribute Strategy API. In TensorFlow 2.0, we will have a set of built-in strategies for distributing your training workflows that work natively with Keras. These APIs have been designed to be easy to use, to have great out-of-the-box performance, and to be versatile enough to handle many different distribution architectures and devices. So how do they work? Well, with Keras, you can add and switch distribution strategies with only a few lines of code. Here, we are distributing the same model you just saw across multiple GPUs by defining the model network, compiling, and fitting within the distribution strategy scope. Because we've integrated distribution strategies throughout Keras and TensorFlow, you get a lot with these few lines of code. Data will be prefetched to GPUs batch by batch. Variables will be mirrored in sync across all available devices using AllReduce. And we see greater than 90% scaling efficiency over multiple GPUs. This means you can scale your model up without changing code and without losing any of the conveniences of Keras. Once you've trained your model, you're likely going to want to package it for use with production systems, mobile phones, or other programming languages. Keras models can now export directly to saved model, the serialization format that works across the TensorFlow ecosystem. This functionality is experimental while we iron out a few API details, but today and going into 2.0, you can easily export your models for use with TF Serving, TF Lite, and more. You can also easily reload these models back into Python to continue training and using in your normal workflow. So that's where we are today in the alpha, but we're obviously not done yet. So let me tell you a little bit about what's coming up in the next few months. We talked about distributing over multi-GPU, but that's just the start. Using the same model code, we can swap out our strategy and scale up to multiple nodes. Here, we take the same Keras model we just saw and distribute it across multiple machines, all working in sync using collective ops to train your model faster than ever before. Multi-worker mirrored strategy currently supports Ring and Nickel for AllReduce, which allows us to achieve great out-of-the-box performance. This API is still being developed, but you can try it out today in the nightlies if you are interested in a TensorFlow native solution to synchronous multi-worker training. And we are very excited to say that using Keras and distribute strategies, you will also be able to use the same code to distribute your model on TPUs. You'll have to wait for the next TensorFlow release for this to actually work on TPUs, but when it's released, this strategy will still work on Google Cloud TPUs and with Colab, which can now access TPUs directly. And as we approach the final 2.0 release, we will continue bringing scalability into Keras. We will be enabling distribution with parameter server strategy, which is the multi-node asynchronous training that Estimator does today. We will also be exposing canned estimators like Wide and Deep directly from the Keras API for those of you who want a higher level API. And we will be adding support for partitioned variables across many machines for some of the largest scale models like those we run at Google. And that's just a sneak peek. So please do check out the 2.0 preview and try out TF Keras if you haven't already. If you have more questions, you'll be hearing more throughout the day about Keras and high-level APIs and how they integrate across TensorFlow. And we also have a workshop tomorrow that Martin mentioned. Thanks, and with that, let me introduce Raziel, who will tell you more about TF Lite.
Thanks, Carmel. Hi, everyone. My name is Raziel. I'm an engineering lead in TensorFlow Lite. And today I will be covering a lot of the work that the team has done over the past year to bring you features that you can take advantage of right away. And hopefully you are already doing that. I will also cover a lot of the work that we have for this year. But before we jump into that, let me give you a brief introduction of what TensorFlow Lite is. So TensorFlow Lite is our infrastructure framework to run machine learning on device. And the reason why we decided to build TensorFlow Lite was because machine learning, you typically think of it as running on the server, right? But more and more is moving to edge devices, like mobile devices, cars, wearables, you name it. So there is more machine learning moving to different kinds of devices. And there is good reasons for that. one, you have access to a lot more data because you have access to the audio, to the camera, and you don't have to stream it all the way to the server. So you can do a lot of stuff. You can do sensor fusion, and that means that you can build faster and close-knit interactions. Another advantage of running machine learning on device is that it has a strong privacy-preserving component, right? Because the data stays on device, it doesn't necessarily have to go to the server. However, well, that means that basically by building machine learning on device, by allowing that, we can build products that otherwise wouldn't be able really to work if you really rely only on server-side execution. However, you know, it is hard. Perhaps one obvious thing is that you don't have the same compute power that you have on the server, right? So if you have a new, very cool, shiny machine learning model, but it consumes too much compute power, it's not like in the server that you can, you know, throw perhaps more servers at it and be done with it. You have to be mindful of the resources that you have in the device. Another of those resources is the memory. So you have restricted memory, so you have to be careful about how you craft your model, perhaps try some compression techniques. And last but not least, many of these devices are battery powered, right? So even if you have a model that fits in memory that can execute, well, you don't want to consume all the battery in a battery powered device. So for all these reasons, that's what we built TensorFlow Lite. We want to make deploying machine learning on edge devices as easily as possible. And what can you do with it right now? Well, you can do a lot of things. These are different tasks that are supported by TensorFlow Lite already. And if you look at it, when you hear machine learning, you typically fall into one of these tasks. You know, text, speech, image processing, audio processing, a lot of content generation. So really, like everything is already there for you to take advantage of. And because we already are able to support all these tasks, it means that it has a lot of usage already. So TensorFlow Lite is currently deployed in over 2 billion devices in production. And this not only means Google properties, and some of which are really core to Google, like the Assistant, Google Photos, but also from other companies, from other large companies, and also frameworks. So a lot of infrastructure is powering frameworks like AutoML and MLKit. And I can tell you many reasons why it's a good idea to use our infrastructure, but we thought that it would be best if we bring two of our important clients to tell you how they use TensorFlow Lite and why they decided to use it. Our first presenter is Alex. He's coming from the Google Assistant, and the Google Assistant, I mean, it has a wide variety of devices where it's running. So let's hear from here why they are using TensorFlow Lite and how they're doing it.
Thanks, Raziel. So I'm Alex. I'm the engineering lead on our embedded speech recognition team at Google. So one of the key applications for speech recognition at Google is the Google Assistant. Google recently announced that the Google Assistant is on about 1 billion devices, ranging from phones, speakers, smart displays, cars, TVs, laptops, wearables. You name it, we're trying to put the Assistant into it. From my perspective, that means a wide range of devices. High-end devices, low-end devices, ARM, x86, battery-powered, plugged in, a wide range of operating systems. So basically, the neural nets that I build have to be able to run anywhere. For Assistant, we have a couple of key speech on-device capabilities. The first is the hot word. You need to be able to say, hey, Google, to trigger your device. We need to both detect that hot word, and we need to recognize that it's your voice and not somebody else trying to activate your phone. This means, because this is running all the time, we have to have a tiny memory and computation footprint running continuously, and we're extremely latency sensitive. As soon as you say the hot word, we need to immediately trigger. Our other major application is on-device speech recognition. We use this often when you're offline or you have a bad network connection. So instead of using the server, we actually run speech recognition on the device. Now, this is kind of on the other end of the spectrum. Here, we're trying to run large models as fast as possible to get the best possible accuracy. So it's a high computational load, typically running in a short burst. Over the years, we've been working on this for a long time. Before there was TensorFlow Lite, before there was TensorFlow. So we've been investing a lot for a long time in building our own on-device neural net libraries and shipping them to production in Google products for a long time. As a team, we've already invested significantly in keeping our code size tiny, our memory usage small, optimizing our compute for all of these different platforms. And all of our code, after many years of production use, is really hardened and hopefully as bug-free as you can get it. But over the last year, we decided to migrate to TF Lite. Now, this wasn't an easy decision for us because our libraries are already so well optimized. And as we switched over, we checked very carefully to make sure that TF Lite would meet or beat our existing libraries in terms of their size and speed. And I'm happy to report that over the last year, we've migrated all of the computation we do on CPU for our models to TF Lite. Now, we're excited about this because this really lays the groundwork for us, moving to a new standard that's being widely adopted. And we think TF Lite will help us accelerate our models on things like GPUs and edge TPUs, all the new kinds of accelerators that are coming. So thanks. I'll turn it back over to Raziel.
Thanks, Alex. So Alex highlights two key goals for TensorFlow Lite. So we want to be able to support your current use cases, but perhaps equally important or more important is we want to cater to your needs that you will have 1-2 years in the future. So our next presenter is Hugh Ji from NetEase. NetEase is a China-based company that has several applications and hundreds of millions of users. So let's welcome him.
Thanks, Reza. I'm Huijie Lin from NetEase Youdao. And in Youdao, we are the first leading company in the online education, as well as we have built a lot of dictionary translation and note-taking applications in China. We have over 800 million users in total, and we also have 22 million daily active users. In the past years, we have built several dictionary translation and note-taking applications. For example, we have the most popular dictionary application in China, which is Youdao Dictionary. And we also have the most popular translation application in China, which is Youdao Translator. And we also have the most popular dictionary and language learning application in India, which is YouDictionary. And in these applications, we provide some features for users to conveniently look up words in the scenarios, such as, for example, you can use your camera to recognize the words from the images and do the OCR and translation on your devices. So we use the TensorFlow Lite to accelerate the OCR and translation here. And also, we have provided the photo translation in our applications. For example, you can use the camera to take a photo from the many scenarios, and it will do the whole image OCR and translate the text into another language. And then it will erase the text on the image and replace the original text to the translated text, and then to present users with the translations. And in this scenario, we also use the TensorFlow Lite to accelerate our OCR and translation services here. As we all know that the OCR and translation, it is very sensitive to the binary size and also computation resources and the responding time. So we choose the TensorFlow Lite to accelerate our abilities on device to provide the more efficient on-device inference here. So that's why we choose the TensorFlow to do this. Thanks.
Thanks, Guille. It's really exciting to see how our infrastructure is used by hundreds of millions of users around the world. And this is something that I wanted to highlight. Just like the rest of TensorFlow, TensorFlow Lite is geared to not only towards Google, but towards everybody out there. Like everybody should be able to take advantage of it. OK, so for the rest of the presentation, I will cover what I said at the start, a lot of the features that have been made available over the past year, and some of our roadmap for this year. In the project, we organize our engineering in 4 main themes. The first one is usability. Overall, it means we want to be able to get you up and running as easily and fast as possible. Now, once you have your model, basically, we want to get you executing that model as fast as possible in the hardware that you care about. Then with optimization, we look at perhaps certain things that we can do to your model to make it even faster and smaller. And finally, with our documentation efforts, we want to give you all the resources that you need so you can get the most out of our infrastructure. So let's start with usability. There is different ways of getting up and running in TensorFlow Lite. But at the end of the day, you most likely will end up wanting at some point train a model in TensorFlow and convert it to TensorFlow Lite. The flow is logically very simple, right? You train in TensorFlow, you get a safe model, then you use a TensorFlow Lite converter, and then you get a TensorFlow Lite model that you can now execute on different kinds of devices. However, there is some points of failure. TensorFlow Lite, we made the decision to take a subset of TensorFlow ops and optimize those. But that means that basically we don't have all the same hundreds of operations that TensorFlow has. The other reason is some semantics we don't support yet on TensorFlow Lite, like control flow, which is typically used for recurrent neural networks. But we've made already strides trying to basically make this easier and better for you. So last year we launched TensorFlow Select, and this basically means that you can execute TensorFlow ops in TensorFlow Lite. In the pipeline, we're making improvements to TensorFlow Select by enabling selective registration, and I will explain what all this means in the following slides. And we're also working on adding control flow support. OK, so Select, like I said, it means that you can execute TensorFlow ops on TensorFlow Lite. It comes at the cost of some binary size increase, because right now it's basically all or nothing. But that's why we're building selective registration. Selective registration is already something that you can take advantage on TensorFlow Lite for our built-in ops. So you only include in the binary the ops that you are really using, so you don't end up increasing your binary size unnecessarily. So we're bringing that to TensorFlow Select. And we are also trying to blur the line of what the TensorFlow ops and the TensorFlow Lite ops are. And one of the key points of this is blur the performance gap that there might be between one and the other. Now, control flow, again, it's something that we are working on. And this is one of the probably larger pain points where you are trying to convert recurrent neural network to TensorFlow Lite. So this is something that is in progress. So we are adding support for loops and conditionals. And all this is a part of a bigger effort to basically revamp entirely our converter. And we took your feedback very seriously. And we want this converter to answer these 3 questions, right? If something fails, what went wrong, right? Where it went wrong, and what can you do to fix it? OK, so jumping to the next theme is performance. We want your models to execute as fast as possible in the hardware that you have available. And if you saw in Megan's slide, we've made huge strides in this area, right? So this is an example of a mobile NetV1. The execution in CPU, floating point compared to the quantized version in CPU. And now with the recently developer preview that we launched for a GPU delegate, we get huge gains, right? Like over 7x improvements. And then by using the HTPU delegate, we get crazy speedups, right? 62x. So again, this is an area that we're working really hard. Again, some things that are already available. We have a very nice benchmark and profiling tool, and we have a few delegates. For those of you who are not familiar with the concept of TensorFlow-like delegates, basically it's our abstraction layer that allows executing models beyond the CPU, right? So right now we have these three delegates like HDPU, GPU, and the neural network API delegate. And in the pipeline, we are working also on CPU improvements because we know that CPU is important. I'm not listing here in the pipeline anything around newer delegates because it tends to be a partnership with other companies, and I don't have anything to announce yet, but we're working on that. Okay, our benchmarking tool is basically a profiler. We added some features to it. It supports multi-threading. You can see statistics per op execution, and it supports the neural network API. So when you execute the profiler, you get a lot of information. This is just a snippet of all the stuff that you get. So in this case, we're showing you here information per each one of the ops in your graph, how long it took to execute. Then you also get a nice summary of all the op types in your graph and many useful statistics. So you can decide maybe there is a way that you can change one op for other type that is more efficient or tweak your graph in some way. Okay, now let's talk about the delegate. So like I said, a delegate is our abstraction layer for executing graphs in different hardware. And the way it works is very nice because basically in the TensorFlow Lite, you prepare a model, right? You are not necessarily saying this model is for this hardware. You just prepare your model. And then the interpreter will take it, and then for those delegates that you register, it will go each one by one, and then we'll say, okay, how much of this graph can you execute, right? And what the delegate cannot execute, it will be executed in CPU. So by doing this, basically, you will always be able to execute, right? And if anything, you will get better performance if the delegate can consume more of your graph. So we have already an HDPU delegate. HDPUs are Google's ML hardware accelerator for the edge. It's very high performance. It's also very small and has a small power footprint. And later on, we'll have more information about the HDPUs and a very cool demo. The next delegate is the GPU delegate. This is a developer preview right now. And we see very nice performance improvements, right? 2 to 7x compared to floating point in CPU at the cost of a relatively small binary size increase. And how do you enable the GPU delegate? Well, just like any other delegate, this is an example of the interpreter and just executing one inference. And the only thing that you need to do to enable, in this case, the GPU delegate, well, you just instantiate it and pass it to the interpreter. And that's it. So stuff that we're working on for the GPU delegate, well, we want to add more ops. Right now, most of the ops in the GPU delegate are covering convolutional networks, but obviously we want to cover recurrent networks, for example. We want to improve performance even further, and we want to finalize the API, so this is generally available, not just a developer preview. The final delegate that I wanted to mention is the Android Neural Network API, right? So this will allow you to execute any other hardware that the Android NN API supports. So it should be just transparent for you. Finally, CPU is still very important for many use cases, right? Like most devices have some form of a CPU. So we are targeting further improvements on ARM and x86 architectures. Okay, so the next theme is optimization. So in the performance thing, we took a model and we coded it in a way that can execute very fast, right? But maybe we can do tweaks to your model to make it even faster or even smaller. So we already did some work here. So last year, we released this post-training quantization tool that it gives very nice performance improvements on CPU. And this is the first launch that we have in what we are calling Model Optimization Toolkit. So more techniques will be part of this toolkit and available for use for everybody. And in the pipeline, some of these new techniques that we're going to put in the toolkit is more quantization work. In this case is what we call fixed point quantization, which gives you further improvements on CPU and allows you to execute in more hardware, because a lot of the specialized hardware, like neural processing units, are just fixed point based. There is no floating point support. We're also excited because we're working on a new technique called connection pruning, and I will cover a little bit of all these things next. So quantization, right, like means just changing the precision of your model and how it's executed on the device. We launch a post-training quantization tool where basically you take your saved model, and when you convert it to TensorFlow Lite format, you can just turn on a flag, and it will be quantized. And because it's on CPU, basically we can do a mix of fixed point and floating point math to try to get the most performance and relatively small accuracy loss. And we see very nice improvements this way. If the model gets fully quantized, then you get 4x compression. And for convolutional models, we see 10 to 50% performance improvement. But for fully connected and RNNs, we see up to 3x. So again, this is something that is extremely simple to try, right? Like if you already are using TensorFlow Lite or plan to use it, just give this a try. Obviously, you have to validate how the accuracy is affected in your particular model, but so far we've seen very good numbers. And many of the 2 billion devices that we mentioned before are running this way. In the pipeline, again, we're making further improvements in the quantization approaches that we have. So we're working on this fixed point quantization. And we want to make it both powerful by enabling quantized training and also very easy to use. And that's why we're also bringing more post-training quantization support. So this is an example of a Keras model, right? It's very easy. You have used 2 dense layers. And now let's say that you want to train with quantization those 2 dense layers. Well, soon enough, you will be able to just import our API and just say quantize those 2 dense layers. And the post-training quantization will work just like for fixed point will work very much like the one that we already support, where you have the conversion path, and the only thing that you need to pass extra is some calibration data. And calibration data is just the typical data that your model sees as the input. So for example, if you have an input, an image processing model, you just need to pass some images. And you don't really need to pass a ton of images. So in preliminary numbers, for example, for mobile nets, we see with 25 images, we do very well. These are some of the numbers, again, preliminary numbers that we see with this tool. We have the float baseline, right? And then if you do quantized training, then you get almost the same accuracy with all the benefits of quantization, of compression and fast execution. And then even further, if you really, for some reason you don't want to invest in quantized training, or perhaps you just have a model, that you got somewhere, you can still quantize it with post-training quantization, and you see there that basically the accuracy is almost the same. The other technique that we are heavily investing right now is connection pruning. What this means is that at training time, we just prune connections in the network. The prune connections become zeros, and that creates just a sparse tensor. The nice benefits of a sparse tensors is that you can compress them because you can skip the zeros, and you can create potentially faster models if you have like less computations to do. So coming very soon, we're going to add a training time pruning, again, as a Keras-based API. And in the pipeline, we're working on first-class support of sparse execution and TensorFlow Lite. So again, in our example from Keras, is you have your 2 dense layers. You want to prune connections from those 2 layers. And then the only thing that you need to do is just say prune. So it's very, very simple. At that point, when you convert the model to TensorFlow Lite format, basically by just even zipping the file, you will get the nice compressions. And these are some, again, very preliminary numbers. In this case, a mobile net, which actually is pretty hard to prune compared to other, perhaps larger models, but we see very small losses at 50% and even 75%. Finally, documentation. Well, again, we want to give you all the resources that you need to get the most out of TensorFlow Lite. And we have already done pretty nice improvements. We have a new site, right, that is not only just pretty, but it has more content. We currently have a model repository with 5 models and applications that you can try. But we want to work, and we are working on more tutorials, and we're also trying to expand our repository. So this is how the new site looks, if you haven't taken a look. The goal is, again, not only that it's pretty, but that it answers your questions. So please give us some more feedback if there is things that are still lacking there. Yeah, so we revamp our documentation, and very important, we also have there the roadmap for the foreseeable future. So a lot of the stuff that I'm talking about now, you can see it there in more detail, perhaps. And then again, we have a repository with all these applications and tutorials, and we are expanding it. We want to make the repository into something that, if you don't want to go, or before you start trying to train something, perhaps we already have a model that you can reuse. By the way, yeah, TensorFlow Mobile is deprecated, right? Especially with the work that we did to bring TensorFlow Select, which allows you to execute TensorFlow ops in TensorFlow Lite. There is no need for TensorFlow Mobile, except if you are doing training on device. So that is the reason why we're keeping that there. But yeah, training. So if you see, we're building a lot of the basic infrastructure that you will need when you are trying to prepare a training pipeline to execute on device. I don't have anything to announce now, but I just wanted to let you know that we're working on it and thinking a lot about it. What about TensorFlow 2.0? Well, it just should work. If you have a safe model, you should be able to convert it to TensorFlow Lite. And before we go, 2 last things. One is there was a lot of content in this talk. Tomorrow we have some breakout sessions where we're going to cover TensorFlow Lite in general, and optimization in particular. And also I want to introduce Pete Warden, who is going to talk about some very cool project.
Awesome. So thanks so much, Raziel. And I'm really excited to be here to talk about a new project that I think is pretty cool. So TensorFlow Lite for microcontrollers, what's that all about? So this all comes back to when I actually first joined Google back in 2014. And as you can imagine, there were a whole bunch of internal projects that I didn't actually know about as a member of the public that sort of blew my mind. But one in particular came about when I actually spoke to Raziel for the first time. And he explained, and he was on the speech team at the time working with Alex, who you just saw. And he explained that they used neural network models that were only 13 kilobytes in size. At that time, I only really had experience with image networks, and the very smallest of them was still like multiple megabytes. So this idea of having a 13 kilobyte model was just amazing for me. And what amazed me even more was when he told me why these models had to be so small. They were running them, they needed to run them on these DSPs and other embedded chips in smartphones, so Android could listen out for wake words like, "Hey Google," while the main CPU was powered off to save the battery. These microcontrollers often only had tens of kilobytes of RAM and flash storage, so they simply couldn't fit anything larger. They also couldn't rely on cloud connectivity because the amount of power that would have been drained just keeping a radio connection alive to send data over would have just been prohibitive. So that really struck me, that conversation and the continued work that we did with the speech team, because they had so much experience doing all sorts of different approaches with speech. They'd spent a lot of time and a lot of energy experimenting. And even within the tough constraints of these embedded devices, neural networks were better than any of the traditional methods they used. So I was left wondering if they'd be really useful for other embedded sensor applications as well. And it left me really wanting to see if we could actually build support for these kind of devices into TensorFlow itself, so that more people could actually get access to it. At the time, only people in the speech community really knew about the groundbreaking work that was being done. So I really wanted to share it a lot more widely. So today, I'm pleased to announce that we are releasing the first experimental support for embedded platforms in TensorFlow Lite. And to show you what I mean, here is a demonstration board that I actually have in my pocket. And this is a prototype of a development board built by SparkFun, and it has a Cortex M4 processor with 384 kilobytes of RAM and a whole megabyte of flash storage. And it was built by Ambiq to be extremely low power, drawing less than 1 milliwatt in a lot of cases. So it's able to run on a single coin battery like this for many days, potentially. And I'm actually going to take my life in my hands now by trying a live demo. So let us see if this is actually... it's going to be extremely hard to see unless we dim the lights. There we go. So what I'm going to be doing here is by saying a particular word and see if it actually lights up the little yellow light. You can see the blue LED is flashing. That's just telling me that it's running inference. So if I try saying yes, yes, yes. I knew I was taking my life into my hands here. Yes. There we go. So I'm going to quickly move that out of the spotlight there. So as you can see, it's still far from perfect. But it is managing to do a job of recognizing when I say the word and not lighting up when there's unrelated conversations. So why is this useful? Well, first, this is running entirely locally on the embedded chip. So we don't need to have any internet connection. So it's a good, useful first component of a voice interface system. And the model itself isn't quite 13 kilobytes, but it is down to 20 kilobytes. So it only takes up 20 kilobytes of flash storage on this device. And the footprint of the TensorFlow Lite code for microcontrollers is only another 25 kilobytes. And it only needs about 30 kilobytes of RAM available to operate. So it's within the capabilities of a lot of different embedded devices. Secondly, this is all open source. So you can actually grab the code yourself and build it yourself. And you can modify it. You can actually, I'm showing you here on this particular platform, but it actually works on a whole bunch of different embedded chips. And we really want to see lots more supported. So we're keen to work with the community on collaborating to get more devices supported. You can also train your own model. Just something that recognizes yes isn't all that useful. But the key thing is that this comes with a tutorial that you can use to actually train your own models. And it also comes with a data set of 100,000 utterances of about 20 common words that you use as your training set. And that first link there, the AIY projects one, if you could actually go to that link and contribute your voice to the open data set, it should actually increase the size and the quality of the data set that we can actually make available. So that would be awesome. And you can actually use the same approach to do a lot of different audio recognition to recognize different kinds of sounds, and even start to use it for similar signal processing problems like things like predictive maintenance. So, how can you try this out for yourself? If you're in the audience here, at the end of today, you will find that you get a gift box, and you actually have one of these in there. And all you should need to do is remove the little tab between the battery, and it should automatically boot up pre-flashed with this yes example. So you can try it out for yourself and let me know how it goes. Just say yes to TensorFlow, I liked, as the... and we also include all the cables, so you should be able to just program it yourself through the serial port. Now, these are the first 700 boards ever built, so there is a wiring issue. So it will drain the battery. It won't last. It will last more like hours than days. But that will actually, knock on wood, be fixed in the final product that's shipping. And you should be able to develop with these in the exact same way that you will with the final shipping product. And if you're watching at home, you can pre-order one of these from SparkFun right now for, I think it's $15. And you'll also find lots of other instructions for other platforms in the documentation. So we are trying to support all of or as many of the modern microcontrollers that are out there that people are using as possible. And we welcome collaboration with everybody across the community to help unlock all of the creativity that I know is out there. And I'm really hoping that I'm going to be spending a lot of my time over the next few months reviewing pull requests. And finally, this was my first hardware project, so I needed a lot of help from a lot of people to actually help bring this prototype together, including the TF Lite team, especially Raziel, Rocky, Dan, Tim, and Andy. Alistair, Nathan, Owen, and Jim at SparkFun were lifesavers. We literally got these in our hands middle of the day yesterday. So the fact that they managed to pull it together is a massive tribute. And also Scott, Steve, Arpit, and Andre at Ambic, who actually designed this processor and helped us get the software going. And actually a lot of people at ARM as well, including a big shout out to Neil and Zach. So this is still a very early experiment, but I really can't wait to see what people build with this. And one final note, I will be around to talk about MCUs with anybody who's interested at the breakout session on day 2. So I'm really looking forward to chatting to everyone. Thank you.
Thanks, Pete. We really hope that you try this. I mean, it's early stages, but you see a huge effort just to make this happen. I think we think that it will be really impactful for everybody. Now, before we go again, and I promise this is the last thing you hear from me, I want to welcome June, who's going to talk about how by using TensorFlow Lite with the HTPU delegate are able to train these teachable machines.
Thanks, Raziel. Hi, my name is June Tate-Gans. I'm actually one of the lead software engineers inside of Google's new Coral group, and I've been asked to give a talk about the Edge TPU-based teachable machine demo. So first, I should tell you what Coral is. Coral is a platform for products with on-device machine learning using TensorFlow and TF Lite. Our first 2 products are a single board computer and a USB stick. So what is the Edge TPU? It's a Google-designed ASIC that accelerates inference directly on the device that it's embedded in. It's very fast, localizes data to the edge rather than the cloud, doesn't require a network connection to run, and this allows for a whole new range of applications of machine learning. So the first product we built is the Coral Dev Board. Now this is a single board computer with a removable SOM. It runs Linux and Android, and the SOM itself has a gigabyte of RAM, a quad-core A53 SoC, Wi-Fi and Bluetooth, and of course, the Edge TPU. Now the second is our Coral Accelerator Board. Now this board is just the Edge TPU connected via USB-C to whatever development system you need, be it a Raspberry Pi or a Linux workstation. Now this teachable machine shows off a form of edge training. Now traditionally, there's 3 ways to do edge training. There's k-nearest neighbors, weight imprinting, and last layer retraining. But for this demo, we're actually using the k-nearest neighbors approach. So in this animated GIF, you can see that the TPU enables very high classification rates. The frame rate you see here is actually the rate at which the TPU is classifying the images that I'm showing it. In this case, you can see that we're getting about 30 frames per second. It's essentially real-time classification. And with that, I actually have one of our teachable machine demos here. So if we can turn this on. There we go. OK. So on this board, we have our Edge TPU development board assembled with a camera and a series of buttons. Now, each button corresponds with a class and lights up when the model identifies an object from the camera. First, we have to plug this in. Now, every time I take a picture, by pressing one of these buttons, it associates that picture with that particular class. And because it's running inference on the Edge TPU, it lights up immediately. So once it's finished booting, the first thing I have to do is train it on the background. So I'll press this blue button, and you can see it immediately turns on. This is because, again, it's doing inference in real time. Now, if I train one of the other buttons using something like a tangerine, press it a few times. OK, so now you can see it can classify between this tangerine and the background. And further, I can even grab other objects, such as this TF light sticker. It looks very similar, right? It's the same color. So let's see, what was the class I used? Yellow, OK. Sorry. So now, even though it's a similar color, it can still discern the TensorFlow Lite logo from the tangerine. Oh, sorry. Tangerine. There we go. So you can imagine, in a manufacturing context, your operators with no knowledge of machine learning or training in machine learning can adapt your system easily and quickly using this exact technique. So that's about it for the demo. But before I go, I should grab the clicker. And also, I should say, we're also giving away some Edge TPU accelerators. For those of you here today, we'll have one available for you as well. And for those of you on the live stream, you can purchase one at coral.withgoogle.com. OK. So we've also got some links for you up here. Please take a look at the TensorFlow Lite and our new hardware. And thank you very much.
Hi, everyone. My name is Gal Oshry, and I'm here to talk to you about TensorBoard and what's new in TensorFlow's visualization toolkit. So how many of you have used TensorBoard before? Awesome. So as you know, TensorBoard helps you visualize a lot of the data that comes out of TensorFlow. It has a wide variety of features, but today we're going to talk about a couple of new additions. So we're actually going to switch over to a demo. So this is Colab, a service from Google Research that makes it really easy to get started with TensorFlow. If you've seen the TensorFlow documentation, you've probably used Colab. A few minutes before the demo, I made sure that we have installed TensorFlow 2.0 Alpha and a couple of other setup steps so we don't have to do them right now. We're going to use the Fashion MNIST dataset, one that I'm sure you've never seen before. And we're going to train a really simple Keras sequential model, one that just has a few layers, including dense and dropout layers. We're going to train it with the Fit API and give it the TensorBoard callback so that we make sure that we log the right data to visualize in TensorBoard. Now, if you've used Colab before, you'll know that at this stage, we would need to download the logs to our local machine, make sure TensorBoard is set up, point it at those logs, and then look at them, and then go back to Colab again. That's not very convenient. So what we've done is enabled showing TensorBoard directly within Colab. You'll notice that the way that we start TensorBoard here is exactly the same as in the command line. It's the same command, just has the magic cell and magic function in front of it. The same thing would also work in Jupyter Notebooks. So let's see what's different. Well, first of all, when using the Keras callback, we now have train and validation showing up on the same charts to make it much easier to compare them in accuracy, loss, and other metrics. This makes it easier to detect things like overfitting. In the graphs dashboard, while seeing all of the ops and auxiliary information is useful for many scenarios, sometimes you just want to see what is the model that I created in Keras? What are the layers in it? So you can now switch to the Keras tag and just view that model. We can expand this to see the actual layers that we added. There are several other APIs for using TensorBoard within notebooks that let you change the height of the cell, as well as list the active instances within your Colab notebook. But we're not going to look at that today, because I want to switch gears and talk about hyperparameter tuning. Now, the model that we created was extremely simple, and we picked a couple of hyperparameters for it: the dropout rate, the number of units in the dense layer, and the optimizer. Now, if we really cared about that model's performance, we're going to want to try out different values. We're going to want to experiment with several of them and see which one leads to the best model. The way this would look today in TensorBoard is that you might include all of that information about what the values are into the run names. So as you can see here in the bottom left, you can then filter using regular expressions or go to the chart and try and hover over which line had the best result to identify which values were good. It's not the best experience, so let's see if we can do something better. Now, what I'm going to show next is something that's going to change, both in terms of the APIs and the UI. But it is available in the TF 2.0 Alpha today, so you can try it out. We're going to do several additional imports and define which values of the hyperparameters we want to try. We'll start out with just a few so that we don't take up too much time during the demo. We're going to log a summary that tells TensorBoard what were the hyperparameters that we care about and what were the metrics. We then wrap the existing training code that we had just to make sure that we log the accuracy at the end on the validation set and also tell TensorBoard that the experiment has started and finished. This time, we're going to start TensorBoard before doing our training, because in most cases, your training will take longer than 1 minute, and you want to view the TensorBoard while your model is training to understand its progress. So we've started it. It has no data, but once a couple of epochs of training have finished, we can refresh it and start to see something. Now, you'll notice in the top, we now have the hparams dashboard, which shows us at first a table where each run is represented by a row, and we have columns for each of the hyperparameters and metrics. As the runs finish, the table will become populated with them. On the left, we have some filtering, so ability to filter and sort. So we can say that we don't actually care about the number of units, or we only want to see experiments where the accuracy is at least 85. Oh, sorry. 85. So before we proceed further, I want to actually cheat a little bit and log and access some completed experiments where we've run a wider range of combinations of values for the hyperparameters. Now, while this is loading, I want to point out that I'm pointing TensorBoard directly at a folder in my Google Drive. So I had all my TensorBoard logs maybe on another machine, uploaded them to my Google Drive, and then I can access them directly within my Colab notebook. So this takes a moment to load, but hopefully when I refresh, we now see it. And I can switch over to the HParams dashboard and now see a more complete set of experiments. I can switch over to the parallel coordinates view, which shows me a visualization where we have an axis for each hyperparameter and each metric. Each run is represented by a line that passes through all these axes at the points corresponding to its hyperparameters and values. I can click and drag on any axis to select a particular range. So in this case, I've selected the experiments with relatively high accuracy, and they become highlighted in this visualization. I can immediately see that all these experiments used the Atom optimizer as opposed to SGD, and had a relatively high number of units in the dense layer. This gives me some great ideas about what I can experiment with next. I can also view the scatter plot view, which shows me the correlations between the different hyperparameters and metrics. I can again select a region here to view those points across the other charts. So just to summarize, we've looked at TensorBoard and Colab, an easier way to compare the train validation runs, visualizing the Keras conceptual graph, and better hyperparameter tuning with the HParams dashboard. All of this information is available as documentation in tensorflow.org/tensorboard. We also have a demo station upstairs, and we'd love to hear from you. So next up, I'm excited to introduce Alex, who will talk about TF function and autograph. Thank you very much.
Hello, I'm Alex, and I'm here to tell you about how you're going to build graphs in TensorFlow 2.0. And this might make you a little uncomfortable because we already spent quite some time earlier today telling you that in TensorFlow 2.0, we use eager execution by default. So why am I taking that away from you? And I'm not. You still have eager execution by default, but graphs are useful for quite a few things. The two ones that I care the most about personally are that some hardware, like our TPUs, really benefit from the kind of full program optimization that we can get if we have graphs. And if you have graphs, you can take your model and deploy it on servers, and deploy it on mobile devices, and deploy it on whatever thing you want. Make it available to as many people as you can think of. So at this point, you're probably, I remember TensorFlow 1.0. I remember the kind of code I had to write to use graphs. And I wasn't proud of it. Is he just going to tell me that I have to keep doing that? And no. One of the biggest changes we're doing with TensorFlow 2 is we're fundamentally changing the programming model with which you build graphs in TensorFlow. We're removing that model where you first add a bunch of nodes to a graph and then rely on session.run to prune things out of the graph to figure out the precise things you want to run in the correct order, and replacing it with a much simpler model based on this notion of a function. We're calling it tf.function because that's the main API entry point for you to use it. And I'm here to tell you that with tf.function, many things that you're used to are going to go away, and I dearly hope you're not going to miss them. The first one that goes away, that I really think no one in this room is going to miss, is that you'll never have to use session.run anymore. So if you've used TensorFlow with eager execution, you know how it works. You have your tensors, and you have your operations, and you pass your tensors to your operations, and the operations execute. And this is all very simple and straightforward. And tf.function is just like an operation, except one that you get to define using a composition of the other operations in TensorFlow however you wish. Once you have your tf.function, you can call it inside another function, you can take its gradient, you can run it on the GPU, on the TPU, on the CPU, on distributed things, just like how you would do with any other TensorFlow operation. So really, the way you should think about the TF function is we're letting you define your own operations in Python and making it as easy as possible for you to do this and trying to preserve as many of the semantics of the Python programming language that you already know and love, and when you execute these functions in a graph. So obviously, the first thing you would think is that, is it actually faster? And if you look at models that are large convolutions or big matrix multiplications, large reductions, it's not actually any faster because eager execution is plenty fast. But as your models get small, and as the operations in them get small, you can actually measure the difference in performance. And here, I show that for this tiny LSTM cell of 10 units, there's actually a 10-fold speedup if you use tf.function versus if you don't use tf.function to execute it. And as I was saying, we really try to preserve as much of the Python semantics as we can to make this code easy to use. So if you've seen TensorFlow graphs, you know that they're very much not polymorphic. If you built a graph for float 64, you cannot use it for float 32, or God forbid, float 16. But tf.function, but like Python code tends to be very free into the types of things it accepts. With tf.function, we do the same. So under the hood, when you call a tf.function, we look at the tensors you're passing as inputs, and we try to see, have we already made a function graph that is compatible with those inputs? If not, we make a new one. And we hide this from you so that you can just use your tf.function as you would use a normal TensorFlow operation. And eventually, you'll get all the graphs you need built up, and your code will run blazingly fast. And this is not completely hidden. If you want to have access to the graphs that we're generating, you can get them. We expose them to you. So if you need to manipulate these graphs somehow or do weird things to them that I don't approve, you can still do it. But really, the main reason why we changed this model is not to replace session.run with tf.function, is that by changing the promise for what we do to your code, we can do so much more for you than we could do before. With the model where you add a bunch of nodes to a graph and then prune them, it's very hard for the TensorFlow runtime to know what order did you want those operations to be executed in. Almost every TensorFlow operation is stateless, so that doesn't matter. But for the few ones where it does matter, you probably had to use control dependencies and other complicated things to make it work. So again, I'm here to tell you that you will never have to use control dependencies again if you're using tf.function. And how can I make this claim happen? So the promise behind tf.function is that you write code that you'd like to run eagerly, we take it, and we make it fast. So as we trace your Python code to generate a graph, we look at the operations you run, and every time we see a stateful operation, we add the minimum necessary set of control dependencies to ensure that all the resources accessed by those stateful operations are accessed in the order you want them to be. So if you have two variables and you're updating them, we'll do that in parallel. But if you have one variable and you're updating it many times, we'll order those updates so that you're not surprised by them happening out of order or something like that. So there's really no crazy surprises and weird undefined behavior. And really, you should never need to explicitly add control dependencies to your code. But you'll still get the ability of knowing what order things execute. And if you want something to execute before something else, just put that line of code above that other line of code. You know, how you do in a normal program. Another thing that we can dramatically simplify in tf.function is how you use variables in TensorFlow. And I'm sure you've all used variables before, and you know that while they're very useful, they let you share state across devices, they let you persist, checkpoint, do all those things, they can be a little finicky. Things like initializing them is very hard, especially if you're using your variables with any kind of non-trivial initialization. So another thing that we're removing from TensorFlow is the need to manually initialize variables yourself. And the story for variables is a little complicated, though, because as I try to make code compatible with both eager execution and graph semantics, you very quickly find examples where it's unclear what we should do. My favorite one is this one. If you run this code in TensorFlow 1.x and you session.run repeatedly the result, you're going to get a series of numbers that goes up. But if you run this code eagerly, every time you run it, you're going to get the same number back because we're creating a new variable, updating it, and then destroying it. So if I wanted to turn this code, wrap this code with tf.function, which one should it do? Should it follow the 1.x behavior or the eager behavior? And I think if I took a poll, you'll probably find that you don't agree with each other. I don't agree with myself, so this is an error. Non-ambiguously creating variables, though, is perfectly OK. So as you've seen in an earlier slide, you can create a variable and capture it by closure in a function. That's a way a lot of TensorFlow code gets written. This just works. Another way you can do is like write your function such that it only creates variables the first time it's called. This is, incidentally, what most libraries in TensorFlow do under the hood. This is how Keras layers are implemented, how the TF1.x layers are implemented, Sonnet, and all sorts of other libraries that use TensorFlow variables. They try to take care to not create variables every time they're called. Otherwise, you're creating way too many variables and you're not actually training anything. So code that behaves well just gets turned into function and is fine. And if you've seen this, I didn't actually need to call the initializer for this variable that I'm creating. And it's even better. I can make the initializer depend on the value of the arguments to the function or the value of other variables in arbitrarily complicated ways. And because we add the necessary control dependencies to ensure that the state updates happen in the way you want them to happen, there's no need for you to worry about this. You can just create your variables like how you would use in a normal programming language, and things will behave the way you want them to behave. Another thing that I'm really happy about tf.function is our autograph integration. And if anyone here has used control flow in TensorFlow, you probably know that it can be awkward. And I'm really happy to tell you that with autograph, we're finally breaking up with tf.const and tf.while loop. And now you can just write code that looks like this. So if you see here, I have a while loop where the predicate depends on the value of a tf.reduce sum on a tensor. This is probably the worst way to make a tensor sum to 1 that I could think of, but it fits in a slide, so yay. If you put this in a tf.function, we'll create a graph and we'll execute it. And this is nice, this is great. But how does it work? Under the hood, things like tf.const and tf.while loop are still there. But we wrote this Python compiler called Autograph that rewrites control flow expressions into something that looks like this. Huh? Why is it clicking? Yes, something that looks like this, which is not like how you would want to write code. And this then can be taken by TensorFlow and turned into fast dynamic graph code. So how does this work? To explain that, I like to take a step back and think about how does anything in TensorFlow work. So you can have a tensor, and you can do tensor plus tensor times other tensor, et cetera. Just use a tensor as you'd use a normal Python integer or floating point number. And how do we do that? I'm sure you all know this, but Python has this thing called operator overloading that lets us change the behavior of standard Python operators when applied on our custom data types, like tensors. So we can overload the underscore, underscore add, underscore, underscore sub, et cetera, and change how TensorFlow does addition, subtraction of tensors. This is all fine and dandy, but Python does not let us override underscore, underscore if. Indeed, that's not an operator in Python. Makes me very sad. But if you think about it for a few seconds, you can probably come up with rewrite rules that would let us lower to bytecode that would have underscore, underscore if overridable. So for example, if code looks like this, if condition A else B, you could conceptually write this as condition.if A and B. You need to do some fiddling with the scopes, because I'm sure you know that Python's lexical scoping is not really as lexical as you would think, and names can leak out of scopes, and it's kind of a little messy, but that's also a mechanical transformation. So if this is potentially a mechanical transformation, let's do this mechanical transformation. So we wrote this Python to TensorFlow compiler called Autograph that does this. It takes your Python code and it rewrites it in a form that lets us call underscore, underscore if, underscore, underscore while, et cetera, on tensors. This is all it does, but this just unlocks a lot of the power of native Python control flow into your TensorFlow graphs. And you got to choose. So for example, on this function here, I have two loops. One, it's a static Python loop because I write for I in range. I is an integer because range returns integers. Autograph sees this, leaves it untouched. So you still get to use Python control flow to choose how many layers your network's going to have and construct them dynamically or iterate over a sequential, et cetera. But when your control flow does depend on the properties of tensors, like in the second loop for I in tf.range, then Autograph sees it and turns it into a dynamic tf.while loop. This means that you can implement something like a dynamic RNN in TensorFlow in 10 lines of code, just like how you'd use in a normal language, which is pretty nice. And anything really that you can do in a TensorFlow graph, you can make happen dynamically. So you can make your prints and assertions happen dynamically if you want to debug, but just using tf.print and tf.assert. And notice here that I don't need to add control dependencies to ensure that they happen in the right order because of the thing that we were talking earlier. We already do this, like we thread these control dependencies automatically for you to try to really make your code look and behave the same as Python code would look like. But all that we're doing here is converting control flow. We're not actually compiling Python to the TensorFlow graph because the TensorFlow runtime right now is not really powerful enough to support everything that Python can do. So for example, if you're manipulating lists of tensors at runtime, you should still use a tensor array. It's a perfectly fine data structure. It works very well. It compiles down to very efficient TensorFlow code on CPUs, GPUs, and TPUs. But you no longer need to write a lot of the boilerplate associated with it. So this is how you stack a bunch of tensors together in a loop. So wrapping up, I think we've changed a lot in TF2, how we build graphs, how we use those graphs. And I think you'll all agree that those changes are very big. But I hope you'll agree with me that those changes are worth it. And I'll just quickly walk you through a diff of what your code is going to look like before and after this. So session.run goes away. Control dependencies go away. Variable initialization goes away. Cond and while loop go away. And you just use functions, like how we'd use in a normal programming language. So thank you, and welcome to TF2. All the examples on these slides, they run. If you go on tensorflow.org/alpha and you dig it a little, you'll find a Colab notebook that has these and a lot more for you to play around with TF function and autograph. And now I'd like to introduce Ryan, who's going to tell you about all the new ways we have of feeding data into TensorFlow.
Hi all, I'm here to tell you about TensorFlow datasets. It's a new way to have a collection of public research datasets. It's on GitHub and PyPy, and it's ready to use with TensorFlow. First, a little bit of setup. Of course, this is the partnership that we all care about, data and models. And TensorFlow 2 makes it look really nice. You set up your model, your optimizer, iterate through your training data. You get predictions, your loss, gradients, update. It all looks fantastic. And they're good together, data and models. And really, I just want to focus in on this one piece, this one line, iterating through your training data set. In TF2, with the TF Data API, you have this really expressive, simple way of expressing high performance, but flexible input pipelines. So we might start with some TF data set, and we can map and shuffle and batch and repeat, build really complex pipelines, and we know that this will be really performant. So this map call, for example, might be doing some complex image preprocessing on each record in the data set. And it's happening in parallel. You can see here num parallel calls equals 10. So TensorFlow will be spinning up a bunch of threads so that this mapping is really high performance. And at the end, you also have this ability to prefetch. So as your tight model training loop is going, you can actually be preparing batches ready to feed into the next iteration. Now, this is fantastic. But unfortunately, the source data is a little bit out of step. And so what we want is we want this amazing tight iteration, 4 inputs and targets in trained data set. But of course, what's hidden from there is how did you get the data into a format that you can actually feed into your model in the first place? Every single source data set, whether it's MNIST or IMDb sentiment classification, the IMDb reviews data set, it's all a little bit different. And of course, this makes perfect sense. When you're distributing data at rest, there's some natural format that you'd like to distribute it in. But we're not really interested in data at rest. We're interested in having data in a format that's sort of ready to move into a TF data pipeline. And what we really want is something that's good together. We want these two pups, data and models, to really be simpatico. And I'm happy to tell you that TensorFlow datasets is really just about this one piece of getting data into a format that's ready to move into a TF data pipeline. And so here's TensorFlow datasets. You import TensorFlow datasets, and this load API for MNIST, because that's our canonical first example always and forever, I hope. And we're grabbing the split train, so the training split of the dataset. We're asking for supervised tuples. So in this case, MNIST is a supervised dataset. It has inputs and targets, and so we'll get inputs and target tuples. We get a TF data dataset right back from the load call. And we can build a complex pipeline. In this case, we're adding some shuffling and some batching. And then we're off. Now we can iterate through our inputs and do all the modeling things that we need. And load actually hides a lot of the complexity. And so what's happening here with load is that MNIST is actually being fetched from the source. It's being pre-processed. It's being put into a standard format. It's being documented with statistics and everything, which I'll show you in a second. And then you're building the front end. So you have pre-processed data on disk, ready to move. Typically, you'd only do this once, and of course, TFDS will cache all those results for you. And then you're getting a TF data pipeline out of it. And we don't just have MNIST. So ImageNet, complex data set. Most places, when you go look at the tutorial for how do I use ImageNet, first step is like, run this bash script, muck with the files over here, make sure you filter out these records, things like that. And of course, this is all taken care of for you. Now, ImageNet is gated with password and username. And so currently, TensorFlow datasets just asks you to download the data, put it in a certain place, and TensorFlow datasets takes it from there. And we're actually working on, with Kaggle, to get ImageNet able to be auto-downloaded just from without having any user intervention at all. We go beyond images. So we have text data sets. So in this case, we have IMDb reviews. Note, again, that the API doesn't change. This is just a tfds.load call to get a data set. So in this case, we'd be getting the plain text IMDb reviews data set. But of course, text is a notoriously difficult sort of format to work with. When you actually are interested in doing machine learning on it, you have to do encodings. And so we're actually shipping with 3 really powerful encodings. One is byte level, so you have character level encoding. And another is subwords. And so we have a really great subword text encoder that was originally developed in the Tensor-to-Tensor library. And so in this case, we'd be getting IMDb reviews already encoded into integers using a subword vocabulary with about 8,000 tokens. So each of these data sets is packaged together as a data set builder. So if you wanted to add a data set to TensorFlow data sets, which I hope every single one of you does, I think there should be about 1,000 new data sets within a week. That's my hope. So data set builder is actually really simple. It does exactly those 3 things that load was sort of hiding. The first, it has a method called download and prepare, which takes source data out on the open web or on a local directory and produces preprocessed files. So it takes data at rest and it puts it into a format that's data ready to move. The second is as dataset. As dataset takes those preprocessed files on disk and produces a tf.data.dataset. And the third is really useful information, metadata about the dataset, which can be programmatically really useful. So dataset info is the documenting object. So in this case, it has the features in the data set. And each of the features, you can see, documents the name, the shape, and the type. So in this case, the image for MNIST is 2828 by 1, 28 by 28 by 1, type uint8. The class labels, the number of classes is documented in the class label feature. You also get statistics on the data set itself. What are the splits that are actually exposed? In this case, train and test. And how many records are in each one? MNIST has 60,000 images in the training set and 10,000 images in the testing set. For supervised tasks, you also get supervised keys. So if you wanted to be able to programmatically grab a data set from TensorFlow data sets and sort of filter for all the ones that are trivially supervised data sets, you can look for supervised keys and pick out the features that you need. And for text, again, one of these things that's a bit annoying to work with often. So this is IMDb reviews. We see that it has a label feature and a text feature. And the text feature actually contains the encoder. We see here that it's a subword text encoder with a vocab size of 8,185. You get the same statistics for the splits. We also support NumPy usage. Now, this is TensorFlow Dev Summit, so maybe this isn't so useful, but we wanted to make TensorFlow datasets really portable. And so you can actually just call this tfds.asNumPy, and it hides all the TensorFlow from you. And you pass it a dataset, it hands you back an iterator, a Python generator over NumPy arrays, which is great. So coming back to our initial example, we had this beautiful model and data. But of course, trained data set, where did this come from, and how did you actually get the data? And with TensorFlow datasets, simple change, and you actually have something that works end-to-end, out of the box, which is something we're really happy about, and we hope you are too. You can come find us on PyPy, the TensorFlow website, and GitHub. We have over 30 datasets already, and there's more being added every day. The community on GitHub has actually gotten surprisingly active surprisingly quickly, so come join us. We absolutely could use your data. If you're distributing some data set and you'd like to make your data set famous, please add it to TensorFlow datasets. It's a great way to make it accessible to a huge community. And come help us on GitHub. There are dataset requests. You can help implement a dataset that's been requested many times, or help us just develop. We develop fully out in the open. All of our internal changes are actually external changes. We just develop straight out on GitHub. So thanks very much. Hopefully you guys find this useful, and come help us out. Next up, thank you. So next is something I think is really great, actually, is Chris Latner and Brendan Seda telling you about Swift for TensorFlow.
Thanks, Brian. Fantastic. Hi, everyone. I'm Chris, and this is Brennan, and we're super excited to tell you about a new approach to machine learning. So here in the TensorFlow team, it is our jobs to push the state of the art in machine learning forward. And we've learned a lot over the last few years with deep learning, and we've incorporated most of that all into TensorFlow 2, and we're really excited about it. But here, we're looking a little bit further beyond TensorFlow 2. And what do I mean by further? Well, eager mode makes it really easy to train a dynamic model. But deploying it still requires you take that and then write a bunch of C++ code to help drive it. And that could be better. Similarly, some researchers are interested in taking machine learning models and integrating them into larger applications. That also often requires writing C++ code. We always want more flexible and expressive auto-differentiation mechanisms. And one of the things we're excited about is being able to define reusable types that then can be put into new places and used with automatic differentiation. And we always love improving your developer workflow. We want to make you more productive by taking errors in your code and bringing them to your source, and also by just improving your iteration time. Now, what we're really trying to do here is lift TensorFlow to entirely new heights. And to do that, we need to be able to innovate at all levels of the stack. This includes the compiler and the language. And that's what Swift for TensorFlow is all about. We think that applying new solutions to old problems can help push machine learning even further than before. But let's jump into some code. So first, what is Swift? Swift is a modern and cross-platform programming language that's designed to be easy to learn and use. Swift uses types, and types are great because they can help you catch errors earlier, and also they encourage good API design. Now, Swift uses type inference, so it's really easy to use and very elegant. But it's also open source, and it has an open language evolution process, which allows us to change the language and make it better for machine learning, which is really great. Let's jump into a more relevant example. This is how you define a simple model in Swift for TensorFlow. As you can see, we're laying out our layers here. And then we can define a forward function, which composes them together in a linear sequence. Now, you've probably noticed that this looks a lot like Keras. And that's no accident, of course. We want you to be able to take what you know about Keras and bring it forward into this world as well. Now, once we have a simple model, let's train it. How do we do that? All we have to do is instantiate our model, pick an optimizer and some random input data, and then pick a training loop. And here we'll write it by hand. One of the reasons we like writing it by hand is that it gives you the maximum flexibility to play with different kinds of constructs, and you can do whatever you want, which is really great. But some of the major advantages of Swift for TensorFlow are the workflow. And so instead of telling you about it, what do you think, Brennan? Should we show them?
Let's do it.
All right. The team has thought long and hard about what's the easiest way for people to get started using Swift for TensorFlow. And what could be easier than just opening up a browser tab? This is Google Colab, hosted Jupyter notebooks. And it comes with Swift for TensorFlow built right in. Let's see it in action. Here is the layer model, the model that Chris just showed you a couple slides ago. And we're going to run it using some random training data right here in the browser. So we're going to instantiate the model. We're going to use the stochastic gradient descent SGD optimizer. And here we go. We have now just trained a model using Swift for TensorFlow in our browser on some training data right here. Now we can see the training loss is decreasing over time, so that's great. But if you're ever like me, and whenever I try and use machine learning in any application, I start with a simple model, and I've got to iterate. I've got to tweak the model to make it fit better to the task at hand. So since we're trying to show you the workflow, let's actually edit this model. Let's make it more accurate. So here we are. Now, let's think a little for a moment. What changes do we want to make to our model? Well, this is deep learning after all, so the answer is always to go deeper, right? But you may have been following the recent literature in state of the art in that not just sequential layers, but skip connections or residual connections are a really good idea to make sure your model continues to train effectively. So let's go through and actually add an extra layer to our model. Let's add some skip connections. And we're going to do it all right now in under 90 seconds. Are you ready? All right, here we go. So the first thing that we want to do is we need to define our additional layer. So we're going to fill in this dense layer. Float. And one thing you can see is that we're using tab autocomplete to help fill in code as we're trying to develop and modify our model. Now we're going to fix up the shapes right here really quick so that the residual connections will all work. If I can type properly, that would go better. All right, great. We've now defined our model with the additional layers. All we need to do is modify the forward pass so that we add those skip connections. So here we go. The first thing we need to do is we need to store in a temporary variable the output of the flattened layer. Then we're going to feed the output of the flattened layer to our first dense layer. So dense.applied to temp in context. Now, for the coup de grace, here's our residual connection. So dense2.applied to temp plus temp2 in context. Run that, and yes, that works. We have now just defined a new model that has residual connections and is one additional layer deeper. Let's see how it does. So we're going to reinstantiate our model and rerun the training loop. And if you recall from the loss that we saw before, this one is now substantially lower. This is great. This is an example of what it's like to use Swift for TensorFlow to develop and iterate as you apply models to applications and challenges. But Swift for TensorFlow, thank you. But Swift for TensorFlow was designed for researchers, and researchers often need to do more than just change models and change the way the architecture fits together. Researchers often need to define entirely new abstractions or layers. And so let's actually see that live right now. Let's define a new custom layer. So let's say we had the brilliant idea that we wanted to modify the standard dense layer that takes weights and biases, and we wanted to add an additional bias set of parameters. Okay? So we're going to define this double bias dense layer right here. So I'm going to type this really quickly. Stand by, 15 seconds. Here we go. Whew, all right, that was great. So let's actually walk through the code so that you can see what's going on. So the first thing that we have is we define our parameters. So these are W, like our weights for our neurons, and B1, bias 1, and B2, our second bias. We define an initializer that takes an input size and an output size, just like dense does. And we use that to initialize our parameters. The forward pass is very simple to write. So here's just applied to. And we just take the matrix multiplication of input by our weights, and we add in our bias terms. That's it. We have now just defined a custom layer right in Colab in just a few lines of code. All right, let's see how it goes. Here's model 2, and so we're going to use our double bias dense layer. And we're going to instantiate, and we're going to train it using, again, our custom handwritten training loop. Here's an example of another way that we think Swift for TensorFlow makes your life easier. Because Swift for TensorFlow can statically analyze your code, it can be really helpful to you. I don't know about you, but I regularly put typos in my code. I don't know if you saw me typing earlier. And Swift for TensorFlow here is helping you out, right? It's saying, look, you mistyped softmax cross entropy. This should be labels, okay? All right, so we run it, we train it, and our loss isn't as good. This was not the right idea, but this is an example of how easy it is for researchers to experiment with new ideas really easily in Swift for TensorFlow. But let's go deeper. Swift for TensorFlow is, again, designed for researchers, and researchers need to be able to customize everything, right? That's the whole point of research. And so let's show an example of how to customize something other than just a model or a layer. So you may have heard that large GPU clusters or TPU superpods are like delivering massive breakthroughs in research and advancing the state of the art in certain applications and domains. And you may have also heard that as you scale up to effectively utilize these massive hardware pools, you need to increase your batch size. And so let's say you're a researcher and you want to try and figure out what are the best ways to train deep neural networks at larger batch sizes. Well, if you're a researcher, you probably can't buy a whole GPU cluster or rent a whole TPU superpod all the time for your experiments. But you often have a GPU under your desk. So let's see how we can simulate running on a super large data parallel GPU or TPU cluster on a single machine. We're going to do it all in a few lines of code right here. So here's our custom training loop. Here's the standard part, right? This is our 1 to 10 training epochs. And what we're going to do is instead of just applying our model forward once, we have an additional inner loop, right? So we're going to run our forward pass. We're going to run our model, 4 times, and we're going to take the gradients for each step, and we're going to aggregate them in this grads variable, okay? This simulates running 4 independent accelerators, 4 GPUs or 4 TPUs, in a data parallel fashion on a batch that's actually 4 times as large as what we actually run. We're going to then use our optimizer to update our model along these aggregated gradients, again, simulating a data parallel synchronous training process. That's it. That's all there is to it. We're really excited by this sort of flexibility and capabilities that Swift for TensorFlow brings to researchers. Back over to you, Chris.
Thanks, Brennan. So we think that the focus on catching errors early and also productivity enhancements like code completion can help you in a lot of ways. And it's not just about like automating typing of code, but it can also be about discovery of APIs. So another thing that's really cool about Swift as a language is that it has really good interoperability with C code. And so in Swift, you can literally just import a C header file and call symbols directly from C without wrappers, without boilerplate or anything involved. It just works. So we've taken this approach in the TensorFlow team. We've taken this approach and brought it to the world of Python. And one of the cool things about this is that that allows you to combine the power of Swift for TensorFlow with all the advantages of the Python ecosystem. How about we take a look?
Thanks, Chris. The Python data science ecosystem is incredibly powerful and vibrant. And we wanted to make sure that as you start using Swift for TensorFlow, you didn't miss all your favorite libraries and utilities that you were used to. And so we've built a seamless Python interoperability capability to Swift for TensorFlow. And let's see how it works in the context of my favorite Python data science library, NumPy. So the first thing you need to do is import TensorFlow and import Python. And once you do that, that defines this Python object that allows you to import arbitrary Python libraries. So here we import pyplot from the matplotlib library and NumPy, and we assign it to NP, okay? After that, we can just use NP just as if we were in Python. So here we call linspace, we're going to call sine and cosine, and we're going to pass those values to pyplot. When we run this cell, It just works exactly as you'd expect. Thank you. Now, this sort of kind of looks like the Python code you're used to writing, but this is actually pure Swift. It just works seamlessly. But this is maybe a bit of a toy example. So let's see this a little bit more in context. OpenAI has done a lot of work in the area of reinforcement learning. And in order to help that along, they developed a library, a Python library called OpenAI Gym. Gym contains a collection of environments that are very useful when you're trying to train a reinforcement learning agent across a variety of different challenges. Let's use OpenAI Gym to train a reinforcement learning agent in Swift for TensorFlow right in our browsers. So the first thing we need to do is we need to import Gym. We're going to define a few hyperparameters here, and now we define our neural network. In this case, we're going to pick a simple 2-layer dense network, and it's just a sequential model. Okay? After that, we have some helper code to filter out bad or short episodes and whatnot. But here's the real meat of it. We're going to use Gym to instantiate the cart poll v0 environment. So that's our env. We're going to then instantiate our network right here in our optimizer. And here's our training loop. There we go. So we're going to get a bunch of episodes. We're going to run our model, get the gradients, and we're going to apply those to our optimizer. And we're going to record the mean rewards as we train. Okay? It's all very simple, straightforward Swift. And here you can see us training a Swift for TensorFlow model in an OpenAI Gym environment using the Python bridge. Totally seamless. And of course, afterwards, you can keep track of the parameters of the rewards. In this case, we're going to plot the mean rewards as the model trained using Python NumPy. Totally seamless. You can get started using Swift for TensorFlow using all the libraries you know and love, and take advantage of what Swift for TensorFlow brings to the table. Back over to you, Chris.
Thanks, Brian. So one of the things I love about this is it's not just about being able to leverage big important libraries like NumPy. We're working on the ability to integrate Swift for TensorFlow and Python for TensorFlow code together, which we think will provide a nice transition path to make you able to incrementally move code from one world to the other. Now, I think it's fair to say that calculus is an integral part of machine learning. And we think that differentiable programming is so important that we've built it right into the language. This has a number of huge advantages, including enabling more flexible and custom work with differentials, with derivatives. And we think this is really cool. So I'd like to take a look.
So we've been using Swift for TensorFlow's differential programming capabilities throughout all of our demos so far. But let's really break it down and see what's going on at a fundamental level. So here we define my function that takes 2 doubles and returns a double based on some products and sums and quotients. If we want Swift for TensorFlow to automatically compute the derivative for us, I would just annotate it at differential. Swift for TensorFlow will then derive the derivative for this function right when we run the cell. To use this auto-generated derivative, use gradient. So gradient takes 2 things. It takes a closure to evaluate and a point that you want to evaluate your closure at. So here we go. This is what it is to take the derivative of a function at a particular point. So we can change this around. This one's my favorite tasty number, and that works nicely. Now, one thing to note, we've just been taking the partial derivatives of my function with respect to a. But of course, you can take the partial derivatives, you get the full gradient of my function, like so. Often with neural networks, however, you want to get not just the gradients for your network as you're trying to train it and optimize your loss function. You often want what the network predicted, right? This is really useful to compute accuracy or other debugging sort of information. And for that, you can use value with gradient, okay? And that returns a tuple containing both the value and the gradient, shockingly enough. Now, one thing to note, in Swift, tuples can actually have named parameters. They aren't just ordered. And so you can actually see that it prints out really nicely, and you can access values. We think this is, again, another nice little thing that helps making makes writing and debugging code, and more importantly, reading it and understanding it later, a little bit easier. But the one thing that I want to call out is that throughout this, we've been using just normal types. These aren't tensor of something. It's just plain old double. This is because automatic differentiation is built right into the language in Swift for TensorFlow. And it makes it really easy to express your thoughts very clearly. But even though it's built into the language, we've actually worked very hard to make sure that automatic differentiation is totally flexible so that you can customize it to whatever needs you have. And instead of telling you about that, let's show you. So let's say you want to define an algebra in 2D space. Well, you're certainly going to need a point data type. So here we define a point struct with x and y. And we just mark it differentiable. We can define helper functions on it, like dot or other helper functions. And Swift for TensorFlow, when you try and use your code, it will often automatically infer when you need gradients to be computed for you, automatically computed for you by the compiler. But often it's a good idea to document your intentions, and so you can annotate your helper functions as @differentiable. The other reason why we recommend doing this is because this helps catch errors. So here, Swift for TensorFlow is actually telling you that, hey, you can only differentiate functions that return values that conform to differentiable. But int doesn't conform to differentiable, right? What this is telling you is that my helper function returns an int. And int is all about taking infinitesimally small steps as you optimize and take gradients, right? And integers just are very discrete. And so Swift for TensorFlow is helping to catch errors right when you write the code very easily and tell you what's going on. So the solution, of course, is just to not mark that as @differentiable. The cell runs just fine. But let's say we also wanted to go beyond just defining the dot product. Let's say we also wanted to define the magnitude helper function. That is the magnitude of the vector defined by the origin to the point in question. So to do that, we can use the distance formula if we're going to do Euclidean distance. And we can define an extension on point that does this. But we're going to pretend for a moment that Swift doesn't include a square root function, because I want a good excuse for you to see the interoperability with C. Okay? So we're actually going to use C's square root function that operates on doubles. Okay? So based on the definition of Euclidean distance, we can define the magnitude, and it totally just, no, it doesn't quite work. Okay, let's see what's going on. So we wanted magnitude to be differentiable, and it's saying that you can't differentiate the square root function because this is an external function that hasn't been marked as differentiable. Okay, what's that saying? Well, the square root, it's a C function. It was compiled by the C compiler. And as of today, the C compiler can't automatically compute derivatives for you. So Swift for TensorFlow is saying, like, hey, this isn't going to work. This is excellent because it gives me a great excuse to show you how to write custom gradients. All right. So here we define a wrapper function, my square root, that just calls down in the forward pass to the C square root function. In the backwards pass, we take our double and we return a tuple of two values. Rather, the first element in the tuple is the normal value in the forward pass. And the second is a pullback closure. And this is where you define the backwards pass, capturing whatever values you need from the forward pass. Okay? So we're going to run that. We're going to go back up to our definition of magnitude and change it from square root to my square root, rerun the cell, and it works. We've now defined point and two methods on it, dot and magnitude, and we can now combine these in arbitrary other silly differentiable functions. So here I've defined the silly function, and we've marked it as differentiable. And we're going to take 2 points. We're also going to take a double, right? You can mix and match differentiable data types totally fluidly. We're going to return doubles, and we're going to take magnitudes and do dot products. It's a silly function after all. And we can then use it, compute the gradient of this function at arbitrary data points. Just like you'd expect, you can get the value of the function, get full gradients in addition to partial derivatives with respect to individual values. That's been a quick run through of how to use customization, custom gradients, custom data types with a language integrated automatic differentiation built into Swift for TensorFlow. But let's go one step further. Let's put all this together and show how you can write your own debuggers as an example of how this power is all in your hands. So often when you're developing models, or debugging models, you often want to be able to see the gradients at different points within your model. And so here, we can just define in regular Swift code a gradient debugger. Now, it's going to take as input a double, and it's going to return it just like normal for the forward pass, right? It's an identity function. On the backwards pass, we're going to get the gradient, we're going to print the gradient, and then we're going to return it. So we're just passing it through, just printing it out. Now that we've defined this gradient debugger ourselves, we can use it in our silly function to see what's going on as we take derivatives. So gradient debugger, here we go. We can rerun that. And when we take the gradients, we can now see that for that point in the silly function of a.b, the gradient is 3.80. That's been a brief tour through how automatic differentiation works in Swift for TensorFlow and how it's customizable so that you can harness the power in whatever abstractions or systems you need to build. Back over to you, Chris.
Thanks, Brennan. So the funny thing about all this is that the algorithms that we're building on were defined back in the 1970s. And so it really took language integration to be able to bring these things forward into the world of machine learning. There's a tremendous amount of depth here, and I'm really excited to see what you all can do with it. And we think that this is going to enable new kinds of research, which we're very excited about. There's also a ton of depth, and if you're interested in learning more, we have a bunch of detailed design documents available online. Now let's talk about performance a little bit. Now, Swift is fast, and this comes from a number of different things, one of which is that the language itself has really good low-level performance. There's also no GIL to get in the way of concurrency. Swift for TensorFlow also has some advanced compiler techniques to automatically identify graphs for you and extract them so you don't have to think about that. The consequence of all this together is that we think Swift has the world's most advanced eager mode. Now, you may not care that much about performance. You may wonder, like, why do we care about this stuff? Well, we're seeing various trends in the industry where people are defining neural nets and then want to integrate them into other larger applications. And typically what this requires is this requires you to export graphs and then write a bunch of C++ code to load and orchestrate them in various ways. So let's take a look at an example of this. AlphaGo Zero is really impressive work that combines three major classes of techniques. Of course, you have deep learning on the one hand, but it also drives it through Monte Carlo tree search to actually find and evaluate these spaces. And then it runs them at scale on industry-leading TPU accelerators. And so it's the combination of all three of these things that make AlphaGo Zero possible. Now, this is possible today, and if you're an advanced team like DeepMind, you can totally do this. But it's much more difficult than it should be, and we think that breaking down barriers like this can lead to new breakthroughs in science, and we think that this is what can drive progress forward. So instead of talking about it again, let's take a look.
Minigo is an open source Go player inspired by DeepMind's AlphaGo Zero project. It's available on GitHub, and you can certainly check out the code, and I encourage you to. They're also going to be here, and they have some other presentations tomorrow. But the Minigo project, when they started out, they were writing everything in normal TensorFlow, and it was working great, until they started trying to run at scale on large clusters of TPUs. There, they ran into performance problems and had to rewrite things like Monte Carlo tree search into C++ in order to effectively utilize modern accelerators. Here, we've re-implemented Monte Carlo tree search and the rest of the Minigo self-play in pure Swift. And we're going to let you see it running right here in Colab. So here we define a helper function where we take in a game configuration and a couple participants. These are our white and black players. And we're going to basically play the game until we have a winner or a loser. And so let's actually run this. Here we define a game configuration. We're going to play between a Monte Carlo tree search powered by neural networks versus just a random player, just to see how easy it is to flip back and forth or mix and match between deep learning and other arbitrary machine learning algorithms right here in Swift. So here you go. You can see them playing white, black, playing different moves back and forth, and it just goes. We think that Swift for TensorFlow is going to unlock whole new classes of algorithms in research because of how easy it is to do everything in one language with no barriers, no having to rewrite things into C++. Back over to you, Chris.
Thanks, Brennan. The cool thing about this, of course, is that you can actually do something like this in a workbook, which is pretty phenomenal. And we've seen many different families of new techniques that can be combined together and fused in different ways. And bringing this to more people, we think, will lead to new kinds of interesting research. Now, our work on usability and design is not just about high-end researchers. So we love them, but Swift is also widely used to teach new programmers how to code. And education is very close to our hearts. And so I'm very excited to announce a collaboration that we're embarking on with none other than Jeremy Howard. But instead of talking about this, I'd rather have Jeremy speak about it now.
At Fast.ai, we're always looking to push the boundaries of what's possible with deep learning, especially pushing to make recent advances more accessible. We've been involved with setting ImageNet speed records at a cost of just $25 and building the world's best document classifier. Hundreds of thousands have become deep learning practitioners through our courses and are producing state-of-the-art results with our library. We think that with Swift for TensorFlow, we can go even further. So we're announcing today that our next course will include a big Swift component, co-taught by someone that knows Swift pretty well.
Chris, I think he means you.
Yeah, we'll see how this goes. So I'm super excited to be able to help teach the next generation of learners. But I'm also really excited that Jeremy will be bringing his expertise in API design and helping us shape the high-level APIs in Swift for TensorFlow. So we've talked about many things, but the most important part is that Swift for TensorFlow is really TensorFlow at its core. And we think this is super important because we've worked really hard to make sure that it integrates with all the things going on in the big TensorFlow family, and we're very excited about that. Now, you may be wondering where you could get this. So Swift for TensorFlow is open source. You can find it on GitHub now, and you can join our community. It also works great in Colab, as you've seen today. We have tutorials, we have examples, and all the demos you saw today are available now in Colab, which is great. We've also released our 0.2 release, which includes all the basic infrastructure and underlying technology to power these demos and examples. And we're actively working on high-level APIs right now. So this is not ready for production yet, as you could guess, but we're very excited about shaping this future, building this out, exploring this new programming model. And this is a great opportunity for advanced researchers to get involved and help shape the future of this platform. So we'd love it for you to try it out and let us know what you think. Thank you. And next up, I'd like to invite Ed to talk about the TensorFlow community.
Thanks, Chris. Hey, everybody. How you doing? Good. Good. Excellent. That was an amazing set of demos, wasn't it? So I work with TensorFlow, helping build community and collaboration around the open source project. And usually I put the thank you slide at the end for listening to me. But actually, I want to thank you for contributing and being part of the TensorFlow project. Whether you're here in this room or on the live stream, there's been some amazing talk on YouTube from people in China and India and Japan, all over the world joining us virtually today. Thank you for your contributions. The project is where it is today because of you. Of course, in core TensorFlow alone, we've had this many commits. This figure's out of date, over 50,000 from over 1,800 contributors. And much more than just code commits. You know, there have been 39,000 Stack Overflow questions about TensorFlow. We have 66 machine learning Google developer experts, many of whom are here with us today. So welcome and thank you, guys. It's really great to have you with us, and thank you for everything you do helping teach people about TensorFlow. And we've had 14 guest posts to the TensorFlow blog, and that keeps going up. There's so many ways that people are contributing. Whether you're organizing a meetup, whether you're teaching other people, whether you're speaking at conferences, thank you. You're really helping build out the TensorFlow ecosystem. So in this talk, what I want to do is discuss how we're growing the ecosystem and report back on some of the changes that we've made over the last year. So I'm going to cover how we're making it easier to get involved in TensorFlow, how also we're trying to consult better with the users and the community and be more transparent about our development. We're going to cover how we're empowering everybody to get involved and to do more, and increasing the number of contact points where you can get involved in the project. And finally, I'm going to go into a bit more depth about the conference that was announced this morning, the TensorFlow World. So let's talk about how we're making contribution easier to TensorFlow. One of the most important things to help people contribute to the project is increasing its modularity. You heard Martin talk this morning about the low-level APIs. And with the move to TensorFlow 2.0, we're trying to make it less of a monolith, both in terms of code and in terms of people organization. When you come and you want to contribute to an open source project, it helps to be able to find where to contribute and who to work with. By splitting things out, we're creating more surface area where it's easy to start building and creating new projects. And our special interest groups play a big part in this, and I'll talk a bit more about them later. But it's not just code. There's so many more places to contribute this year compared to where we were last year. So I'm going to talk briefly about our documentation groups, the groups getting involved in testing, people who are blogging, and on YouTube and more. You know, I was super excited to see last week that we have published a TensorFlow tutorial now in Korean. And that's not a translation that we've done in our team, but that has come from the community. So thank you so much to Hassan Park for the Korean work. Similarly, we're able also to publish it in Russian. Thank you to Andrew Stepin. This is just so exciting to see that TensorFlow is being taken to more areas around the world, thanks to you. I'm also really excited about the TensorFlow 2.0 testing group. Led by Paige Bailey, this is a bunch of contributors and Google developer experts who are working to give TensorFlow 2.0 a thorough test. And you see on the screen an example of a friction log. And so what's happening here is the folks are going through ML workflows with TensorFlow 2.0, documenting what they find delightful and awesome, and also things that could be a little bit better. If you'd like to join in this work, this group meets weekly and often has guest talks from maintainers and SIG leaders and so on, and is really helping bring TensorFlow 2.0 from the cutting edge into something that is thoroughly tested and ready for use. I already mentioned we have over 14 posts from guests on the TensorFlow blog. This is from a great post about real-time person segmentation in the browser with TensorFlow.js that comes from a grad student and researcher at ITP. So whether it's testing, whether it's documentation, whether it's blogs, conference talks, thank you. Now I want to talk a little bit about TensorFlow RFCs. As you probably know, RFC means request for comments. This time last year, we weren't that organized about how we evolved TensorFlow's design in terms of communicating it. And I stood on this stage and told you about how we were going to launch the RFC process. Well, now we've accepted 21 RFCs over the period of the last year. This is our key way to communicate design, where before code gets landed in the project, we post an RFC about the design and consult widely. Now, this isn't just about code that's coming in from the TensorFlow core team outwards. They can be created on and commented on by anyone. And we've had several RFCs that have come from the broader community, and I expect to see so many more of those in the future. We have several, for instance, from the SIG groups already. One of the things I'm most proud about is how the RFC process is underpinning the 2.0 transition. As was mentioned earlier, but all the major changes in TensorFlow 2.0 have been proposed and consulted with in RFCs. You know, this isn't just a great way of consulting and getting information and feedback. Going forward, you now have a big repository of technical documentation about why design choices were made a certain way in TensorFlow. And it's a great educational resource as well for people who are coming on and want to get involved in contributing to the project. So I really want to give a big thanks to anyone who has authored or reviewed an RFC. You've played a vital role in making TensorFlow better. Let's talk a bit about the social structure of TensorFlow. You know, last year I talked about how coming to a large project can be a little bit daunting. You don't know where people are, where the people that have your interests in common are. And so we created the Special Interest Groups, or SIGs, as a way of organizing our work. There are so many uses of TensorFlow, so many environments, so many architectures, and many of them are outside of the scope that the core team can resource. And what we wanted to do was enable TensorFlow to grow and be more sustainable by creating a way for like-minded people to collaborate around well-defined projects. So this is why SIGs exist. They're groups of people who are working together for a defined project focus. We started last year with SIG Build, and now we have 6 of them up and running. I'm going to give you a quick state of the SIGs. Many, in fact, most of all the SIG leaders are here with us today as well, so I'll give a shout out to them. And hopefully you'll also be able to talk to them in the lunch and tomorrow. So, SIG add-ons first. Thank you to Sean Morgan and Armando Fandango for leading this group. Martin mentioned at the beginning of the day that TF-Contrib is no longer a part of TensorFlow going into TensorFlow 2.0. And SIG add-ons is a place where a lot of that code is going. So these are parts of TensorFlow that don't fall into the core, but do conform to these well-defined APIs, so more losses, ops, layers, and so on. Now, there's already an RFC published about where you can find things that you used to find in Contrib that have gone into add-ons. And add-ons are also going to publish another RFC real soon to say, well, how can you get involved if you have your favorite op or whatever that you want to step up and be a maintainer and maintain it for everybody, how you can join in the project. So I'd encourage you to take a look at that. SIG Build. SIG Build really is where TensorFlow meets the outside world. And it's not always the most glamorous piece of work, but building TensorFlow, packaging it, distributing it is tough. And so thank you so much to Jason Zaman and Austin Anderson who lead that SIG. SIG Build has achieved a lot in the last few months. One thing, it's the home for third-party contributed builds for architectures that we don't ship out as part of core. So IBM Power, Intel MKL optimized builds. And SIG Build works on improving the TensorFlow build and helps us be a better neighbor in the Python ecosystem as well. As you can imagine, machine learning generates a lot of extreme situations that needs changes in ways we evolve in packaging and distributing software. SIG.io is a fantastic group that helps connect TensorFlow to other systems. You know, out in the real world, your data exists somewhere. You're using other systems. It's in other formats. So this group is led by Yong Tang and Anton Dmitriev. And it really ships support for extra file systems, extra file formats. So if you're using any of these things in the Apache ecosystem or any of these file formats, you can use the SIG add-ons module to use that data in TensorFlow. This group is prolific. They've already dropped 4 releases. Last week, they just created the 0.4 release. And they also ship our integration with their module too. SIG networking is where a lot of the alternative networking schemes that are available in Contrib are going to. This is led by Byron Yee and Joran Bedorf. So if you're using GDR, verbs, MPI, this is where you can find that. SIG Rust, led by Adam Chrome, is developing idiomatic language bindings for the Rust programming language. If you're interested in this or any of the other SIGs, please talk to the leaders. They really do want more help, and now they're up and running. They're in a great place to bring people on. If you're looking for a way to get involved in contributing to TensorFlow, this is an ideal one. Finally, let me touch on SIG TensorBoard. We've rebooted SIG TensorBoard this year to really work closely with the community. And so this is a great time to be involved as the TensorBoard team is starting to consult and figuring out how we can best enable people who are using TensorBoard, both in terms of creating plugins or using it at scale. If you go to the demo area above and go to the TensorBoard stand, you'll find Mani and Gal there who will be happy to talk to you. So this is the URL for anything you want to do with joining the TensorFlow community. From docs to testing to SIGs and all the other ways to be involved, the developer mailing list. Please head there. And if you're here with us rather than on the live stream, we're doing a contributor luncheon tomorrow where there'll be a little panel discussion about contributing to TensorFlow, and many of the core team and the SIG leaders will be there to talk to you. So finally, let's move on and talk about TensorFlow World. I'm so excited about this. It's our vision to bring together the amazing people who are part of our community and give us space for everyone to connect with each other. You know, there's so much we can all learn from how we're all working with TensorFlow. So working with O'Reilly Media, we're going to have this event at the end of October this year here in Santa Clara. It'll be 4 days that really celebrate the TensorFlow ecosystem. We'll have content from talks to tutorials. There'll be an expo and a place for vendors to present. So we understand that as TensorFlow gets out into the real world, there's a large ecosystem beyond folks in this room. And we're really excited that that means that we can bring everyone together. You know, the main point of doing something like this is to connect all the amazing users and everyone with experience to share. As you heard, the call for proposals is now open. So if you have anything to share with your work, your product, your company, head to TensorFlow World, put in a proposal. You've got about 4 or 5 weeks while the call for proposals is open, and then we'll be selecting talks a few weeks after that. I really hope that you will lend your voice to this event, and I'm so excited to see you all in October. So once again, thank you. We really appreciate how much that you are part of our community. Honestly, in my job, the best thing every day is when I get to talk to folks who are using or developing TensorFlow, and I know that's the same for everyone in the team. It really is so exciting to work with everybody here. This is the way you can meet me. Please do, if you have any issue or any desire to contribute or get involved with the community, reach out. We're really happy to talk to you. So thank you very much for your attention.
Exciting event so far, and it's great to see all the questions that are being asked on social media. Please keep asking them and putting hashtag TensorFlow. We're here today to answer them live on the live stream. I'm Lawrence Moroney.
And I'm Paige Bailey, and remember, it is hashtag AskTensorFlow.
Hashtag AskTensorFlow.
Because we're the TensorFlow that you shall be asking.
Exactly. So we're here to try and answer as many questions as we can. Sorry if we don't get to them all, but we'll do our best. So should we take the first question?
Absolutely. Let's go for it. Well, actually, first, let's talk a little bit about where we are, what we're doing, what actually is the TensorFlow Dev Summit. So what is TensorFlow,
What
Lawrence?
is TensorFlow? Well, TensorFlow is as TensorFlow does, right? But, you know, I like to look at it as like really 3 main things. That number one, that's a set of programmer APIs that will allow us as developers to build machine learned models easily and quickly. The second is a set of runtimes. So for example, runtimes that will run on your supercomputer, runtimes that will run in the browser with JS, and runtimes like, for example, with TensorFlow Lite that run on mobile and embedded systems. And then number 3 is the ecosystem of tools around this, like TensorBoard to help you to see what's going on, and all the great stuff in TFX to allow you to kind of productize this. And what's more,
Oh, yes. So absolutely. The biggest announcement of this conference really is TensorFlow 2.0.
Indeed.
So the latest version of TensorFlow and a new addition to its bright and shining ecosystem. So I guess I could talk about that for a little bit.
Yeah.
Absolutely. So TensorFlow 2.0 is focused on ease of use, developer productivity, Keras, eager execution, all of those things that we've come to know and love through the last several iterations of TensorFlow development. We've got a lot of great tutorials and documentation that have been recently released. And really, it's all about being able to make you productive in as quick of a way possible and still giving you scalable, reproducible machine learning with just a few lines of code.
And what's more, it's all open source.
Absolutely. Everything's open source. And TensorFlow was open sourced about 3 years ago, right? Like we
Something
just
like
had
that,
the third
yeah.
birthday.
Third birthday recently. So did you go?
I was there. I was on the internet. I played with the tensors. I made them flow. That
Nice,
was, yes.
nice, yeah. So and with it being open source, of course, then community is just a huge part of what we do.
Absolutely. We couldn't do anything without the community.
And that's why we're doing this live stream, right? So to try and help to give back to that community that's given us so much.
Absolutely. And again, if you have questions, ask TensorFlow. The hashtag is how you would go about reaching us.
So one of the first questions that we're going to cover, and it's one question, I bet you've had it today, I get it almost every time I meet a TensorFlower, is it's great to be able to do training and like I'll usually do my training for a fixed number of epochs.
Yep.
But what happens when I reach my desired accuracy metric? How do I cancel training?
Right, like it doesn't make any sense to keep using compute if you've already gotten to a point where your boss would say, okay, cool, 99% accuracy, that's fine for us today.
So should we take a look at how we'd actually do that?
Absolutely, let's go for it.
So I've opened up a Colab here that you can see where I'm using callbacks. And callbacks are the way that you would actually achieve this. So at the top of my Colab here, you can see I have class, my callback. And on this one then, when an epoch ends in training, I'm able to take a look at the logs. And if the accuracy log, for example, in this case, is greater than 60%, because I have a really nice boss, he's really happy when my training's 60% accurate, then I would actually cancel the training. And then to be able to set that up, I'll just say, I'm going to create an object called callbacks, which is an instance of my callback class. And I love the way in Colab, when I double click, it actually highlights. I don't know, it's just a little thing that I like.
Absolutely.
And then down here on callbacks, I'll just say callbacks equals callbacks. And then when I actually do the training, and you know what, I'm going to really show off, and I'm going to make my runtime type to be a GPU, so it goes nice and fast. So this is FashionMNIST. Let's do a little bit of training on FashionMNIST with this one. And we're doing this live, so I'm connecting up to the VM. And here we go. Now it's actually training. It's getting ready to start. It's on the first
showing you
epoch.
your RAM and disk utilization.
Yeah. We're on the first epoch. The first epoch is progressing away. 60,000 images being trained. And boom, I hit accuracy of 83.
That's pretty good.
In just one epoch, right? But we can see now that it actually reached 60% accuracy, so it canceled the training. So callbacks are your friend if you're doing this. Certainly when you're learning, when you're experimenting. I used to, before I learned about callbacks, I keep saying collabs. Before I learned about callbacks, it's like I would like set something up to train for like 100 epochs and then go to sleep and then wake up the next morning and found like after 3 epochs it had done its job and I'd wasted my time. So use callbacks, I think, would be the answer to that.
Absolutely. Keras callbacks are incredibly valuable. It doesn't just apply to accuracy either. There are a bunch of additional metrics that could be useful for your particular workflow. And this code also would work in TensorFlow 2.0. So
Absolutely.
It's Keras. Gosh, I love Keras.
Keras, yes.
Yeah.
This is a Keras love affair right now. And actually, one of the really neat things about Keras that you may not realize, and we've been talking about TensorFlow 2.0, is that the same code that you write for TensorFlow 1.x is the same code for 2.0, but what's going on behind the scenes is that it's executing eagerly in 2.0 instead of with graph mode. So even though this Colab, I think I'm running 1.13, this code will actually still run in 2.0 without you modifying the code.
Absolutely.
All right, so should we take the next question?
Oh, cool. So our next question is from Twitter, it looks like. And what about all the web developers who are new to AI? Does the version 2.0 help them get started?
Oh, web developers.
There's some, oh man. So I just got finished talking to 2 of the folks on the TensorFlow JS, and you just pulled it up, the TensorFlow JS team, about all of the cool new demos that they've seen arise from the community. It's really such a vibrant ecosystem of artists and creators that are using browser-based or even server-based tools now to create these machine learning models, training and running them.
Yep. So I mean, I think for web developers, there's a whole bunch of ways that you can get started with this. Okay, so you've mentioned TensorFlow JS. So let's talk about that for a little bit first. The TensorFlow JS, it's a JavaScript library, and this JavaScript library will allow you to train models in the browser as well as executing them. And that actually blew my mind when I first heard about it.
The node bindings, right? Like being able to use the GPU inside your laptop with, you know, Google Chrome or your favorite flavor of browser to train a model. Like that is absurd. And
it's sci-fi now, right? So,
yeah, it is. We live in the future.
So like you said, node bindings as well. So like with Node.js, so it's not just in-browser JavaScript, it's also server-side JavaScript with Node, right? And am I supposed to say Node or Node.js? Or I'll say Node. I'll say Node. So, and then, of course, there's, by the fact that it is in Node, one of my personal favorites. Are you familiar with Cloud Functions for Firebase?
I'm not. Tell me more.
Okay,
I'm intrigued.
Yeah, so I used to work on the Firebase team, so a shout out to all my friends in Firebase.
All right, I'm leaving.
You know?
No, I'm just kidding. I've heard so many good things about Firebase.
So it's for mobile developers and for web developers. And one of the things that Firebase gives you are these things called Cloud Functions for Firebase. I've called up the web page here with the URL. But in summary, what they do is that they allow you to execute functions on a back end without you needing to maintain a server infrastructure and allow you to execute these in response to a trigger. So a trigger might be, for example, an analytic event or a sign-in event.
Or you get new data and you need to process it.
Bingo.
Man, I should try
You
this
know?
out for machine learning stuff.
So now, like the fact that they run JavaScript code Node on the back end, now it's a case of you could actually train models in a cloud function, which just for me.
That's amazing.
So yep, web developers, there's lots of great options for you. However it is you want to do it, in the browser, on the back end, in mobile, that kind of stuff. Hopefully there's lots of great stuff that you'll be able to get started with.
Absolutely. And the question about TensorFlow 2.0 and whether it gives additional tools for application developers, I think it would mostly be in terms of those codes and tutorials that we were mentioning before. We've also released some courses. So it's easier than ever to get started. And the models that you create using Saved Model can be deployed to TF Lite, to TensorFlow.js, to wherever.
And the important thing is we've been talking a lot about Keras, this thing that we love, and the Keras layers are supported in TensorFlow.js. So it's not just for Python developers. If you're a JS developer, you can define your layers.
And an R developer. Like they have Keras for R, which is awesome. It was created by JJ Allaire and Francois Chalet. They have a book out about it.
Nice, nice, cool. So web developers, lots of options for you.
Yeah.
Right? Yep. So shall we take the next question? And this looks like it also came from Twitter. And it's, are there any TensorFlow.js transfer learning examples for object detection?
So TensorFlow.js is popular.
TensorFlow.js.
We have learned.
Yes, so object detection is, so how do we answer this one? Okay, so it depends on what you mean by object detection, because in Google we talk about object detection. We use that specific term for in an image where you got lots of objects and you put bounding boxes around them, right? Right now there are no samples for that.
No, there aren't. But, and lovely thing is that the community is incredibly adept at creating TensorFlow.js examples. So example, the Taropa's CodePens. And then also Victor Dibia, a machine learning Google developer expert, had a great recent example with using it to track hand movements in a browser.
Nice.
So if anybody wanted to create an object detection
I hear you
example,
have an incentive.
I do. I have a collection of limited edition TensorFlow socks and shirts. And I would be delighted if you create any sort of example using TensorFlow.js or TensorFlow 2.0 to send you a bright, shiny pair of limited edition socks.
And they're limited edition classics because they have the old logo, not the new logo that you're sporting today.
Not the new logo, with but the old Gödel Escher box style one. So.
I love them both, but like, so the question though was really about transfer learning, and I think one of the things is that even though we don't have a demo of transfer learning with object detection, I'd like to show a demo of transfer learning with being able to detect a single item within a frame. So to do, we call that an image classification. So can I roll the demo? Is like,
Please do. Are you gonna do your
I'm
favorite?
Gonna do Pac-Man.
You are.
I'm a child of the 80s. I love Pac-Man. If you look carefully, it says actually loading MobileNet now. So what's happening is that just downloaded the MobileNet model. So what I'm going to do is I'm going to add some new classes to the MobileNet model and then use transfer learning to get them.
There it goes.
So do you want to do it?
No. Go for it, dude.
All right.
So
Pac-Man, right? Old arcade game. You move up, down, left, and right, and you try and run away from the ghost. So I'm going to try and train it to move up when I point up like this. So I'm holding it down and I'm gathering a bunch of samples. There are about 50 samples. And then when I go right like this, I didn't really think this one through though, because then turning left is going to be hard, but bear with me. And like 50. And maybe I'll do left like this and get my head out of the way. And, you know, a few samples like that. And then down will look like this. Hopefully these aren't rude gestures in some country. And something like that. Okay, so I've now picked like 50 samples of these. And I'm going to retrain this model in the browser with transfer learning. So if you look over on the left here, my learning rate, my batch size, I'm just going to train it for 20 epochs. And I'm going to start training, and we'll see, it starts going quickly. You see my loss started at 4, and then went down, 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 down. Now it's at 0. So it's like, wow, it's probably a digit beyond the 6 digits. It's never actually at 0. But we see we have a very low loss, so now we can actually give it a try. So let me see if I can avoid getting eaten by ghosts. So I'm going to start playing the game, and I'm going to move left. And you can see the bounding box around it kind of shows that I'm up. Yeah, up. No. Okay. Up. Right. No, go right.
No.
Oh, no. I'm watching the screen instead of watching Pac-Man. But we can see now that I've actually trained it. Let's try going right this time. Come on. Right. Right. There we go. And up. It thinks it's down. There we go. Up and right. Ah! And we see, I'm not very good at this game. I wasn't even good at it with the joystick.
You're just using this as an excuse to play Pac-Man all day, aren't you?
Exactly. But there's just a great example of using transfer learning. So if you can take this sample apart, and we have some other samples that are out there for transfer learning in JavaScript, so you can just see how easy it was for us to be able to extract the features from MobileNet and then retrain it. It's actually moving as I'm talking here on my gestures to be able to use that. So enough fun with Pac-Man. Shall we move to the next question?
Absolutely. So, and I'd also want to point out that transfer learning can be used for a variety of use cases other than just images too. So, so make sure to check out all of the great examples that we've got listed on the website.
Sounds good.
And the next one also looks like it was from Twitter. Twitter must be very popular.
I like Twitter.
I love Twitter. Hi, dear Ask TensorFlow.
Oh, we have to respond to this one because there's a dear Ask TensorFlow.
I'm awesome. We're dear. Are you going to publish the updated version of TensorFlow for Poets tutorial from Pete Warden, implementing TF 2.0, TF Lite 2.0, and a lot of other shenanigans?
Yeah, the neural network API.
Yeah.
Faster inference on Android.
Yeah, and I love Pete Warden's code lab on TensorFlow for Poets. He also had a great talk today.
Oh, I didn't get to see it, so.
Yeah.
I've been in here preparing.
Yeah, it was wonderful. You'll want to make sure to catch it again. It was all about creating tiny models and putting them on tiny computers.
Nice.
So mobile and embedded devices. But
Nice.
do you want to take this question?
Sure. So the TensorFlow for Poets code lab, at some point we will update it. I don't think there's an updated version available right now. But one of the things that I really liked about the TensorFlow for Poets code lab was it got me building a model very quickly that I could then use on a mobile device. But the downside of that, the drawback of that, was it was a bunch of scripts that I ran, and I didn't really know what was going on with them. So one of the things that we've been doing is that we've decided to get a whole bunch of new TensorFlow Lite examples and put them online on the site, and I have them on here. So there's 4 new ones: gesture recognition, image classification, object detection, and speech recognition. And what's nice about these is they're all open source. They're both Android and iOS, and they include full instructions on how to build them for yourself. The image classification one is really fun. I'm actually going to try to run that in my, whoops, I don't want Bitly. I actually want to try and run that in my Android emulator. And so we can see it running in an emulated environment.
Absolutely.
So let me get that started. Oh. We can see it being cached. So, so for example, now here I'm actually running it, and it's doing a classification of what's in the background. Like if I hold up a water bottle, whoops, this way, you know, see if it, there we go. See, it actually detects it's a water bottle. Now this is running in the Android emulator, okay? This is using TensorFlow Lite, and this is the sample that's on there that basically does the same thing that you would have seen in TensorFlow for Poets, where it's using MobileNet and building an application around MobileNet. But if you look, even running in the emulator, I'm getting inference times in like the 170 milliseconds.
It's
How
so
cool
fast.
is that, right?
Yeah.
So,
the ability to be able to take large-scale models and sort of pull them down to a manageable size on a mobile or an embedded device is huge. I'm really excited to see what TensorFlow Lite does this year.
yeah, so we're working on a bunch of new tutorials. Those samples are out there. If you take a look at their GitHub page, you'll see that there's details on how it's built. Let me just go back on here. So for example, if I say explore on Android, you'll see there's details on how it's built, how you can put it all together, how you can compile it. You don't need to build TensorFlow in order to use TensorFlow Lite. That was one bit of confusion that folks had in the past. Now it's just a case of what you add to your build.gradle, or if you're an iOS developer, the pods that you add, that kind of stuff. So you can go and like start kicking the tires on these applications for yourself.
Excellent.
Alrighty, and but we will have more code labs, and I would love to get Pete's TensorFlow for Poets code lab updated, hopefully for I/O.
Yes. And make sure to watch Pete's talk if you happen to miss it.
It must
Lawrence.
be a really good talk.
I'm telling you, it was so good.
Nice. Well,
people were talking about putting models on Commodore 64.
On a Commodore 64?
I'm telling you, man. Like, and
Wow.
yeah, it's nerding out a little bit.
Oh, okay, well, that's why we're here, right? So, cool. Do we have time for one more question before break? Okay, so we're heading to a break now, and so Paige and I will be back after the break with the rest of your questions. Please keep asking them on the live stream, and please keep asking them in social media. Like I said, anything that we can't get to, we will try to get to offline, and we'll reach out back to you. So
Absolutely. So super excited to have you here. Super excited to be at the TensorFlow Developer Summit.
Yep, and we'll see you back here in just a few minutes.
Yeah. Welcome back. I'm Paige Bailey, and this is
Lawrence Moroney.
And we are here to answer all of your Ask TensorFlow questions at the TensorFlow Dev Summit. So if you have any questions, please submit them to social media with the hashtag AskTensorFlow.
And we'll answer as many of them as we can, but any that we can't get to today, we'll try to reach out to you later to answer them.
Absolutely. So let's get started with the first question.
Okay, so shall I try this one?
Yeah, absolutely.
So this one I think came on Twitter from Hugo, and it said, once I installed TensorFlow GPU, import didn't work for me. Been trying to use it, but has been unable to do so. It fails to load native TensorFlow runtime. I remember seeing this one, and actually it was on YouTube, and it was in response to one of my videos about pip install TensorFlow GPU in Colab, because once upon a time in Colab, you had to pip install TensorFlow GPU to be able to use it, and now if you try to do that, you end up having some issues. And the reason for that is actually really good, and it's good news, and it's because you don't need to do it anymore.
Excellent.
So if we switch to Colab for a second on my laptop, I can show you. This was the notebook that I was showing earlier on. And all you have to do if you want to use GPU in Colab is just change your runtime type, pick GPU as the hardware accelerator, and now you don't need to pip install TensorFlow GPU. It actually does it for you under the hood behind the scenes. So it's really, really cool. And that's why earlier I was able to train this so quickly, because I was actually using the GPU. And as you can see, there's no pip install GPU on here.
Excellent. Right? So whenever we were initially testing TensorFlow 2.0, we had a kind of similar issue as well with the GPU install, in that you needed specific CUDA drivers. But now CUDA 10 is supported in Colab as well. So Colab is a great experience if you're using a GPU or if you're using any other accelerated hardware.
Yep, and a pro tip going forward as well, if you want to do GPU stuff, because this was something that I ran into a number of times when trying to use the GPU, was that you always have to carefully take a look at the version of CUDA and CUDNN that you're using, because I made the mistake that I just went to the vendor's website, I downloaded the latest versions, I installed them, and then I saw TensorFlow was actually supporting a slightly earlier version. So if you do get an error when you're trying to use GPU, just take a look at the version of the driver that it's looking to support, and then from the vendor's website, download that specific version.
Yep. Driver issues.
Driver issues.
They're always a treat, right?
Exactly, exactly. And it's like it's one of the things that makes our job interesting. Right?
Absolutely.
All right, so shall we take a look at the next one?
Yeah, let's go. Oh, AD Kumar. So AD Kumar had at least 8 excellent questions on Twitter, and
AD wins the volume award.
He absolutely does, and we'll get to all of them. Not in this sort of Ask TensorFlow segment, but let's focus on just one for today, and then answer the rest offline.
Yeah, and I think a lot of them were really about file formats and how do I use different file formats. So shall we drill into that?
Absolutely. So the question is, which is the preferred format for saving the model going forward? Saved model or something else? And if we look at the laptop, we can take a gander at one of the slides from the keynote this morning, really showing that Keras is a first-class citizen in TensorFlow 2.0, and saved model is at the heart of every deployment. So here you can see saved model being used for TensorFlow serving, for TensorFlow Lite, for TensorFlow JS, and lots of other language bindings. So really, we're pushing for the saved model.
And if you focus on saved model, you can't go wrong.
Yes, absolutely. Right, it's a lot easier to use than some of the other deployment options that we'd seen before.
Yeah. So I think the guidance would be in the recommendation, not just for AD, but for everybody else. And when you're thinking about saving out your models, take a look at saved model, consider using saved model, and as a result, it's like not only is the advantage of the file format, but just how it's supported across all of these things.
And an excellent point of TensorFlow 2.0, I'm just going to keep selling it, is that we have a number of code samples and tutorials available today about how you can deploy your models with saved model.
Yeah, and I personally found, like from playing with some of the TensorFlow Lite stuff in 2.0, saving as a saved model and then going through the conversion to the TF Lite process, it was a lot easier for me than in previous iterations where I had to use like Toko converter and all that kind of stuff. So it's like, it's really been refined. We're really iterating on that, and I think it looks really cool. So.
Yeah.
All right,
Excellent.
So thanks for all of those questions, AD. There's some great stuff in there. We will try to answer some of the rest of them, but understood that most of them were focused around the file format, and hopefully Save Model will help you. All right.
Perfect. So let's go to the next one.
So this next one comes from Eli Gakuba, and asking, is it possible to run TensorBoard on Colabs? And I know this made Paige really happy.
Oh, dude, you were going to be so delighted.
Because before TensorBoard was running on Colabs, you know, we were like talking about it. We really wanted on Colabs.
It was so painful. Like if you wanted to get it working in a Colab notebook or in Jupyter, you ended up using a tool like ngrok, and that was kind of not approved by our bosses or in general. But yes, so the good news is that you can run TensorBoard in Colabs.
And when it was first announced internally in Google before it was publicly announced, we all got this email from Paige, and it was full of all these smiley emojis and hearts. You know, it was like, Ely, thank you for the question, because I think you've made Paige's day.
Excellent. And so you can see here in the Colab, I'm running through and sort of downloading some files in the hope that we could play with it a little bit. But here you can see it actually working. You should be able to do different operations like smoothing, changing some of the values, and then also making, using the embedding visualizer directly from your Colab notebook in order to understand kind of your accuracies and to be able to do model performance debugging. Another nice thing that the team has been working very, very hard on is that you don't have to specify ports. So you don't have to remember, if you wanted to have multiple TensorBoard instances running, that you were using, what is it, 6006 or whatever for another. It just automatically selects one that would be a good candidate and creates it for you. So the team is phenomenal. If you have any interest whatsoever in TensorBoard at all, I suggest stalking their PRs like I do, because that's how I found out that TensorBoard got added to Jupyter Notebooks and also to Colab.
Yep.
But yeah, it's so excited, and we'll have this link in the documentation for the video as well, the little notes underneath for you to go and play with too.
And I do have to say, it's so great to have a PR stalker in our group.
Dude, I get push notifications to my phone. It's a problem. But yeah, they've been doing such great work.
Yep. So the question is, yes, TensorBoard is working in Colab.
And also Project Jupyter Notebooks. Use it wherever.
Yep.
TensorBoard everywhere.
TensorBoard everywhere, and we all love TensorBoard. I haven't really played with it that much, but do a lot of the plugins also work?
So right now, so TensorBoard really is a collection of these different visualizations. So you can see scalars like your accuracy, you can see histograms, you can see embedding visualizers, which allows you to do clustering, like that great MNIST example from the Dev Summit a couple of years ago. Moving it around.
I play with that all day.
Yeah, it's beautiful. And then also Beholder, which was created by a community member. The plugins, it's so funny you mention it. A couple of our GSOC, Google Summer of Code projects this summer are focused on getting additional visualization plugins added to TensorBoard. So in addition to the What If tool, in addition to Beholder, you could make your own TensorBoard plugin.
So while I could geek out about this all day, I think we should move on to some other questions.
Are you sure we can't geek out about this all day?
Yeah, can we extend the stream for 3 or 4 hours? So the next question that came in from Amar Hussain Harandi, how would you use feature columns with Keras?
And I know you know the answer to this question.
But I know that's a particular passion of yours, that you're working with estimators in Keras. So for the folks who are watching, feature columns are really part of estimators, right? They're a way of like really getting your data efficiently into estimators. And with people like saying, hey, it's all there in estimators, what about Keras?
Yeah.
And you've been working on some great stuff around that, right?
I have, but I know that your YouTube channel has a series from Carmel, who spoke earlier today.
Yeah, so Carmel is our engineering director, like for high-level APIs, and she has this great series around high-level APIs for TensorFlow. And so like really, really teaching you how to use the high-level APIs. And Carmel is working actively, and her team are working actively for parity of things like feature columns in TensorFlow 2. I'm not sure if it's fully there yet in the alpha. I haven't checked into it yet. But yeah, it's on the way if it's not there already, so you should be able to use them in Keras.
Yes, and we're also in the process of building out, if you wanted to migrate your models from using estimators to being more of a TensorFlow 2.0 format with Keras, I am currently in the process of building a migration guide. So if you have any interest around that, please feel free to reach out, and we're excited to get that released pretty soon.
I'm really excited to see that personally, because the very first stuff I did in TensorFlow was with estimators before I learned Keras.
Yeah.
And I really want to go back and kind of start changing them to use Keras without rewriting them. So.
Absolutely. Keras is just friendlier to work with, I feel.
Yeah, so they're both great estimators where it really gives you the power. Keras, great for beginners, so it's like, hopefully we'll get the best of both worlds. So it's like, so shall we take a look at the next question?
Yes.
And Jeff Thomas asks, looking for some simple data sets for testing and comparing different training methods. Looking for new data sets, like MNIST is great, Fashion MNIST is great, but after a while, people want something new and fresh, right?
Yes.
So what can you think we can say to Jeff?
We could tell them about TensorFlow datasets.
And there's a great blog post right here about it.
Yes, it is. And TensorFlow datasets is really about creating those data ingestion pipelines for you to be able to easily use a variety of datasets with all of your deep learning and machine learning models with just a few lines of code. So if you're familiar with scikit-learn and all of its sort of nifty data ingestion practices, this feels very similar. It's very easy to do training and testing splits and verification splits. And we have a lot of data sets readily available right now for you to go and explore. Another thing that I would especially like to call out is a member of our community. So anybody can make your data famous, right? Like if you have a data set that you're using in your research lab, if you have like a bright and shiny CSV that you think would be a cool add to the structured section.
I've never heard a CSV called bright and shiny before.
Well, you know, everybody uses them. So, but it's the one of our community members, Andrew Kondrick, who's an undergrad researcher at Stanford. He added this CheckSpurt data set from his lab, 200,000 chest radiograms from the Stanford ML group, and he was able to do it in like less than a day. Like it really is just as simple as take the template format for images or for audio or whatever you're using, add some additional metadata for the data set, change potentially the types for some of the features that you're using within it, and voila, there you go.
You're off to the races.
Absolutely, and you can make your data famous.
Yep, and one of the really important things about it, particularly if you're getting started or if you're learning, is that if you take a look at a lot of the samples pre-TensorFlow data sets, there tends to be lots and lots of code about download your data, unzip it here, you know, label it like this, put these files in these folders, or take your CSV and make these features. But when it's in TFDS, it's like 1 or 2 lines of code, and the data will just get sorted into training and test sets for you, that type of thing. And so I think for learners in particular, I found it like really, really exciting, because I didn't have to go through 100 lines of code before I got to the neural network.
And also data science-y people. Like so much of creating and training a model is understanding the shape and the format and sort of the statistical distributions. And this is really helpful.
Yep. So that's all we have time for. We're going to take a break, and we're going to be taking a look at some more of your questions during the break, and then we'll be back in just a few minutes to start answering them. So thanks very much. Welcome back, everybody, to the live stream where Paige and I are going to be answering questions that you've posted on social media, on the live chat, on Stack Overflow, and anywhere else that we could find them. If you want us to answer some of your questions, please hashtag #AskTensorFlow.
Absolutely. And if we don't get to your questions right now, today, we will in further episodes of Ask TensorFlow. So get excited and keep asking, even if we don't necessarily get to them.
Yep, exactly. We've had so many, we can't get to them all today, and it's a great problem to have. Right?
Yeah, it absolutely is.
So we were just actually discussing in the break that we have a show on YouTube called Ask TensorFlow, and we're going to actually take a lot of these questions and put them into the show. And so, like we say, please keep asking, and thank you so much for being engaged. That's what makes a community, right?
It does.
So shall we take a look at the first one that came in? Was from Alpha Arthur. Can I ask about any pre-built binary for the RTX 2080 GPU on Ubuntu 16?
That is very specific.
That is very specific, so I like specific questions,
yes.
Even if I can't answer that. But so in this case, so the pre-built binaries for TensorFlow tend to be associated with a specific driver from NVIDIA. So like the version of CUDA that we support or the version of CUDNN that we support. So my recommendation would be if you're taking a look at any of the pre-built binaries, take a look at what driver or what version of the driver you have supported on that specific card. I'm not an expert in NVIDIA cards, although I love them, so I don't really know what's supported by that card, Arthur. But if you go over here, like on my laptop, I have I've called up like some of what NVIDIA say as their TensorFlow system requirements and the specific versions of the drivers that they support. And the one gotcha, and we had this in the last segment as well, that I find when working with GPUs is that it's easy for you to go to the driver vendor and download the latest version, but that may not be the one that TensorFlow is built for, or the one that TensorFlow supports. So just make sure that they actually match each other.
Yes.
And you should be good to go even with that particular card.
Yes, and if you have warm feelings and excitement about builds in general for TensorFlow, we have a great special interest group specifically focused on that called SigBuild.
SigBuild.
SigBuild. So strongly suggest going to the community section of our GitHub and checking out the SigBuild listserv and sort of joining it and joining our weekly stand-ups.
Right. So thanks, Arthur, for that question. And then the next question is a really funny one, I think. How many times have you been asked this today?
Oh my God, at least 12, at least. Oh man, and then the other flavor of it is, well, is this particular symbol that I use all the time, is this going to also be supported in TensorFlow 2.0? And if not, what has changed?
Yeah, I mean, people have invested so much time building stuff in TensorFlow 1.x. They don't want it to be deprecated. They don't want it to go away.
Understandable, understandable.
So how do we answer? Do my TensorFlow scripts work with TensorFlow 2?
Yes. So the sad fact is that probably not. They would not work with TensorFlow 2.0 out of the box. But we have created an upgrade utility for you to use. It's automatically downloaded with TensorFlow 2.0 whenever you download it. For more information on it and what in particular it's doing, you can check out this Medium blog post that I and my colleague Anna created, as well as this upgrade to TensorFlow 2.0 video. It goes through and with GIFs, which is the best communication medium possible, shows you how you can use the upgrade script on an N file. So any sort of arbitrary Python file or even Jupyter notebooks. One of our machine learning GDEs created an extension that will allow you to do that as well. And it'll give you an export.txt file that shows you all of the symbol renames, the added keywords, and then also some manual changes if you have to make manual changes.
Cool.
Usually you do not. So to see this in action, we can go and take a look at this particular text generation example that we have running a Shakespeare, takes all of the corpus of Shakespeare text, trains against the Shakespeare text, and generates something that the Bard could have potentially written, should he have had access to deep learning resources.
I know you all and will uphold a while this unyoked humor of your idolatry.
I did not know you knew Shakespeare.
I actually played Henry IV in high school.
That's amazing. I was.
That's why I love this notebook.
I was Beatrice in Much Ado About Nothing.
Oh, cool.
Yeah.
So while we're on Much Ado About Nothing, maybe we should get back to the notebook.
Yes. So here's what it looks like in Colab form, text generation using an RNN with eager execution. You could export the Python file, and then to upgrade it,
we got to reconnect the runtime
this
first.
This is true. So starting it. It looks like the requirements have already been, we can check to see that we're using TensorFlow Alpha. And then, like I mentioned before, all you would have to do is preface this with a bang, TF upgrade v2. The name of the Python file is text generation. I want to create an upgrade, shift enter. It does its upgrading magic, and very quickly tells me all the things that would need to be changed to make it 2.0 compatible. And creates that file for me off to the side. So now, if I wanted to run this model, it should be able to train as it would. So let's just check to make sure that would be the case.
And I think a lot of the errors that you're seeing here, it's more just renamed APIs rather than breaking changes within the APIs
This
themselves.
is true. Right? So you can see that you have some renames and some additional keywords.
Yep.
But yeah, and so for more information about that and to see it running in a video, you can go and take a look there.
Sounds good. And I saw you have some like handy dandy GIFs in there.
Yes,
Right,
absolutely.
So are there any GIFs for those of us who don't say GIF? Sorry, I had to work that joke in.
Oh, well, I'm PB, so peanut butter, it automatically works.
Exactly, sounds good. So when it comes to upgrade, there are a few little gotchas, basically, in summary, but hopefully this blog post and your video and all the stuff that we're doing will help you get around those gotchas.
Yeah. And even more amazingly, the community that you were mentioning before, we've had such an interest in testing TensorFlow 2.0 and trying it out against historic models that we've formed a weekly testing stand-up. And also we have a migration support hour that's being implemented with the internal support hour.
Right.
So if you have an external group to Google that's interested in upgrading your models, please join the testing group and we can get you situated.
Yep. And a lot of stuff that we've seen, like in Keras models, for example, Carmel had that great slide where she was training Fashion MNIST.
And the code is the exact same.
It's exactly the same.
This
so
is
while
true.
there might be stuff changing under the hood, it's like a lot of the surface level code that you're going to be writing in Keras at least isn't changing.
Yeah. If you've used Keras, you're probably not going to have any problems.
Yeah. Yeah. So good stuff. So shall we move on to the next question?
Yes.
I know we could talk about 2.0 all day, but
Yes.
Okay, we just mentioned Keras and it appears, so.
So I guess I could ask you this question.
Okay.
Hopefully you know the answer. What is the purpose of keeping estimators and Keras as separate APIs? Is there going to be something native to Keras models that allows a distributed training a la train and evaluate?
Okay, so the purpose of keeping them, I think, is there's many purposes, right?
Yeah.
So I think for me, the main purpose that I would like to think of, though, is one that is because a lot of people are using them.
Including internal Google teams that would tar and feather us if we removed them quickly.
So it's like, and so when it comes to like estimators are really great for large-scale training.
Yes.
Right, and it's like a lot of time, if you're doing a lot of that large-scale training, it's like really keep going with estimators because they're great. You know, like I said, when I first started with TensorFlow, I started like with estimators because I couldn't figure out what a node was in a neural network, and there were all these concepts that I had to learn, and I had just this simple estimator that I could use to do like a DNN or something like that. So you know, they're there for a reason, and they're staying for the reason. Keras is one of the things that, from the point of view of making life easier for developers, that we've really been doubling down on in TensorFlow 2, and things like we just spoke about. The code is the same between 1 and 2, and it's the layers API, I think, makes it super simple for you to design a neural network. And then the fact that you can go low level beyond that and, like, you know, define your own layers really gives you, allows you to drive stick instead of driving automatic.
Absolutely. One of the beauties of Keras in 2.0 is that you have Keras the way that you're probably familiar with using it. And then if you need to do additional customizations, there's a subclassing component.
Yep.
And then if you need to go even lower, then we have something called TF module, and we even expose some of the basic, most core ops of TensorFlow as well. So really, at any sort of level you want to interact with the API, you can.
Yep, and I think there was another part of the question was then around distributed training. Sorry, it scrolled off, so I can't see it now. But there's there's something called distributed strategy, right? In with Keras and with TensorFlow 2, and the whole idea behind that is to allow you to be able to distribute your training, maybe across multiple GPUs on the same machine, maybe across multiple GPUs on different machines, maybe across TPUs spread all over the place, that kind of thing. So distribution strategy is really all about that. So to help you with that. So estimators and Keras, we love them both. They're both still there. Hopefully this is something that will help you with a question. And I think we've got time for just one more.
Absolutely.
So, this is a Paige question.
This is totally a me question. I am the Python person. So ask TensorFlow, when will TensorFlow be supported in Python 3.7 and hence be accessed in Anaconda 3? So I can certainly answer the Python 3.7, and also I would love to speak a little bit more about support for Python going forward.
Please.
So to answer the 3.7 question, I'm going to bounce over to our TensorFlow 2.0 project tracker. These are all of the standing issues that we have when doing development for TensorFlow 2.0. It's transparent.
I see your avatar.
Yes, I have filed many issues. And all of them are transparent to the public. So if you ever want to have a sort of context on where we stand currently and what we have yet to do, this project tracker is a great way to understand that. But let's take a look at 3.7, and there we go. So in process of releasing binaries for Python 3.5 and 3.7. That's issue 25.420, and it's going a little bit off the screen, 429. But you can take a look at that issue and see that it's currently in progress. There's not really an ETA, but it's something that we want to have complete by the time that the alpha RC is released.
Yep.
So that is wonderful to see. There's also a website called Python 3 Statement. I think it's python3statement.com. Maybe it's .org. There we go. Cool. So TensorFlow has made the commitment that as of January 1st, 2020, we no longer support Python 2, and we have done that with a plethora of our Python community. So TensorFlow, Pandas, Scikit-learn, etc. We are firmly committed to Python 3 and Python 3 support.
Nice,
So you will be getting your Python 3 support. And we're firmly committed to having that.
And the nice thing about the issue tracker is it's not going to be a big, hey, we have it, coming at some random point in the future. It'll be a case of it's totally transparent. You can keep an eye on what we're doing with
and you can see people commenting and our engineers commenting back with like, yeah, man, I totally ran the thing last night and it's almost there. One more test.
Sounds good. Okay, I think that's all we have time for. So again, remember, #AskTensorFlow on Twitter, Stack Overflow, on YouTube, on the YouTube live stream.
Send us a carrier pigeon, if that's your preferred method of communication.
I prefer owls, but that's,
owls are also nice.
Yeah, so like if you have any other questions, please ask them. We'll do our best to answer them. We'll be putting together a lot of new videos and a lot of new shows on youtube.com/TensorFlow. So whatever you do, don't forget to hit that subscribe button. All right, and thank you so much, and thanks for being engaged.
Thank you.
Yeah.
Airbnb is an online marketplace. We have over 5 million different homes in 81,000 cities, which equates to hundreds of millions of photos, making it possibly the largest collection of images of homes in the world today. When a guest decides to select a home, one of the biggest influences in their decision is a diverse set of images. But a lot of times hosts will take a lot of pictures of a single room and forget to take pictures of the other rooms.
They also have the option to add captions, but a lot of cases they're totally off.
We were faced with a challenge of identifying what's actually in these pictures and present them properly on the site. That's one area where machine learning excels. But the real challenge was one of scale. We had upwards of 500 million images to get through. It was going to take months to really go through all of these.
Using TensorFlow, we were able to speed up the process and deliver a reasonable model within days. BigHead is Airbnb's machine learning platform. We had the idea of making it very agnostic to different ML frameworks, and so we leveraged TensorFlow to train the model, and then BigHead helps with the model lifecycle, the feature management, and then TensorFlow serving to help serve the model results.
Before you think about which tool to use, you first think about which model to use, right? And we did research on this. We find that ResNet 50 was one of the state-of-the-art performing models. We used that as the basic architecture.
We used TensorFlow's Keras APIs and serving and some of the distributed GPU computations. This ultimately led to a pipeline that we can deploy to go through hundreds of millions of images very quickly.
So the end goal is basically using these classifications of images to make sure that their first initial set of photos that they see aren't just a picture of the garage and bathroom, but it could be of the living room that's gorgeous, and the bedroom and the swimming pool. Future applications could be to detect different objects in homes, and if users decide to search on the website for specific amenity types, we can actually bubble that up to the surface.
If you like how Airbnb operates today, the reason was because of machine learning, because machine learning is almost everywhere in the company. Search ranking, pricing, predicting booking.
We're passing into the hundreds of models, so it's something I expect to keep growing.
And with a lot of these new frameworks coming out, we can make better experiences for our guests and better business decisions as well.
All right. Welcome back, everyone. That's a great case study. I know that some of our friends at Airbnb are in the audience, so let's give them another round of applause for that great work. My name is Clemens. I'm the product lead for TensorFlow Extended, the end-to-end machine learning platform that we built for TensorFlow. And we have a lot of exciting announcements, so let's jump right in. A lot of you may be familiar with this graph. We published this in a paper in 2017. And the main point that I usually make on this graph is that there's more to machine learning than just the training part. In the middle, the trainer piece, that's where you train your machine learning model. But if you want to do machine learning in production reliably in a robust way, you actually need all of these other components before and after and in parallel to the training algorithm. And often I hear sometimes from researchers, well, I really only do research. I only care about training the machine learning model, and I don't really need all of these upstream and downstream things. But what I would argue is that research often leads to production, and what we want to avoid is researchers having to re-implement their hard work in the model that they've built when they want to put their model into production. And that's actually one of the main reasons why we open source TensorFlow, because we really wanted the research community to build the models in a framework that we can then use and actually move into production. A second comment that I hear often is, well, I only have a very small data set that fits in a single machine, and all of these tools are built to scale up to hundreds of machines, and I don't really need all of these heavy tools. But what we've seen time and time again at Google is that small data today becomes large data tomorrow. And there's really no reason why you would have to re-implement your entire stack just because your data set grew, right? So we really want to make sure that you can use the same tools early on in your journey so that the tools can actually grow with you and your product with the data so that you can scale the exact same code to hundreds of machines. So we've built TensorFlow Extended as a platform at Google, and it has had a profound impact to how we do machine learning in production and into becoming an AI-first company. So TFX really powers some of our most important alphabet companies. Of course, Google is just one of the alphabet companies. So TFX is used at 6 different alphabet companies. And within Google,
It's really used with all of the major products, and also all of the products that don't have billions of users that are not on this slide. And I've said before that we really want to make TFX available to all of you, because we've seen the profound impact it has had on our business, and we're really excited to see what you can do with the same tools in your companies. So a year ago, we talked about the libraries that we had open sourced at that point in time. So we talked about TensorFlow Transform, the training libraries, estimators, and Keras, TensorFlow Model Analysis, and TensorFlow Serving. And I made the point that back then, as today, all of these are just libraries. So they're low-level libraries that you still have to use independently and stitch together to actually make work end-to-end for your own use cases. Later that year, we added TensorFlow Data Validation. So that made the picture a little more complete, right? But we're still far away from actually being done yet. However, it was extremely valuable to release these libraries at that point in time, because some of our most important partners externally has also had a profound impact with some of these libraries. So we've just heard from our friends at Airbnb. They use TensorFlow Serving in that case study that they mentioned. Our friends at Twitter just published this fascinating blog post of how they used TensorFlow to rank tweets on their home timeline. And they've used TensorFlow Model Analysis to analyze that model on different segments of their data, and used TensorFlow Hub to share some of the word embeddings that they've used for these models. So coming back to this picture. For those of you who've seen my talk last year, I promised everyone that there will be more. Because again, this is only the partial platform. It's far away from actually being an end-to-end platform. It's just a set of libraries. So today, for the very first time, we're actually sharing the horizontal layers that integrate all of these libraries into one end-to-end platform, into one end-to-end product, which is called TensorFlow Extended. But first, we have to build components out of these libraries. So at the top of this slide, you see in orange the libraries that we've shared in the past. And then in blue, you see the components that we've built from these libraries. So one observation to be made here is that, of course, libraries are very low level and very flexible. So with a single library, we can build many different components that are part of a machine learning pipeline. So in the example of TensorFlow Data Validation, we used the same library to build 3 different components. And I will go into detail on each one of these components later. So what makes a component? A component is no longer just a library. It's a packaged binary or container that can be run as part of a pipeline. It has well-defined inputs and outputs. In the case of model validation, it's the last validated model, a new candidate model, and the validation outcome. And that's a well-defined interface of each one of these components. It has a well-defined configuration, and most importantly, it's one configuration model for the entire pipeline. So you configure a TFX pipeline end-to-end. And some of you may have noticed, because model validation needs the last validated model, it actually needs some context. It needs to know what was the last model that was validated. So we need to add a metadata store that actually provides this context, that keeps a record of all of the previous runs, so that some of these more advanced capabilities can be enabled. So how does this context get created? Of course, in this case, the trainer produces new models. Model validator knows about the last validated model and the new candidate model. And then downstream from the validator, we take that new candidate model and the validation outcome. And if the validation outcome is positive, we push the model to the serving system. If it's negative, we don't. Because usually, we don't want to push a model that's worse than our previous model into our serving system. So the metadata store is new. So let's discuss why we need this and what the metadata store does. First, when most people talk about machine learning workflows and pipelines, they really think about task dependency. They think, there's one component, and when that's finished, there's another component that runs. However, all of you who actually do machine learning in production know that we actually need data dependency, right? Because all of these components consume artifacts and create artifacts, and as the example of model validation just showed, it's incredibly important to actually know these dependencies. So we need a system that's both task and data aware, so that each component has a history of all of the previous runs and knows about all of the artifacts. So what's in this metadata store? Most importantly, type definitions of artifacts and their properties. So in our case for TFX, it contains the definition of all of the artifacts that are being consumed and produced by our components and all of their properties. And it's an extensible type system, so you can add new types of artifacts if you add new components, and you can add new properties to these artifacts if you need to track more properties of those. Secondly, we keep a record of all of the execution of the components. And with that execution, we store all of the input artifacts that went into the execution, all of the output artifacts that were produced, and all of the runtime configuration of this component. And again, this is extensible. So if you want to track things like the code snapshot that was used to produce that component, you can store that in the metadata store as well. So putting these things together allows us to do something we call lineage tracking across all executions. Because if you think about it, if you know every execution, all of its inputs and all of its outputs, you can piece together a story of how an artifact was created. So we can actually, by looking at an artifact, say, what were all of the upstream executions and artifacts that went into producing this artifact, and what were all of the downstream runs and downstream artifacts that were produced using that artifact as an input. Now that's an extremely powerful capability, so let me talk you through some of the examples of what this enables. The first one is a pretty straightforward one. Let's say I want to list all of the training runs that I've done in the past. So in this case, I'm interested in the trainer, and I want to see all of the training runs that were recorded. In this case, I had 2 training runs, and I see all of the properties of these training runs. This is pretty straightforward yet, nothing new to see here. However, I just spoke about lineage. We can visualize that lineage and all of the information that we have. The first comment on this slide to make is we're working on a better UI. This is really just for demonstration purposes. But if you look at the end of this graph to the right side, you see the model export path. This is the specific instance of a model that was created. And as you can see, we see that the model was created by the trainer, and the trainer created this model by consuming a schema, transform, and examples. And again, these are specific instances, so the IDs there are not just numbering, they're like schema of ID number 4 and transform of ID number 5. And for each one of those artifacts, we also see how they were created upstream. And this allows us to do this lineage tracking and going forward and backward in our artifacts. And I just the narrative I used was walking back from the model, but similarly, you could look at your training data and say, what were all of the artifacts that were produced using that training data? This slide shows a visualization of the data distribution that went into a model. Now, at first glance, this may not be something like earth-shattering, because we've done this before. We can compute statistics and we can visualize them. But if you look at the code snippet, we're not referring data or statistics. We're referring to a model. So we say, for this specific model, show me the distribution of data that the model was trained on. And we can do this because we have a track record of all of the data and the statistics that went into this model. Right? We can do a similar thing in the other direction of saying, for a specific model, show me the sliced metrics that were produced downstream by TensorFlow model analysis. And we can get this visualization. Again, just by looking at a model and not specifically pointing to the output of TensorFlow model analysis. Of course, we know all of the models that were trained and where all of the checkpoints lie. So we can start TensorBoard and point to some of our historic runs. So you can actually look at the TensorBoard for all of the models that you've trained in the past. Because we have a track record of all of the models that you've trained, we can launch TensorBoard and point it to 2 different directories. So you can actually compare 2 models in the same TensorBoard instance. So this is really model tracking and experiment comparison after the fact. And we enable this by keeping a track record of all of this. And if you have multiple models, you can also look at the data distribution for multiple models. So this usually helps with debugging a model. If you train the same model twice or on different data and it behaves differently, sometimes it can pay off to look at whether the data distribution has changed between the 2 different runs. And it's hard to see in this graph, but here we're actually overlaying 2 distributions of the statistics for one model and the other. And you would see if there's a considerable drift between those 2. So all of these are enabled by this lineage tracking that I just mentioned. Another set of use cases is visualizing previous runs over time. So if you train the same model over time over new data, we can give you a time series graph of all of the evaluation metrics over time, and you can see if your model improves or gets worse over time as you retrain it. Another very powerful use case is carrying over state from previous models. Because we know that you've trained a model in the past, we can do something we call warm starting. So we can reinitialize the model with weights from a previous run. And sometimes we want to reinitialize the entire model or maybe just an embedding. And in this way, we can continue training from where we left off with a new data set. And another very powerful application of this is being able to reuse previously computed outputs. A very common workflow is to iterate on the model and basically iterate on your model architecture. Now, if you have a pipeline that ingests data, applies transformations to your data, and then you train a model, every time you make a small change to your model, you don't want to recompute everything upstream. There's no reason why you would have to re-ingest your data, recompute the transform just because you changed something in your model. Because we have a track record of all of the previous steps, we can make a decision of saying, your data hasn't changed, your transform code hasn't changed, so we will reuse the artifacts that were produced upstream, and you can just iterate much, much faster on your model. So this improves iteration speeds, and it also saves compute because you're not recomputing things that you've already computed in the past. So now we've talked about components quite a bit. Now how do we actually orchestrate TFX pipelines? First, every component has something we call a driver and a publisher. The driver's responsibility is to basically retrieve state from the metadata store to inform what work needs to be done. So in the example of model validation, the driver looks into the metadata store to find the last validated model, because that's the model that we need to compare with the new model. The publisher then basically keeps the record of everything that went into this component, everything that was produced, and all of the runtime configuration, so that we can do that lineage tracking that I mentioned earlier. And in between sits the executor. And the executor is blissfully unaware of all of this metadata stuff, because it's extremely important for us both to make that piece relatively simple. Because if you want to change the code in one of these components, if you want to change the training code, you shouldn't have to worry about drivers and publishers. You should just have to worry about the executor. And it also makes it much, much easier to write new components for the system. And then we have one shared configuration model that sits on top that configures end-to-end TFX pipelines. And let's just take a look at what that looks like. As you can see, this is a Python DSL. And from top to bottom, you see that it has an object for each one of these components, from example gen, statistics gen, and so on. The trainer component, you can see, basically receives its configuration, says that your inputs come from the transferred output and the schema that was inferred. And let's just see what's inside of that trainer. And that's really just TensorFlow code. So in this case, as you can see, we just use an estimator, and we use the estimator train and evaluate method to actually train this model. And it takes an estimator, and we just use one of our pre-canned estimators in this case. So this is a wide and deep model that you can just instantiate and return. But what's important to highlight here is that we don't have an opinion on what this code looks like. It's just TensorFlow. So anything that produces a saved model as an output is fair game. You can use a Keras model that produces the inference graph. Or if you choose to, you can go lower level and use some of the lower level APIs in TensorFlow. As long as it produces a saved model in the right format that it can be used in TensorFlow serving, or the eval graph that can be used in TensorFlow model analysis, you can write any type of TensorFlow code you want. So if you've noticed, we still haven't talked about orchestration, right? So we now have a configuration system, we have components, and we have a metadata store. And I know what some of you may be thinking right now. Is he going to announce a new orchestration system? And the good news is no, at least not today. Instead, we talked to a lot of our users, to a lot of you, and unsurprisingly found out, whoops, can we go back one slide? Yeah. Unsurprisingly found out that there's a significant installed base of orchestration systems in your companies. We just heard from Airbnb. Of course, they developed Airflow, and there's a lot of companies that use Kubeflow. And there's a number of other orchestration systems. So we made a deliberate choice to support any number of orchestration systems because we don't want to make you adopt a different orchestration system just to orchestrate TFX pipelines. So the installed base was reason number one. Reason number two is we really want you to extend TFX pipelines. What we publish is really just our opinionated version of what a TFX pipeline looks like and the components that we use at Google. But we want to make it easier for you to add new components before and after and in parallel to customize the pipeline to your own use cases. And all of these orchestration systems are really made to be able to express arbitrary workflows. And if you're already familiar with one of those orchestration systems, you should be able to use them for your use case. So here we show you two examples of what that looks like with Airflow and Kubeflow pipelines. So on the left, you see the same TFX pipeline configured that is executed on Airflow. And then on our example, we use this for a small data set so we can iterate on it fast on a local machine. So in the Chicago taxi cab example, we use 10,000 records. And then on the right side, you see the exact same pipeline executed on Kubeflow pipelines on Google Cloud, so that you can take advantage of Cloud Dataflow and Cloud ML Engine and scale it up to the 100 million rows that are in that data set. What's important here is it's the same configuration, it's the same components, so we run the same components in both environments. And you can choose how you want to orchestrate them in your own favorite orchestration system. So this is what this looks like if it's put together. TFX goes all the way from your raw data to your deployment environments. We discussed a shared configuration model at the top, the metadata system that keeps track of all of your runs, no matter how you orchestrate those components, and then 2 ways that we published of how to orchestrate them with Airflow and with Kubeflow pipelines. But as mentioned, you can choose to orchestrate a TFX pipeline in any way you want. All of this is available now, so you can go on GitHub, on github.com/tensorflow/tfx to check out our code and see our new user guide on tensorflow.org/tfx. And I also want to point out that tomorrow we have a workshop where you can get hands-on experience with TensorFlow Extended from 12 to 2 p.m. And there's no prerequisites. You don't even have to bring your own laptop. So with this, we're going to jump into an end-to-end example of how to actually go through the entire workflow with the Chicago taxi cab dataset. And just to set some context, so the Chicago taxi dataset is a record of cab rides in Chicago for some period of time. And it contains everything that you would expect. It contains when the trip started, when they ended, where they started and where they ended, how much was paid for it, and how it was paid. Now, some of these features need some transformation. So latitude and longitude features need to be bucketized. Usually, it's a bad idea to do math with geographical coordinates. So we bucketize them and treat them as categorical features. Vocab features, which are strings, need to be integerized. And some of the dense float features need to be normalized. We feed them into a wide and deep model. So the dense features we feed into the deep part of the model, and all of the others we use in the wide part. And then the label that we're trying to predict is a Boolean, which is if the tip is larger than 20% of the fare. So really what we're doing is we're building a high tip predictor. So just in case if there's any cab drivers in the audience or listening online, come find me later and I can help you set this up for you. I think it would be really beneficial to you if you could predict if a cab ride gives a high tip or not. So let's jump right in, and we start with data validation and transformation. So the first part of the TFX pipeline is ingesting data, validating that data if it's okay, and then transforming it such that it can be fed into a TensorFlow graph. So we start with example gen, and the example gen component really just ingests data into a TFX pipeline. So it takes as input your raw data. We ship, by default, capabilities for CSV and TF records, but that's, of course, extensible, so you can ingest any type of data into these pipelines. What's important is that after this step, the data is in a well-defined place where we can find it, in a well-defined format, because all of our downstream components standardize on that format, and it's split between training and eval. So you've seen the configuration of all of these components before. It's very minimal configuration in most of the cases. Next, we move on to data analysis and validation. And I think a lot of you have a good intuition why that is important. Because, of course, machine learning is just a process of taking data and learning models that predict some field in your data. And you're also aware that if you feed garbage in, you get garbage out. There's really no hope in learning a good machine learning model if the data are wrong, right? Or if the data have errors in them. And this is even reinforced if you have continuous pipelines that train on data that was produced by a bad model, and you're just reinforcing the same problem. So first, what I would argue is that data understanding is absolutely critical for model understanding. There's no hope in understanding why a model is mispredicting something if you don't understand what the data looked like and if the data was okay that was actually fed into the model. And the question you might ask as a cab driver is, why are my trip predictions bad in the morning hours? And for all of these questions that I'm highlighting here, I'm going to try to answer them with the tools that we have available in TFX later. So I will come back to these questions. Next, we really would like you to treat your data as you treat code. There's a lot of care taken with code these days. It's peer-reviewed, it's checked into shared repositories, it's version controlled, and so on. And data really needs to be a first-class citizens in these systems, right? And with this question, what are expected values for my payment types? That's really a question about the schema of your data. And what we would argue is that the schema needs to be treated with the same care as you treat your code. And catching errors early is absolutely critical, because I'm sure, as all of you know, errors propagate through the system. If your data are not okay, then everything else downstream goes wrong as well. And these errors are extremely hard to correct for or fix if you catch them relatively late in the process. So like really catching those problems as early as possible is absolutely critical. So in the taxi cab example, you would ask a question like, is this new company that I have in my data set a typo, or is it actually a real company, which is a natural evolution of my data set? So let's see if we can answer some of these questions with the tools we have available, starting with statistics. So the statistics gen component takes in your data, computes statistics. The data can be training, eval data. It can also be serving logs, in which case you can look at the skew between your training and your serving data. And the statistics really capture the shape of your data, and the visualization components we have draw your attention to things that need your attention, such as if a feature is missing most of the times, it's actually highlighted in red. The configuration for this component is minimal as well, and let me zoom into some of these visualizations. And one of the questions that I posed earlier was, why are my tip predictions bad in the morning hours? So one thing you could do is look at your data set and see that for trip start hour, in the morning hours between 2 a.m. and 6 a.m., you just don't have much data because there's not that many taxi trips at that time. And not having a lot of data in a specific area of your data can mean that your model is not robust or has higher variance, and this could lead to worse predictions. Next, we move on to schema gen. Schema gen takes as input the output of statistics gen, and it infers a schema for you. In the case of the Chicago taxi cab example, there's very few features, so you could handwrite that schema, although it would be hard to handwrite what you expect the string values to look like. But if you have thousands of features, it's hard to actually handwrite that expectation. So we infer that schema for you the first time we run. And the schema really represents what you expect from your data, and what good data looks like, and what values your string features can take on, and so on. Again, very minimal configuration. And the question that we can answer now is what are expected values for payment types. And if you look here at the very bottom, you see the field payment type can take on cash, credit card, dispute, no charge, P card, and unknown. So that's the expectation of my data that's expressed in my schema. And now the next time I run this, and this field takes on a different value, I will get an anomaly, which comes from the example validator. The example validator takes the statistics and the schema as an input and produces an anomaly report. Now that anomaly report basically tells you if your data are missing features, if they have the wrong valency, if your distributions have shifted for some of these features. And it's important to highlight that the anomalies report is human readable, so you can look at it and understand what's going on. But it's also machine readable, so you can automatically make decisions based on the anomalies and decide not to train a model if you have anomalies in your data. So the example validator just takes as input statistics and the schema. And let me zoom into one of these anomaly reports. Here you can see that the field company has taken on unexpected string values. That just means that these string values weren't there in your schema before. And that can be a natural evolution of your data. Right? The first time you ran this, maybe you just didn't see any trips from those taxi companies. And by looking at it, you can say, well, all of these look like they're normal taxi cab companies. So you can update your schema with this expectation. Or if you saw a lot of scrambled text in here, you would know that there's a problem in your data that you would have to go and fix. Moving on, we actually get to transform. And let me just recap the types of transformations that we want to do. I've highlighted them here in red, in blue, sorry. So we want to bucketize the longitude and latitude features. We want to convert the strings to ints, which is also called integerizing. And for the dense features, we want to actually normalize them to a mean of 0 and a standard deviation of 1. Now, all of these transformations require you to do a full pass over your data to compute some statistics. To bucketize, you need to figure out the boundaries of the buckets. To do a string to int, you actually need to see all of the string values that show up in your data. And to scale to a z-score, you need to compute the mean and the standard deviation. Now, this is exactly what we built TensorFlow Transform for. TensorFlow Transform allows you to express a preprocessing function of your data that contains some of these transformations that require a full pass over your data. And it will then automatically run a data processing graph to compute those statistics.
So in this case, you can see the orange boxes are statistics that we require. So for mean normalization, we require a mean and a standard deviation. And what TensorFlow Transform does is it has a utility function that says scale to z-score, and will then create a data processing graph for you that computes the mean and the standard deviation over your data, return the results, and inject them as constants into your transformation graph. So now that graph is a hermetic graph that contains all of the information that you need to actually apply your transformations. And that graph can then be used in training and in serving, guaranteeing that there's no drift between them. This basically eliminates the chances of training serving skew by applying the same transformations. And at serving time, you just need to feed in the raw data, and all of the transformations are done as part of the TensorFlow graph. So how does it look like in a TFX pipeline? The transform component takes in data, a schema. The schema allows us to parse the data more easily. And code, in this case, this is the user-provided preprocessing function. And it produces the transform graph, which I just mentioned, which is a hermetic graph that applies your transformations, that gets attached to your training and your serving graph. And it optionally can materialize the transform data. And that's a performance optimization that sometimes you need when you want to feed hardware accelerators really fast. It can sometimes pay off to materialize some of your transformations before your training step. So in this case, the configuration of the component takes in a module file. That's just a file where you configure your preprocessing function. And in this code snippet, the actual code is not that important, but what I want to highlight is the last line in this code snippet is how we transform our label, because of course the label is a logic expression of saying, is the tip greater than 20% of my fare? And the reason why I want to highlight this is because you don't need analyze phases for all of your transformations, right? So in cases where you don't need analysis phases, the transformation is just a regular TensorFlow graph that transforms your features. However, to scale something to z-score, to integerize strings, and to bucketize a feature, you definitely need analysis phases, and that's what Transform helps you with. So this is the user code that you would write, and TF Transform would create the data processing graph and return the results and the transform graph that you need to apply these transformations. So now that we've done with all of this, we still haven't trained a machine learning model yet, right? But we've made sure that we know that our data is in a place where we can find it. We know it's in a format that we can understand. We know it's split between training and eval. We know that our data are good because we validated them. And we know that we're applying transforms consistently between training and serving. Which brings us to the training step. And this is where the magic happens, or so they say, right? But actually, it's not, right? Because the training step in TFX is really just a TensorFlow graph and the TensorFlow training step. And the training component takes in the outputs of transform, as mentioned, which is the transform graph and optionally the materialized data, a schema, and the training code that you provide. And it creates as output TensorFlow models. And those models are in the saved model format, which is the standard serialized model format in TensorFlow, which you've heard quite a bit about this morning. And in this case, actually, we produce two of them. One is the inference graph, which is used by TensorFlow serving. And another one is the eval graph, which contains the metrics and the necessary annotations to perform TensorFlow model analysis. And so this is the configuration that you've seen earlier. And again, the trainer takes in a module file. And the code that's actually in that module file, again, I'm just going to show you the same slide again, just to reiterate the point, is just TensorFlow. So in this case, it's the train and evaluate method from estimators and a canned estimator that is being returned here. But again, just to make sure you're aware of this, any TensorFlow code here that produces the saved model in the right format is fair game. So all of this works really well. So with this, we've now trained the TensorFlow model, and now I'm going to hand it off to my colleague, Christina, who's going to talk about model evaluation and analysis. Thank you.
Thank you, Clemens. Hi, my name is Christina, and I'm a software engineer on the Google Brain team. I'm here today to tell you about some tools that my team and I have built to help make the end-to-end life cycle of the machine learning pipeline easier. I'm going to start by talking about model analysis and validation. These are two different components in TFX, but they are very similar in how they're actually executed. The main difference is how you as an end user will use them. I'm going to start by talking about the evaluator. So why is model evaluation important? Well, for one thing, we have gathered data, we've cleaned that data, we've trained a model, but we really want to make sure that that model works. And so model evaluation can help you assess the overall quality of your model. You also may want to analyze how your model is performing on specific slices of the data. So in this case, with the Chicago taxi example that Clemens started us off with, why are my tip predictions sometimes wrong? Slicing the data and looking at where you're doing poorly can be a real benefit because it identifies some low-hanging fruit where you can get gains in accuracy by adding more data or making some other changes to make some of these segments improve. You also want to track your performance over time. You're going to be continuously training models and updating them with fresh data so that your models don't get stale. And you want to make sure that your metrics are improving over time and not regressing. And model evaluation can help you with all of this. The component of TFX that supports this is called the evaluator, and it is based on a library called TensorFlow Model Analysis. From the pipeline perspective, you have inputs, which is your eval set that was generated by your example gen. You have the trainer outputting a saved model. You also need to specify the splits in your data that you find most interesting so that the evaluator can pre-compute metrics for these slices of data. Your data then goes into the evaluator, and a process is run to generate metrics for the overall slice and these slices that you have specified. The output of the evaluator is evaluation metrics. This is a structured data format that has your data, the splits you've specified, and the metrics that correspond to each one of these splits. The TensorFlow Model Analysis library also has a visualization tool that allows you to load up these metrics and dig around in your data in a user-friendly way. So going back to our Chicago taxi example, you can see how the model evaluator can help you look at your top-line objective. How well can you predict trips that result in large tips? The TFMA visualization shows the overall slice of data here. The numbers are probably small, but accuracy is 94.7%. That's pretty good. You'd get an A for that. But maybe you want to say 95%. 95% accuracy is a lot better number than 94.7. So maybe you want to bump that up a bit. So then you can dig into why your tip predictions are sometimes wrong. We have sliced the data here by the hour of day that the trip starts on. And we've sorted by poor performance. When I look at this data, I see that trips that start at like 2, 3 a.m., we're performing quite poorly in these times. Because of the statistics generation tool that Clemens talked about, I do know that the data is sparse here. But if I didn't know that, perhaps I would think maybe there's something that people that get taxis at 2 or 3 in the morning might have in common that causes erratic tipping behavior. Someone smarter than me is going to have to figure that one out. You also want to know if you can get better at predicting trips over time. So you are continuously training these models for new data, and you're hoping that you get better. So the TensorFlow Model Analysis tool that powers the evaluator in TFX can show you the trends of your metrics over time. And so here you see 3 different models and the performance over each with accuracy and AUC. Now I'm going to move on to talking about the model validator component. With the evaluator, you were an active user. You generated the metrics, you loaded them up in the UI, you dug around in your data, you looked for issues that you could fix to improve your model. But eventually, you're going to iterate, your data's going to get better, your model's going to improve, and you're going to be ready to launch. You're also going to have a pipeline continuously feeding new data into this model. And every time you generate a new model with new data, you don't want to have to do a manual process of pushing this to a server somewhere. The model validator component of TFX acts as a gate that keeps you from pushing bad versions of your model while allowing you to automate pushing of quality models. So why model validation is important? We really want to avoid pushing models with degraded quality, specifically in an automated fashion. If you train a model with new data and the performance drops, but say it increases in certain segments of the data that you really care about, maybe you make the judgment call that this is an improvement overall, so we'll launch it. But you don't want to do this automatically. You want to have some say before you do this. So this acts as your gatekeeper. You also want to avoid breaking downstream components. If your model suddenly started outputting something that your server binary couldn't handle, you'd want to know that also before you push. The TFX component that supports this is called the model validator. It takes very similar inputs and outputs to the model evaluator, and the libraries that compute the metrics are pretty much the same underneath the hood. However, instead of one model, you provide two: the new model that you're trying to evaluate and the last good evaluated model. It then runs on your eval split data and compares the metrics on the same data between the two models. If your metrics have stayed the same or improved, then you go ahead and bless the model. If the metrics that you care about have degraded, you will not bless the model. Get some information about which metrics failed so that you can do some further analysis. The outcome of this is a validation outcome. It just says blessed if everything went right. Another thing to note about the model validator is that it allows you to do next day eval of your previously pushed model. So maybe the last model that you blessed, it was trained with old data. With a model validator, it evaluates it on the new data. And finally, I'm going to talk about the pusher. The pusher is probably the simplest component in the entire TFX pipeline, but it does serve quite a useful purpose. It has one input, which is that blessing that you got from the model validator. And then the output is, if you passed your validation, then the pusher will copy your saved model into a file system destination that you've specified. And now you're ready to serve your model and make it useful to the world at large. I'm going to talk about model deployment next. So this is where we are. We have a trained saved model. A saved model is a universal serialization format for TensorFlow models. It contains your graph, your learned variable weights, your assets like embeddings and vocabs. But to you, this is just an implementation detail. Where you really want to be is you have an API, you have a server that you can query to get answers in real time or provide those answers to your users. We provide several deployment options, and many of them are going to be discussed at other talks in this session. TensorFlow.js is optimized for serving in the browser or on Node.js. TensorFlow Lite is optimized for mobile devices. We already heard a talk about how Google Assistant is using TensorFlow Lite to support model inference on their Google Home devices. TensorFlow Hub is something new, and Andre is going to come on in about 5 minutes and tell you about that, so I'm not going to step on his toes. I'm going to talk about TensorFlow serving. So if you want to put up a REST API that serves answers for your model, you would want to use TensorFlow serving. And why would you want to use this? For one thing, TensorFlow serving has a lot of flexibility. It supports multi-tenancy. You can run multiple models on a single server instance. You can also run multiple versions of the same model. This can be really useful when you're trying to canary a new model. Say you have a tried and tested version of your model. You've created a new one. It's passed your evaluator. It's passed your validation. But you still want to do some A/B testing with real users before you completely switch over. TensorFlow serving supports this. We also support optimization with GPU and TensorRT. And you can expose a gRPC or a REST API. TensorFlow serving is also optimized for high performance. It provides low latency, request batching, so that you can optimize your throughput while still respecting latency requirements, and traffic isolation. So if you are serving multiple models on a single server, a traffic spike in one of those models won't affect the serving of the other. And finally, TensorFlow serving is production ready. This is what we use to serve many of our models inside of Google. We've served millions of QPS with it. You can scale in minutes, particularly if you use the Docker image and scale up on Kubernetes. And we support dynamic version refresh. So you can specify a version refresh policy to either take the latest version of your model, or you can pin to a specific version. This can be really useful for rollbacks if you find a problem with the latest version after you've already pushed. I'm going to go into a little bit more detail about how you might deploy a REST API for your model. We have two different options for doing this presented here. The first, the top command, is using Docker, which we really recommend. It requires a little bit of ramp up at the beginning, but you will really save time in the long run by not having to manage your environment and not having to manage your own dependencies. You can also run locally on your own host, but then you do have to do all of that stuff long term. I'm going to go into a little bit more detail on the Docker run command. So you start with Docker run. You choose a port that you want to bind your API to. You provide the path to the saved model that was generated by your trainer. Hopefully it was pushed by the pusher. You provide the model name, and you tell Docker to run the TensorFlow serving binary. Another advantage of using Docker is that you can easily enable hardware acceleration. If you're running on a host with a GPU and the NVIDIA Docker image installed, you can modify this command line by a few tokens and then be running on accelerated hardware. If you need even further optimization, we now support optimizing your model for serving using TensorRT. TensorRT is a platform for NVIDIA for optimized deep learning inference. Your Chicago taxi example that we've been using here probably wouldn't benefit from this. But if you had, say, an image recognition model, a ResNet, you could really get some performance boosting and cost savings by using TensorRT. We provide a command line that allows you to convert this saved model into a TensorRT optimized model. So then again, a very simple change to that original command line, and you're running on accelerated GPU hardware with TensorRT optimization. So to put it all together again, we introduced TensorFlow Extended, or TFX. We showed you how the different components that TFX consists of can work together to help you manage the end-to-end lifecycle of your machine learning pipeline. First, you have your data, and we have tools to help you make sense of that and process it and prepare it for training. We then support training your model, and after you train your model, we provide tools that allow you to make sense of what you're seeing, of what your model's doing, and to make improvements. Also, to make sure that you don't regress. Then we have the pusher that allows you to push to various deployment options and make your model available to serve users in the real world. To get started with TensorFlow Extended, please visit us on GitHub. There is also more documentation at tensorflow.org/tfx, and some of my teammates are running a workshop tomorrow, and they'd love to see you there. You don't need to bring a laptop. We have machines that are set up and ready to go, and you can get some hands-on experience using TensorFlow Extended. Thank you, and now please welcome Andre, who's going to talk about TensorFlow Hub.
Thank you, Christina. Could I get notes on the presentation? Thank you. Hello, my name is Andre, and I'm a software engineer in Zurich. I'm the technical lead for the TensorFlow Hub project. TensorFlow Hub is a library and a repository for reusing machine learning. We open sourced it last year, and today I'll give you an update on the project. Let's start by talking about when you'd want to use it. If you have problems collecting enough data to train your models from scratch, then transfer learning is a technique for you. You can use UB to make it easy to reuse parts of models that were trained on large amounts of data. Additionally, since it's so easy to reuse computations and weights, it becomes possible to leverage features without having to learn how to feed them into neural networks. So images, text, and videos are features you can use with a single line of code. You might also have encountered problems where code bases become really coupled and experimentation becomes slower over time. By defining an artifact that does not depend on code, UB allows for more maintainable systems, similar to how libraries have helped software engineer. So the main concept is these pre-trained building blocks that we call modules. Typically, we start by training a large model with the right algorithm and data. From this large model, we're just interested into a part of it, which is reusable. This is typically a bottleneck layer or some other distributed representation. Then we can package them into a saved model that defines this computation and awaits our train and no longer depends on the original code. You can share this artifact via the file system, web servers, cloud. Then you can bring this module back as a piece of a new model to solve a new task. Since the model is defined by TensorFlow primitives, you can fine-tune its weights and adjust them to your problem. So what's new? For the last few months, we have been making it even easier to use. This concept of saving a part of a model and then loading it back is getting integrated right in the core of TensorFlow. We have added save model features that make it possible to share more than just signatures. And with eager execution, it becomes even easier to select the part of a network that gets exported. Let's look at a few examples. In TensorFlow 2.0, we can load a module with up.load. We can also use tf.savedModel.load if the model is already on our file system. Due to eager execution, once loaded, we can call it right away. Additionally, due to the new capabilities, you can now share any object which is composed of TensorFlow primitives. So in this case, text features as two members, call, which is a TF function, and embeddings, which is a TF variable. We are also really excited that we added support for polymorphic functions when we serialize TF functions on saved model. This will provide a more natural interface than we had before with signatures. For example, here we see an image representation module being loaded and then being used in inference mode, or being used during training mode where batch norm is on. Or when it's on, we can also control some of its parameters. And all of this is just baked by TF graphs, so we no longer need to be selecting things here and there. We just get all the API that looks very, very like Python. Additionally, we have added a new symbol, up.keras layer. This makes integrating up modules into a keras model easier. In this example, we see how easy it is to build a text sentence classification model. So we have three layers. The top layer, this keras layer, which is the NNLM, is a layer that receives sentences as inputs and outputs a dense representation. Then we have a dense layer and a classification layer. Since the keras layer, this NNLM layer, includes text preprocessing on it, we can just feed sentences straight into our model. We never had to define the logic for it. Additionally, if we wanted to try other text models, we could just change that string. That'll be as easy to try like the latest research. So the status is we have released a 0.3 version of TensorFlow Up. It has these two new symbols we just saw, up.load and up.keras layer, and they are usable in TensorFlow 2, both in eager and graph mode. To let you preview this functionality, we have published some modules in this format, and the next steps for us is to backport existing models. Okay, a bit more practical now. Google AI and DeepMind teams have been sharing their research with you on tfup.dev. This was already launched last year, and there are some new modules, and we're going to have a look at some of those. One of the most popular was the Universal Sentence Encoder. This was a module that encoded short sentences into a high-dimensional vector that could be used for many natural language tasks. Recently, the team has added a cross-lingual version of this. So sentences with similar meaning, independent of the language, they'll end up in points close together. What's exciting about this is that now you can learn a classifier using English data, and then you could run it on other languages. We have also added image augmentation modules. The policies to augment images were trained by reinforcement learning on tasks such as ImageNet, and they have been shown to transfer to new tasks. An interesting thing is that you could grab this module and you could grab one of the image representation modules, and you could string them together. In this case, the image augmentation module would reduce the amount of data by data augmentation and the image feature vector by transfer learning. And there are many more. We have BERT module for text tasks. We have object detection modules, big GAN modules for controlled image generation, i3D kinetics for video action recognition, and more. Some of these models' architectures were specially designed for low resources. Additionally, we have been working on making modules more integrated with other pieces of TensorFlow ecosystem. We have a command line utility to convert a hub module into a TF-JS model. Hub models can be used together with Addenet, which is a library for AutoML. And they can also be used inside TF Transform. So if you want to try it, you can go to tfhub.dev, and you can search for modules. Most of them include a link where you can see them in action. Thank you.
extreme weather is changing. There's more extreme rainfall, heavy flooding, forest fires. There isn't really a signature done. Being able to predict these extreme events more accurately is kind of the big challenge that we're facing right now. There's 100 terabytes of climate data every day from satellites, from observations, from models. So climate data is a big data problem. We need things that are fast, that can sift through all of that data rapidly and accurately. And deep learning is almost perfectly poised for problems in climate science.
A lot of NERSC users are using TensorFlow. It's one of the more popular frameworks. We use TensorFlow to iterate quickly over different models, different layer parameters. For this particular climate project, to create the deep learning model, we started from segmentation models which have proven to be successful, for example, our satellite imagery segmentation tasks. And then we used TensorFlow to enhance the models until we found like a set of models which perform well enough for this specific task. But for the volume of the data, complexity of the data, the network required 14 teraflops. So if you want to do this on your workstation, it would take like months to train.
To really tackle these problems requires the largest computational resources that are available on the planet. So systems like the Summit supercomputer. It's 2 tennis courts in total size. I mean, this thing is state-of-the-art. It's 1,000,000 times faster than your common laptop. 3.3 exaflops. Just imagine what you do at your workstation, but now imagine having 27,000 times that power. We can do that now.
We were surprised how good it actually scales. 1,000 nodes and 2,000 nodes, 5,000 nodes.
This was the first time anybody's ever run an AI application at this scale. Instead of having the climate scientists figure out how to write high-tune code, they could express things in a very natural way in Python in TensorFlow and get all the high-performance code that most HPC people are used to within TensorFlow.
We're now entering the space where AI can actually contribute to the predictions of these extreme weather events.
When you combine traditional HPC with AI, you can tackle things we never thought that we could tackle. Fusion reactor research, understanding diseases like Alzheimer's, cancer, right? That's incredible.
We've shown that with a high productivity framework such as TensorFlow, you can get to massive scale and you can get awesome performance and accomplish your goals.
Genetics, neuroscience, cosmology, high energy physics. That's immensely exciting for me.
Okay, hello everyone. I'm Josh Dillon, and I'm a lead on the TensorFlow probability team. And today, I'm going to talk to you about probability stuff and how it relates to TensorFlow stuff. So let's find out what that means. Okay, so these days, machine learning often means specifying deep model architectures and then fitting them under some loss. And happily, Keras makes specifying model architecture relatively easy. But what about the loss? Choosing the right loss is tough. Improving one, even a reasonable one, can be even tougher. And once you fit your model, how do you know it's good? Does accuracy tell the full picture? Why not use mean, entropy, mode? Wouldn't it be great if there existed some mathematical framework which unified these ideas? Better still, wouldn't it be nice if it was plug and play with Keras and the rest of TF? This would make comparing models easier by simply maximizing likelihood and having readily available evaluative statistics. We can rapidly prototype different generating assumptions and quickly reject the bad ones. In short, wouldn't it be great if we could do this? Just say, I want to maximize the log likelihood, and then summarize what I learned easily and in a unified way. So let's play with that idea. Here we have a data set, these blue dots, and our task is to predict, our pretend task is to predict the y coordinate from the x coordinate. And the way you might do this is specify some deep model. And of course, you might choose the mean squared error as your loss function. OK. But our wish here is to think probabilistically. And so that means maximizing the log likelihood, as indicated here with this lambda function, the negative random variable log prob under y. And what we want in addition to that is to get back a distribution, a thing that has attached to it statistics that we can use to evaluate what we just learned. If only such a thing were possible. Of course, it is, and you can do this now. Using TensorFlow probability distribution layers, you can specify the model as part of your deep net. And the loss now is actually part of the model, sort of the way it used to be, the way it's meant to be. And so let's unpack what's happening here. So we have two dense layers. It's sort of business as usual. The second one outputs one float. And that one float is parameterizing a normal distribution's mean. And that's being done through this distribution lambda layer. In so being, we're able to find this line. That looks great. And The best part is once we instantiate this model with test points, we have back a distribution instance, for which you get not just the mean, which is what you'd get today, but also entropy, variance, standard deviation, all of these things. And you can even compare between this and other distributions, as we'll see later. But if we look at this data, something's still a little fishy here, right? Notice that as the magnitude of x increases, the variance of y also seems to increase. So that means that maybe our model's a little suspicious. So since we're in this probabilistic framework, and we're no longer doing loss hacking, we're actually building a model, what can we do to fix this? Answer, learn the variance too. It's actually pretty obvious. If we're fitting a normal, why on earth do we think that the variance would just be 1? And by the way, that's what you're doing when you use mean squared error. And so now, to achieve this, all I had to do is make my previous layer output 2 floats. I pass 1 in as the mean to the normal, 1 in as the standard deviation of the normal, and presto changeo, now I've learned the standard deviation from the data itself. That's what the green lines are. So this is really cool because now if you're a statistician, you would say, hey, I'm able to handle heteroscedasticity. If you want a $10 word, you can call this aleatoric uncertainty. And what this really means is that you're learning known unknowns. It means that the data itself had variance, and you learned it. And it cost you basically nothing to do but a few keystrokes. And furthermore, the way in which you saw how to do this was self-evident from the very fact that you were using a normal distribution which had this curious constant just sitting there. So this is good, but I don't know, is there enough data for which we can reliably claim that this red line is actually the mean and these green lines are actually the standard deviation? How would we know if we have enough data? Is there anything else we can do? Of course there is. Why learn just a single set of weights? A Keras-dense layer has 2 components, a kernel matrix and a bias vector. What makes you think that those point estimates are the best, especially given that your data set itself is random and possibly inadequate to meaningfully and reliably learn those point estimates? Instead, if you use a TensorFlow probability dense variational layer, you can actually learn a distribution over weights. This is the same as learning an ensemble that's infinitely large. But luckily, it doesn't take infinitely long to train this ensemble. In fact, it takes just a little bit longer than what it took to train on the previous slides. And as you can see here, all I had to do is replace keras.dense with tfp.dense variational layer, and in so doing achieve this kind of Bayesian weight uncertainty. The $10 word here is epistemic uncertainty, but again, I like to think of it as unknown unknowns. I'm not sure what my data is not telling me, so I'm going to be careful in the bookkeeping I make when tracking the weights that I learn. As a consequence, of course, this means that any model you make, any instantiation of this model is now actually a random variable because the weights are random variable. And that's why you see here all of the lines, there are many lines. We have an ensemble of them. But if you were to average those and take the sample standard deviation, say, then that would give you an estimate of credible intervals over your prediction. So now you can go to your customer and say, look, here's what I think would happen, and here's how much you should trust me. So this is great, right? But we seem to have lost the heteroscedastic part. Notice that the blue dots are still more dispersed on the right-hand side. So can we do both? Of course we can. It's all modular. I just have my dense variational layer output 2 floats instead of 1, like we did before, feed that into my output layer, which is a normal distribution, and presto changeo, I'm learning both known and unknown unknowns, and all it cost me was a few keystrokes. And so what you see here now is an ensemble of standard deviations associated with the known unknown parts, the variance present or observable in the y-axis, as well as a number or an ensemble of these mean regressions. OK, that's cool. So I like where this is going, but I have to ask, what makes you think a line is even the right thing to fit here? Is there another distribution we could choose, a richer distribution, that would actually find the right form of the data? And of course, the answer is yes. It's a Gaussian process. By tossing in this fancy distribution, it turns out that the data wasn't linear at all. No wonder we had such a hard time fitting it. It was sinusoidal. And the Gaussian process can see this. How can the Gaussian process see this? Because it treats the loss itself as a random variable. Now, how could you do that if you're just specifying mean squared error as your loss? You can't. It has to be part of your model. And that's the power of probabilistic modeling. When you bake in these ideas into one model, you get to move things around fluidly between weight uncertainty and variance in the data, and even uncertainty in the loss function you're fitting itself. And so the question is, how can this all be so easy? How did it all fit together with TensorFlow probability? So TensorFlow probability is a collection of tools designed to make probabilistic reasoning in TensorFlow easier. It is not going to make your job easy. It's just going to give you the tools you need to express the ideas you have. You still have to have domain knowledge and expertise, but you can encode that domain knowledge and expertise in a probabilistic formalism, and TFP has the tools to do that. Statisticians and data scientists will be able to write and launch the same model. Gone are the days of hacking your model in R and then porting it over to a faster language like C++, or even TensorFlow. You can do it all in the same framework. ML researchers and practitioners will be able to make predictions with uncertainty. If you predict the light is green, you better be pretty confident that you should go. You can do that with probabilistic modeling and TensorFlow probability. So we saw one small part of TFP. Broadly speaking, the tools are broken into two components. Those tools useful for building models, and those tools useful for doing inference on those models. On the model building side, you saw the normal distribution and the variation of Gaussian process distribution. A distribution just is a collection of simple summary statistics, exactly like it is in every other library. There's a few differences. Our distributions support this concept of batch shape, which automatically takes advantage of vector processing hardware. But for the most part, they should be pretty natural and easy to use. We also have something we call bijectors, which is a library for transforming random variables. In the simplest case, this can be like taking the exp of a normal, and now you have a log normal. In more complicated cases, it can involve transforming a random variable with a neural network. This includes things like masked autoregressive flows, if you've heard about it, real NVPs, and other sophisticated probabilistic models. You saw layers. We also have some losses that help you build Monte Carlo approximations to otherwise intractable calculations. Edward 2 is our probabilistic programming language that helps you combine different random variables as one. On the inference side, no Bayesian library would be complete without Markov chain Monte Carlo tools, within which we have several transition kernels. One of them is called Hamiltonian Monte Carlo, which naturally takes advantage of TensorFlow's automatic differentiation capability. We also have tools for performing variational inference, again, taking advantage of TF's automatic differentiation and optimizer toolbox. And of course, we have our own optimizers that often come up in probabilistic modeling problems, such as Nelder-Mead, BFGS, things like that. The point is, this toolbox has maybe not everything, but certainly it has most of what you might need to do fancier modeling to actually get more out of your machine learning model. And it doesn't have to be hard. You saw the Keras examples were just a sequence of one-line changes. So, of course, TensorFlow probability is used widely around Alphabet. DeepMind uses it extensively. Google Brain uses it. Google Accelerated Sciences, product areas, infrastructure areas even use it for planning purposes. But it's also used outside of Google. So Baker Hughes GE is one of our sort of early adopters of TensorFlow probability. And they use it to build models to detect anomalies. Anomaly detection is a very hard problem because hopefully your data set never has the anomaly you're trying to detect. For example, anyone who flew out here would be happy to know that Baker Hughes GE uses this anomaly detection to predict the lifespan of jet engines. And if we had a data set that had a failing jet engine, that would be a tragedy. And so using math, we can get around this by they get around this by modeling models and then trying to, in the abstract, figure out if those are going to be good models. So what you see is their data processing pipeline. The orange boxes use TensorFlow probability extensively. The orange border box is where they use TensorFlow. And the basic flow is to try to treat the model itself as a random variable and then determine if it's going to be a good model on otherwise an incomplete data set. And from this, they're able to do they get remarkable results, dramatic decreases in false positives and false negatives over very large data sets in complicated systems. So the question is, who will be the next success story? Try it out. It's an open source Python package built using TensorFlow that makes it easy to combine deep learning with probabilistic models. You can pip install it. Check out tensorflow.org/probability. And if you're interested in learning more about Bayesian approaches, check out this book, which we rewrote using TensorFlow probability, within which you can learn, like I said, Bayesian methods, but also just how to use TensorFlow probability. If you're not a Bayesian, that's fine too. We have numerous tools for frequentists. We have a second-order generalized linear model solver, which you should care, because if you're doing linear regression, it could solve that problem on the order of 30 iterations, which definitely cannot be said of a standard gradient descent. And if you want to find out more about this example, you can check out our GitHub repository, where you'll find several Jupyter notebooks. Thanks. And with that, I would like to hand it off to Eugene and Sergio, who will be talking about reinforcement learning.
Hello, everyone. How's it going? Very packed day, a lot of good stuff. Are you ready for more or not? OK, good. So my name is Sergio Guadarrama. I'm a senior software engineer at Google Brain, and I'm leading the TF Agents team.
And I'm Eugene Brevdo, a software engineer on Google Brain team working on reinforcement learning.
So today we're going to talk about reinforcement learning. So how many of you remember how you learn how to walk? Yeah? You stumble a little bit, you try one step, doesn't work, you lose your balance, you try again. So when you're trying to learn something that is hard and you need a lot of practice, you need to try many times. So in this cute little robot, it's basically trying to do that. Just moving the legs, doesn't coordinate very well, but it's trying to learn how to walk. After learning try multiple times, in this case 1,000 times, it learns a little bit how to do the first steps, moving forward a little bit before falling off. It will learn train a little longer, then it's able to actually walk around, go from one place to another, and find their way around the room. Probably you have heard about all the applications of reinforcement learning over the last couple of years, including recommender assistance, data certain coolings, real robots like that, chemistry, maths, this little cute little robot, but also like AlphaGo, that play Go like better than any human. Now I have a question for you. How many of you have tried to actually implement some RL algorithm? OK, I see quite a bit of hands. Very good. It's hard. Yeah, we went through that pain too. Many people who try get the first prototype right away. It seems to be working, but then you miss a lot of different pieces. All the details have to be right, all the things, all the bugs, everything, because it's very unstable. You don't know if it's a bug, it's a feature. So there's a lot of pieces. A replay buffer, there's a lot of things you need to do. So we suffer through the same problem at Google, so we decided to implement a library that many people can use. And today, the TF Agents team is very happy to announce that it's available online. You can go to GitHub, you can pip install it, and start using it right away. And hopefully, you will provide feedback, contributions, so we can make this better over time. So now, what is TF Agents and what it provides? So we try to make it very robust, very scalable, and easy to use reinforcement learning for TensorFlow. So it's going to be easy to debug, easy to try, and easy to get good things going. For people who are new to reinforcement learning, we have collabs and things, documentation and samples, so you can learn about it. For people who want to really solve a real problem, a complex problems, we have already ways to take state-of-the-art algorithms and apply directly. Or for people who are researchers and want to develop new RL algorithms, they don't need to build all the single pieces. They can build on top of it. We make it well-tested and easy to configure, so you can start doing your experiments right away. We build on top of all the goodies of TensorFlow 2.0 that you just saw today, like TF figures to make the development and the debugging a lot easier, TF keras to build the networks and the models, TF function when you want to make things to go faster, and then we make it very modular and extensible, so you can cherry pick. It's a library, you can cherry pick with the pieces that you need and extend it as you need it. And for those who are not ready for the change yet, we make it compatible with TensorFlow 1.14. So we go back to the little example of the little robot trying to walk. this is in a nutshell how the code looks like. You have to define some networks, in this case, an actor distribution network and a critic network, and then an actor, an agent, the soft-actor critic agent in this case. And then, assuming we have some experience already collected, we can just train through it. TF agents provide a lot of RL algorithms, RL environments already, like OpenAI Gym, Atari, Muyoko, PyBullet, DNControl, and maybe yours soon. We also provide the state-of-the-art algorithms, including DQN, TD3, PPO, soft-actor critic, and many others. And there are more coming soon, and hopefully more from the community. They are fully tested with quality regression tests and speed tests to make things keep working. As an overview of the system, it looks like that. On the left side, you have all the collection aspects of it, and we're going to have some policy that's going to interact with the environment and collect some experience. Probably we put in some replay buffers to work with later, and on the right side, we have all the training pipeline. We're going to read from this experience, and our agent is going to learn to improve the policy by training a neural network. Let's focus for a little bit in this environment. How do we define a problem? How do we define a new task? Let's take another example. In this case, it's breakout. The idea is like you have to play this game, move the paddle left and right, and trying to break the bricks on the top. You break the bricks, you get reward, so the points go up. You let the ball drop, then the points go down. So the agent is going to receive some observation, in this case, multiple frames. From the environment, it's going to decide which action to take, and then based on that, it's going to get some reward, and then just loop again. How this look into the code is something like this. You define the observation specification. It's like what kind of observation this environment provides. In this case, will be frames, but it could be any tensors or any other information, multiple cameras, multiple things. And then the action specs. It's like what actions can I make in this environment? In this case, only left and right. But many other environments, we have multiple actions. Then a reset method, because we're going to play this game a lot of times, so we have to reset the environment. And then a step method, that taking an action is going to produce a new observation and give us some reward. Given that, we could define a policy by hand, for example, and start playing this game. You just create the environment, define your policy, reset the environment, and start looping over it and start playing the game. If your policy is very good, you will get a good score. To make the learning even faster, we make these parallel environments, so you can run these games in parallel multiple times, and wrap in TensorFlow, so it will go even faster, and then do the same loop again. What happened in general is like we don't want to define these policies by hand. So let me hand it over to Eugene, who's going to explain how to learn those policies.
Thank you, Sergio. Yeah, as Sergio said, I'll give an example of how you would interact with the environment by a policy. And we're going to go into a little bit more detail and talk about how to make policies, how to train policies to maximize the rewards. OK, so kind of going over it again. Policies take observations and emit parameters of a distribution, emit a distribution over the actions. And in this case, the observations are an image or a stack of images. There's an underlying neural network that converts those images to the parameters of the distribution. And then the policy emits that distribution, or you might sample from it to actually take actions. So let's talk about networks. I think you've seen some variation of this slide over and over again today. A network, in this case, a network used for deep Q learning, is essentially a container for a bunch of Keras layers. In this case, your inputs go through a convolution layer, and so on and so forth. And then the final layer emits logits over the number of actions that you might take. The core method of the network is the call. So it takes observations in a state, possibly an RNN state, and emits the logits in the new updated state. OK, so let's talk about policies. First of all, we provide a large number of policies, some of them specifically tailored to particular algorithms and particular agents. But you can also implement your own. So it's useful to go through that. So a policy takes one or more networks. And the fundamental method on a policy is the distribution method. So this takes the time step, which essentially contains the observation, passes that through one or more networks and emits the parameters of the output distribution, in this case, logits. It then returns a tuple of 3 things. So the first thing is an actual distribution object. So Josh Dillon just spoke about TensorFlow probability, and here's a TensorFlow probability categorical distribution built from those logits. It emits the next state, again, possibly containing some RNN state information. And it also emits site information. So site information is useful. Perhaps you want to emit some information that you want to log in your metrics. That's not part of that's not the action. Or you maybe want to log some information that is necessary for training later on. So the agent is going to use that information to actually train. OK, so now let's actually talk about training. The agent class encompasses the main RL algorithm, and that includes the training and reading batches of data and trajectories to update the neural network. OK, so here's a simple example. First, you create a deep Q-learning agent. You give it a network. You can access a policy, specifically a collection policy, from that agent. That policy uses the underlying network that you passed in and maybe perform some additional work, like maybe perform some exploration, like epsilon greedy exploration, and also logs site information that is going to be necessary to be able to train the agent. The main method on the agent is called train. It takes experience in the form of batch trajectories. These come, for example, from a replay buffer. Now, assuming you have trained your networks and you're performing well during data collection, you also might want to take a policy that performs more greedy action and doesn't explore at all, just exploits, takes the best actions that it thinks are the best, and doesn't log any side information, doesn't emit any side information. So that's the deployment policy. And you can save this to a saved model, for example, and put it into deployment. OK. So a more complete example, again, here we have a deep Q-learning network. It accepts the observation and action specs from the environment and some other arguments describing what kind of Keras layers to combine. You build the agent with that network. And then you get a TF data set. In this case, you get it from a replay buffer object. But you can get it from any other data set that emits the correct form trajectory, batch trajectory information. And then you iterate over that data set calling agent.train to update the underlying neural networks, which are then reflected in the updated policies. So let's talk a little bit about collection. Given a collection policy, and it doesn't have to be trained. It can have just random parameters. You want to be able to collect data, and we provide a number of tools for that. Again, if your environment is something that is in Python, you can wrap it. So the core tool for this is the driver. And going through that, first you create your batched environments at the top. Then you create a replay buffer. In this case, we have a TF uniform replay buffer. So this is a replay buffer backed by TensorFlow variables. And then you create the driver. So the driver accepts the environment, the collect policy from the agent, and a number of callbacks. When you call driver.run, what it will do is it will iterate. In this case, it will take 100 steps of interaction between the policy and the environment, create trajectories, and pass them to the observers. So after driver.run has finished, your replay buffer has been populated with 100 more frames of data. All right, so here's kind of the complete picture. Again, you create your environment. You interact with that environment to the driver, given a policy. Those interactions get stored in a replay buffer. The replay buffer you read from with a TF data set. And then the agent trains with batches from that data set and updates the network underlying the policy. Here's kind of a set of commands to do that. if you look at the bottom, here's that loop you call driver run to collect data. It stores that in the replay buffer. And then you read from the data set generated from that replay buffer and train the agent. You can iterate this over and over again. OK, so we have a lot of exciting things coming up. For example, we have a number of new agents that we're going to release, C51, D4PG, and so on. We're adding complete support for contextual bandits that are backed by neural networks to the API. We're going to release a number of baselines, and as well as a number of new replay buffers. So in particular, we're going to be releasing some distributed replay buffers in the next couple of quarters, and those will be used for distributed collection. So distributed collection allows you to parallelize your data collection across many machines and be able to maximize the throughput of your training your RL algorithm that way. We're also working on distributed training using TensorFlow's new distribution strategy API, allowing you to train at massive scale on many GPUs and TPUs. And we're adding support for more environments. So please check out TF Agents on GitHub. And we have a number of collabs, I think 8 or 9 as of this count, exploring different parts of the system. And as Sergio said, TF Agents is built to solve many real-world problems. And in particular, we're interested in seeing what your problems are. For example, we welcome contributions for new environments, new RL algorithms for those of you out there who are RL experts. Please come chat with me or Sergio after the talks, or file an issue on the GitHub issue tracker, and let us know what you think. Thank you very much.
Thank you.
And now I'd like to pass it off to Nick and Yannick, who will talk about TensorFlow.js.
Hey everybody, my name's Nick, and this is my colleague Yannick. We're going to talk today about JavaScript and ML. TensorFlow.js is a library we launched last year. It's a library for training and deploying ML models in the browser and on Node.js. We want to showcase what you can do today with the platform and where we're going. One of the great parts about the library is there's really no drivers installed. If you run it in the browser, you can get out of the box GPU acceleration. The browser itself tends to be very interactive by nature, which builds really great applications and demos for using ML. And privacy is a very important part to the library. You can run inference and training locally on the client, which works around all sorts of privacy issues you might have with doing server-side inference or training. And what can you do today with the library? Well, we have a collection of pre-trained off-the-shelf models that you can use without any knowledge of ML. We also have the ability to take existing Python models and convert them and run them in TensorFlow.js. We also have a full stack for training, inference, and low-level linear algebra, and that runs in the browser in Node.js. And we also have a bunch of platforms that JavaScript can run on outside of just the browser. The first thing I want to showcase is some of our new off-the-shelf models we've launched. The first one, it's a bunch of pre-trained, our off-the-shelf models are a bunch of pre-trained models. They are image, audio, and text classification models. And the APIs are all user-friendly. You don't have to worry about converting images to tensors or resizing. They're very high-level, easy-to-use APIs. These are available on NPM for local application development, or we also have pre-compiled hosted scripts as well. We're also working on this a lot in the upcoming year. We'll have more and more models as we go forward. The first model is BodyPix. We were actually showcasing this at our booth, and I want to show you how easy it is to use this model. So the first thing we need to do is include the library and our BodyPix model. This can be done with our pre-compiled scripts. So it's 2 simple imports. Now the next step is we'll just create an image in the DOM. So this is a body image detection thing. So I have a picture of my toddler trying to do yoga. It's kind of a funny picture that isn't so much a human just like this and finding arms and legs. So this is Frank. He's trying to do something on the couch. But I want to actually load the model and find body parts on Frank. So the first thing to do is to load the BodyPix model, which is a simple 1-line call. And the next step is to call one of the methods we expose, which is estimate person segmentation. And I can pass in a DOM element. This returns a JavaScript object with the width and height of the object or the image and a value for every pixel that was in the image, if it's an arm or a leg or a head, et cetera. There's also a bunch of really easy use methods for doing filtering on the image. So I can take the results of that and then render it directly on the DOM. So it shows head, body, arm, and so on. Another model we just launched just a couple weeks ago is the toxicity model. It's a out-of-the-box text classification model. Again, to use this model, we'll use the pre-hosted scripts, 2 lines of code. And then I'll load the toxicity model and ask the model to classify just some really lovely text, pretty PG, you suck. And I'll get a result back, again, as a JavaScript object that has the 7 labels that we identify different types of toxic type text and the probabilities and if it matches. We also have the ability to take pre-trained Python models and run them directly in browsers. So if you have a pre-trained model today that's already been trained in Python world, we have a command line tool that makes it really easy to serialize the model as a JSON object and the weights and distribute them in a web format. We support save model, TF Hub, and Keras models. The converter itself right now supports over 170 and counting ops. And we will be TensorFlow 2.0 compatible. I want to walk through how simple it is to use this. So I have a Python model. I run it through the command line tool. And then I can easily just load that in my JavaScript application. Very simple. And with that, I want to hand it off to Yannick to walk through our training APIs.
Thanks, Nick. So in addition to working with pre-trained models, TensorFlow.js also allows you to author and train models directly in JavaScript, both in the browser and in Node. The primary tool for this is the Layers API, which is a Keras-compatible API for authoring models. There's also a lower-level op-driven API if you need fine control over model architecture or execution. And we're going to take a quick look at what TFJS code for training looks like. And the main takeaway is that it's pretty similar to using Keras in Python, but follows JavaScript conventions. So the first step is to import the library. And when working in Node.js, you can also use the Node.js bindings, which execute the TensorFlow operations using native compiled C++ code. If you're on a system that supports CUDA, you can import TFJS Node GPU to get CUDA-accelerated performance when doing training or inference. And this is what creating a convolutional model for a classification task looks like in JavaScript. As you can see, it's very similar to Keras code in Python. We start by instantiating a model. We add our convolutional layers, and we finish our model definition by adding a flatten operation and a dense layer with a number of output classes. Similar to Python, we use model.compile to get it ready for training, and here we specify our loss function and our optimizer. And model.fit is the function that drives the train loop. In JavaScript, it's an async function, so here we want to wait for the result or wait for it to be done. Once the model is done training, we can save the model. And here we're saving it to the browser's local storage. We support saving it to a number of different targets, both on the client and on the server. And finally, just like you're used to, you can use model.predict to get a result from the model. So over the past year, we've also heard feedback from the community on ways we can improve the experience of training with TensorFlow.js. And 2 particular requested areas are that of data management and data visualization. So we'd like to show you some of the progress we've made in those areas. So first up is TF Data, and it's an API for managing data pipelines to drive training. It's a JS analog to Python's TF Data and provides a whole set of utility functions for dataset transformation. And finally, it works with streams, and the lazy evaluation allows you to work with data that doesn't fit in memory, which can be quite important. So let's take a look at a simple example. So here, we load up a CSV file using TF-Data CSV loader. And we specify that we want to predict the price column using the isLabel attribute. So this is going to set it as a label in future transformations. So for example, in this map transformation, the price data has been separated out into that Y's object. And the rest of the features are in the X's object. Once we've flattened our data, we can now apply sort of typical ML transformation operations, including things like shuffling, which is an ML best practice, and batching, which will do the work of creating properly sized mini batches for training and know what to pull into memory when the train loop is running. And other kinds of transformations you may want to do here include things like normalization. And finally, we run the train loop on this data set. So model.fit dataset is an analog to model.fit that supports consuming TF datasets and knows how to sort of pull the right stuff into memory as needed. And that's TF data. So the other area we've been responding to community feedback is that of visualization. And the first thing I want to talk about here is TFJS Viz, which is a library for in-browser visualization of model behavior. So with it, you can view training behavior, model internals, as well as evaluation metrics. And we're going to take a look at the first two. So first, we import the library. And here you should note that we do provide TFJS Viz as a separate package. And to visualize training behavior, we can use this show.fitCallbacks function. And we're going to specify a named drawing area to render the charts to, as well as our metrics that we want to see. So in one line, show.fitCallbacks will plot our selected metrics. In this case, our loss and our accuracy metrics on batch end and at the end of each epoch. So this lets us view how the model is converging live in the browser. Lets us adjust hyperparameters as usual. You can also look at model internals with functions like show.modelSummary and show.layer. And similarly, we pass these named drawing areas. And here we see the architecture of the model, including things like output shapes of various layers and the number of trainable parameters. And in this example, we also see the distribution of values in the first convolutional layer of this network, including important statistics like nans and zero counts, which are useful for debugging models. And finally, we also want to announce TensorBoard support in Node.js. Now you can monitor training performance right in TensorBoard when using the TensorFlow.js Layers API in Node. And you can see what that looks like. So a single line will generate the necessary callbacks to write the model metrics to a TensorBoard log file using this tf.node.tensorboard command. Then you can open it in TensorBoard and look at how your training is going, just like you may be used to. And with that, I'm going to hand it back to Nick to talk about some of the platforms we execute on.
JavaScript's an interesting language because it actually runs in a lot more places than you think. There's the traditional browser front for running JavaScript in the browser. We all know about that. Node.js is a big server-side solution, very popular. But there's also a growing trend with JavaScript in more places. One of them is desktop applications. Electron is a very, very popular platform for developing applications. Those of you who have used the Spotify desktop application or Visual Studio Code, those are good examples of Electron. And JavaScript is also moving into the mobile space. I want to highlight a couple of examples that we've seen in the industry on all four platforms. The first is the browser. Our friends at Google Creative Labs have built a series of experiments to explore how creative tools can be more accessible for everyone. There's going to be a great lightning talk on this tomorrow, and I encourage you to go. And they'll talk about everything they've built with this project. Uber has built an in-browser tool for model-agnostic visualization of ML performance. They use TensorFlow.js for acceleration of their linear algebra, k-means clustering, KL divergence computations, and so on. They are also giving a great lightning talk about how they use TensorFlow.js to solve this problem for their platform. And again, this is all in browser. Another really cool industry example is Airbnb. Airbnb built a identity document detection model that they use as a full TensorFlow ecosystem solution. So they On your Airbnb profile, if you were to upload a government-issued ID, is a very big trust and safety issue. So the trust team at Airbnb built a TensorFlow model to detect if a profile picture that you're trying to upload directly in the client contains government-issued IDs. They use this in the browser using TensorFlow.js, as well as on their mobile devices with TF Lite. On Node.js, a good example of this being used in the industry is Clinic Doctor and Clinic.js. This is a Node.js performance analysis tool, and they use our Node.js bindings to filter out GC spikes on node processes that are running to give a true, accurate CPU performance benchmark. And on the desktop, our team here at Google with Magenta and their music generation models have built a series of desktop plugins for the Ableton Studio. So these are little mini applications that are full desktop applications that use the Magenta models and accelerate them all into GPU and desktop applications. And we have a demo at our booth as well for how this works. Again, the really cool part is all JavaScript and GPU acceleration on the desktop with no CUDA drivers all through our WebGL bindings. And mobile is another interesting space. WeChat, for example, is one of the most popular apps in the world. They have over 1 billion total users and have a sub-application platform called the Mini Programs. The Mini Programs are great because it's a no-need install app in advance, use on demand, and it has over 1 million apps and 1.5 million developers. The Mini Program itself is built using JavaScript, and it makes it really easy for developers to create and deploy and share these on the WeChat platform. I actually want to show a demo of one of our TFJS models running on WeChat. So I have just a regular iOS device here, and I'm going to open WeChat. Someone shared with me this TFJS example, and I can load up the application, and it's running our PostNet model. And if I aim it at Yannick here, I can do, yeah, there we go. So this is just purely done in JavaScript, and it's running our off-the-shelf MobileNet model, and we're doing about 30 frames a second. And this is all done with the WeChat JavaScript platform.
Thank you. So all this work over the past year and the fantastic projects created by the community makes us very excited to announce TensorFlow.js 1.0 today. It's available now, and we're super excited to see what the community builds with it and hope that the API stability will make this even easier for developers going forward. And really with this release, we're focusing on two main things: providing a stable API that you can build applications on and make managing your upgrades easier. And we're also bringing market improvements in performance, particularly on mobile devices. And we'll look at that in a bit more detail. So to look at it a bit closer, since we announced TensorFlow.js last year at the Dev Summit, we've been steadily working on performance improvements across a number of platforms. And today we see increases of about 1.4x to 9x in some extreme cases. So this chart shows inference performance with a batch size of 1 on MobileNet in Chrome. So MobileNet is a mobile-friendly image classification model. And we see inference times going from about 15 milliseconds on a modern laptop with discrete graphics to about 150 milliseconds on the Pixel 2. And over the past year, we've been able to do quite a bit of work to improve performance on iOS devices as well. So we're really excited for you to try this. So what's next for us? Well, we want to enable you to execute saved models on our Node.js backend without going through the conversion process. And this will open up many more models to be able to serve using the Node.js stack. We want to provide more off-the-shelf models, like we talked about earlier, to make it easier to build ML-powered JavaScript apps without getting into the nitty-gritty of machine learning models. We're always keeping an eye on browser acceleration proposals, like SIMD and WASM, as well as emerging proposals like WebGPU and WebML. So the browser is only going to get faster, and so will we. And finally, we also want to work on expanding the platforms on which TensorFlow.js can run. So for example, we saw examples of Electron and things like WeChat, but we're also working on platforms like the Raspberry Pi and other hybrid mobile platforms that run JavaScript. So thanks. And for more information about the things we talked about, you can visit any one of these links. Thank you. And last up is Elena to talk to you about her work using machine translation in the Vatican Secret Archive.
Thank you, Yannick. Thanks, Nick. It's great to be here. Just 1 second. So, I'm excited to be here and to talk to you about the In Codice Ratio project. That is a project going on at Roma Tre University, and to talk to you about TensorFlow helped us build a model that is able to transcribe ancient manuscripts in the Vatican Secret Archive. So, some introduction first. This is our team. On the right, you can see paleographers and archivists, and on the left, there's us, the data science team. And that's why I think the name we chose, In Codice Ratio, reflects us very well, because it's a wordplay between the Italian and the Latin meaning of the word codice. Now, in Latin, In Codice Ratio would mean knowledge through manuscripts, but the word codice in Italian also means software code, so it's also knowledge through software, which is exactly what we're planning to do. And so you might ask yourselves, what brings paleographers and archivists and data scientists together? Well, they have one problem in common. They both want to discover knowledge from big data. We are used to think of big data as something that happens in the web, but actually historical archives are endless source of historical information, of important information, of cultural information. And just to give you a scale of how large this information can be, let's just compare for a second the size of the Vatican Secret Archive to the height of Mount Everest. Now, if you were to take each shelving of a Vatican Secret Archive and stack it one on top of the other, you would get to 85 kilometers tall. That is about 10 times the size of Mount Everest. And the content spans the centuries and the continents. For example, there you have examples of letters coming from China, from Europe, from Africa, and of course, from the Americas. So what is our goal? Our goal is to build tools and technology that enable historians, archivists, and scholars of the humanity in general to perform large-scale analysis on historical archives. Because right now, the process, let me tell you, is entirely manual. You still have to go there, consult the documents manually, and be able to read that very challenging handwriting. And then, if you find information that maybe links to another collection, then you have to do it all by yourself. But first, we have to face the very first challenge, that is, when you're dealing with web content, for example, if you want to extract data from the internet, well, that's already text. When instead we're dealing with historical documents, that's often scans. And traditional OCR is fine for printed text, but then you get to this. This is medieval handwriting. It's Latin, a language nobody uses anymore. It's a handwriting nobody is able to write or read anymore, for that matter. It's heavily abbreviated, and still you want to get text out of it. So you might want to train a machine learning model, of course you want. But then we come to the second challenge, and that is scalability in the dataset collection process. Now, the graph you see there is on a logarithmic scale, and it might show you something that you already know, that it's known as the zip flow. That tells you that there is very few words occurring at humongous times, and then most of the words, they do not occur that often. What does that mean for us? That if we want to collect data, for example, at word level, at vocabulary level, this means that we have to annotate thousands of lines of text, which means hundreds of pages. Okay, and similar systems do exist. They are state-of-the-art systems. But most of the paleographers, even when they know of these tools, get discouraged in using them because they say, well, it's not cost-effective for me because it can take up to months or even years of work on these documents just to get a transcription system that they will maybe use once or twice, I don't know, whereas they would like to do it faster. So we asked ourselves, how can we scale on this task? And so we decided to go by easier steps, simpler steps. The very first things that we did was to collect data for single characters. And this enabled us to not to involve paleographers, but people with very less experience. We built a custom crowdsourcing platform that worked pretty much like CAPTCHA solving. What you see there is an actual screen from the platform. So the workers were presented with an image and with a target, and they had to match the target with and select the areas inside of the image. And in this way, we were able to involve more than 500 high school students, and in about 2 weeks' work, we made more than 40,000 annotations. So now we had the data. We wanted to build a model. When I started working at the project, I was pretty much a beginner in machine learning. And so TensorFlow helped me put in practice what I was studying in theory. And so it was a great help that I could rely on tutorials and on the community, and where everything else failed, even the source code. We started experimenting, and we decided to start small first. We didn't want to overkill. We wanted the model to fit exactly our data. So we started small and proceeded incrementally. And in this phase, in a constant cycle of tuning hyperparameters and model tuning, choosing the best optimizer, the best initializers, the number of layers and the type of the layers, and then evaluating and training again. Then we used Keras. It was good for us because it allowed us to keep the code small and readable. And then this is what we settled for. It might look like trivial, but it allowed us to get up to 94% average accuracy on our test characters. So where does this fit in the whole scheme of the transcription system? It's there in the middle, and it's actually, so far, the only neural park, but we're planning to expand, and you will see how later. We will see how later. And so we have the input image. So far, we're relying on an over-segmentation that is old school. It's a bit old school, but it allows us to feed single characters or combinations of characters inside of the classifier, which then produces different transcription who are ranked according to a latent language model, which we also build from publicly available sources. How good do we get? We get about 65% exact transcription, and we can get up to 80% if we consider minor spelling errors, or if the segmentation is perfect. If we had perfect segmentation, we could get up to 80%. We will see that this can be more challenging. Okay, so what are our plans for the future? We're very excited about the integration of TensorFlow and Keras, because I described you the process as being fully Keras. What we actually found out was that sometimes some features were lagging behind, and sometimes we wanted to get to one part of the features or from Keras or from TensorFlow. And so we found ourselves doing lots of, I don't know if that's your experience as well, but we found ourselves doing lots of back and forth between TensorFlow and Keras. And now we get the best of the two worlds, so we're very excited about that. And so how do we plan to expand our machine learning system? First thing first, we are trying UNets for semantic segmentation. These are the same nets that achieved very good results on medical imaging. And we're planning to use them to get rid of this tricky computer vision, old school segmentation. And that would also achieve the result of having classification together, because this is semantic segmentation we're talking of. This is some preliminary examples that were particularly well. Of course, there is work still we have to do. And then, of course, since there could still be ambiguity, we could do error correction and then transcription. But I think this would be, in itself, a significant improvement. And another thing we're experimenting with is enlarging our data set, because we don't want to stick to characters. We want to evolve. We want to move to word level and even sentence level annotated characters. But still, our focus is scalability in the dataset collection, so we want to involve paleographers as little as possible. So for example, this is our generated inputs from GAN, but we're also planning on using, for example, a variational autoencoder so that we can evolve our dataset with little human interaction, the less we can. And in the end, this would bring us to actually use sequence model that could take full advantage of the sentence level context, for example, and could even be able to solve things that we couldn't be able to solve for with single, let's say, with single character classification, for example, abbreviation. In this kind of text, many words occur abbreviated, for example. Just like you would text, in some texts you would say me too and use to, the number, or for you. And that's the same with this kind of manuscript. So, and that's one of the applications you could have. Also, we are planning to use sequence models to get to a neural language model, because so far we only have experimented with statistics. And one last thing before I let you go. I mentioned the people in the team, but there is so many people I would like to thank that were not in that slides. And first of all, Simone, who should have been here, but he couldn't make it, and he was my machine learning Jedi master. And then Pi School of AI and Sebastian Bratiers and Lukas Kaiser for their amazing mentoring. And Marika Shone, who is the high school teacher that actually allowed us to involve those students that work for the platform. And of course, all of the graduate and undergraduate students that worked with us and helped us achieve what we have achieved and what we plan to achieve in the future. And of course, thank you for your attention.
Thank you, Elena. All right, this is the end of day one. We hope you had a great time. A big thank you to our speakers, our staff, our crew, and to the audience here in Sunnyvale and all around the world. And with that, let's take the live stream out with a look at some highlights.
all.